situation is getting better. Yeah, sure. Yeah, they will start it. But if there is any problem, you have my number, you can write me. Like if there is any problem with the timer or anything, and we will solve it right away. Good morning, everyone. I'm very happy to welcome you to day 2 of the 5th annual Floating Wind Europe. I hope you enjoyed the first day and had a restful night. Same like yesterday, please let me share a couple of organizational remarks with you. All the networking and coffee breaks will be held in the lobby in front of the registration desk. Restrooms are located in the networking area on the right. As for the lunch, same as yesterday, it will be served at the restaurant located by the entrance. In case of emergency, please follow green exit signs. I would like to remind you all to fill in the evaluation forms and hand them to my colleagues at the registration desk or to me directly. Your feedback is very important to us. If you have anything you'd like to discuss with us, feel free to speak to me or my colleagues. Our chairman today is Alex Gunt. Alex, the floor is yours. Thank you.
Good morning, everyone. How are the heads? Do we need to test the alcohol consumption levels from last night by doing some karaoke, or are we okay? Good. Thank you, everybody, for coming today to day 2 of the Floating Wind Europe conference from Leadvent. This is the 5th year that we're running this event, and it's been a busy 24 hours. Obviously, yesterday, my colleague Ricardo Rocha ably chaired the event, and I'll be taking over from him and trying to do nearly as good a job as him. That's the bar I set for myself. But yesterday, we covered the market, policies, finance, new concepts in floating wind, and of course, the environmental and permitting side of things. And I can tell you firsthand, angry fishermen is not something you want to deal with on a day-to-day basis. So lots of respect to those people who do that for a living. Today, we're kicking off the day with design and standardization. We're going to talk about some of the technology challenges out there. We're also going to talk about ports and the maintenance and decommissioning of wind farms. We're going to be looking at the full life cycle from the concept through to the operations through to what happens after. A little bit about myself. I'm the head of Offshore Wind UK for Fjordbase. Fjordbase is one of the largest ports you'll never have heard of. And I'll talk about that after lunch a little bit more. 1.5 million square meters of high hard standing capacity port, currently available and working away in the oil and gas sector, but like many of you, trying to find their feet in the offshore wind sector. Personally, I've been in the offshore wind sector for 22 years now. I spent half my career as a developer, making promises that supply chain had to keep, and half my career as supply chain, realizing that developers don't know what they're talking about, by which I mean me, of course. And it's been a bit of a wild ride. I know that there's people in the room who've been in the offshore wind sector since even before myself, Stephen. But the reality is that we're still working out what we're doing in the offshore wind sector, and that's fixed bottom. Never mind floating wind, which we're just kicking off. And there's so much exciting opportunity in the floating wind sector to try and innovate and do things even better than what happened in the fixed bottom offshore wind market. So I'm very excited today to bring all these speakers to you and help curate what will be an excellent day for you all. Thank you very much for your attention, and I would like to invite the first speaker, Henrik, to come up and start his presentation. Thank you.
Thank you very much, and good morning. You are the real heroes of the conference, coming to the first presentation of day 2. So glad to see you, and thanks for a great day yesterday. I really enjoyed seeing the presentations from many of you in the room here. So my name is Henrik Bredmose. I'm a professor at DTU Wind Energy, and I will present some results to you from a project we have running, which is called the Float Lab. And let's see if we can get into the first slide here. So this is me. I already said that. And in my daily work, I'm leading a section at DTU Wind, which is called the Section for Response, Elasticity, Control, and Hydrodynamics. And as one of my former students said, Henrik, that's all the cool topics you need to deal with floating wind. You got a section dealing with that. And I do feel it's a lucky place to be. This project we have, which is called Float Lab, is a Danish project. We have DHI on board, we have Ørsted, we have Siemens Gamesa, Strømning, more partners. Mikkel from DHI is in the room, and I will also point at you later, Mikkel. But today in the presentation, I will talk about, and now I will check if there's a pointer, and there is, some recent results we have got in this project, Float Lab. Some of them deals with storm waves and the response to the storm waves as a function of directional spreading. So what does it mean that the sea is spread for the response? Damping from heave plates is another element. So what does it do to your response to have heave plates, and what damping does it contribute? I will touch on some results for control of floating wind turbines. That feeds into the last point, which is our extension of our lab capabilities to deal with what we call 20 plus megawatt turbines, where we want to deal with control also in that setup. We have worked with floating wind turbine tests since 2012. Most of the work we have done at DHI in a number of test campaigns. So these are the first ones. And now in Float Lab, we then did in 2023 a campaign with the TetraSub floater, a design variant of Stigsdal Offshore's TetraSub floater. And you can see it in the video here, it's plain. It's a pretty large model, it's 1 in 40, meaning it's 3 meters in its scale in the tank, and it has a weight of about 150 kilos in this setup. And we did these tests with the directional spreading. So that means we exert the floater to different wave climates, and then we repeat the tests where the spreading is included. How many knows directional spreading? What is directional spreading? Some of you know. Maybe when we do a simple test, all the waves go in one direction. In the ocean, the waves, they come from different directions. There will be a main direction, but there will also be some changes. So it's the effect of that change we are looking into. So here are some of the results. So we look at spectra here, and then we look at what we call response statistics over here. We have 2 sea states in the picture, many results to look at. But the main finding we have from this is that when it comes to the free surface elevation, so the local wave height, there's no sort of real visible effect of spreading in our tests. When it comes to the heave response, so that is the up and down response, that's the same. That's also what you would expect from the theory. But when you come to the pitch and when you come to the surge, so that means the tilting motion and the translational motion of the floater, you can see some smaller differences from the spreading, and it's a reduction. So that's what you would expect, but you could also have a wish to look deeper into this. Especially you could have a wish to look into the response which is right below the wave spectrum. So at the frequencies where the waves are, and the low frequency response, which is a response where you have the natural frequencies of the floater in the wave basin. And we have techniques to separate that. So that's the next slide here. And that technique is called harmonic separation. It was developed in Oxford. Paul Taylor was sort of the person behind it. And what it is about is if you have a linear wave, so that could look like a cosine curve, then it's known that the second order correction to it will appear at the double frequency. It will add under the crests, it will add under the troughs. So the resulting signal, the one that you will measure in the tank, will look as a blue signal here. And now you can imagine to repeat this test, but with the input signal reversed. So now we do the red test. Turns out still get something under the troughs, still get something under the crests. So actually my second order correction is the same as before. I'm able to measure the red signal in that test. So now by adding the blue and red signals or subtracting, I can actually isolate the initial linear part and the second order part. So in the tank, we did all our tests with the paddle signal and minus the paddle signal. And that allows us then to do this separation. So that means when we look at our response spectrally, we can actually decompose the response into response in the wave frequency range. That's what we call odd or linear response. And in the low frequency range, where the floater actually has appreciable motion, because that's where the natural frequencies are, the second order forcing. And we can look into the response statistics of that. We can see for the odd response, which is dominantly linear, that response scales pretty well with the significant wave height. And that is what you would expect, because it's dominantly a linear process. But then our surprise came in the what we call the even response. That is the low frequency motion, which is second order. One would expect that second order response to scale with hm0 squared. And our results show that that was not really the thing. It is rather a H scaling. And the sort of explanation behind that is that you also have damping in the wave basin. That damping becomes stronger when the C state is stronger. So if you have a forcing that is second order, if you have a damping that is first order, then the resulting response will scale first order like. So an easy way to say that is that we have C state dependent damping. And that's something we have seen in previous works where we have analyzed lab scale data. And all of that calls for better damping descriptions. Because it's not so nice if you, as a design engineer, need to calibrate your damping in the model for each C state. Then you need more lab tests and you need a more sort of thorough way of running your models. So there is a need for better damping description that you can utilize and calibrate from lab tests more easily. We have worked with CFD as well. We developed what we call the FloatStepper CFD code together with Strømning, our partner. There's a paper, there's a GitHub repository. It's an open foam floating body code, and it's very robust, so that's the benefit. And we recomputed some of the lab tests with that code. So in the video here you see a focused wave group, so very isolated event. And then to the right you can see how our CFD results in black matches the experiment in red. So we have sort of the benefit that we are able to run a CFD code, replicate what we saw, even sort of run some parametric studies with that. So the next example here is when you repeat such a focused wave group test, but now with a directionally spread wave group. So again, we have a successful match, and we can study the response in detail. So what sort of study would we then like to make with such a solver? That could be to look into these spreading effects that we have looked at statistically already from the wave tank. So what we did was to run what is called, again, a focused wave group. We look here at the pitch response. So how does the floater react in pitch? And we can decompose that into its linear part, its low frequency part, and its high frequency part. And both of these are dominantly second order effects, and we are able to sort of take them out with this harmonic separation. And then we can run with and without spreading, and you can see there's a label somewhere, maybe it's lost, but anyway, red is spread. And what you see is that the red signal is a little bit reduced, as we also saw in the statistics. Do the same in CFD, that's the right column, and you can see that the CFD solver replicates the trends we see in the lab, and maybe with the strongest reduction here in the superharmonic, so high frequency second order motion. But more or less a confirmation of what we could expect, but now quantified and in a setup that can be used, of course, for other purposes. Our next test campaign, which we conducted 1 year ago, was then with heave plates. How many knows what a heave plate is? I see a couple of hands, fantastic. How many knows what a heave plate is? I see more hands, fantastic. So the heave plate is this device that you mount here on the bottom of typically the buoyancy tanks. And you mentioned it yesterday also. And what it does is that it adds to the mass of water you need to move around when you move the floater. So you sort of effectively increase your mass, and that lowers the natural frequency. And you also get damping. So then we conducted tests with this heave plate, and we looked at both a situation where there was no heave plate and when there was a heave plate. And we have here an example of up and down motion, where we then measure what is the vertical force in the setup. And maybe surprisingly, without the heave plate, the peak force was bigger than with the heave plate. And we scratched our heads a little bit. We could not really understand, why do you get smaller loads when you add the heave plate? It turns out you have two competing force effects here. So there's a buoyancy force and there's an acceleration force from the water. They act opposite. The buoyancy force dominates. So when you add the heave plate, you actually add a force that goes to the other direction. And that's why at this frequency here, low frequency, we see the reduction. We also conducted tests where we had a combined motion of the structure moving up and down and then waves at the same time. So that enabled us to look at what are these effects on the damping that changes when we have the different sea states. So we have many tests where we have this combined motion of the structure in different wave fields. And as an example of our analysis, you could imagine running a test with harmonic waves. You could run a test with harmonic motion. You could add the forces you measure from that. That would give you this signal down here. You could, of course, also conduct the test where you have both the waves and the motion running at the same time. That's the top panel. Now, the difference between that top panel and the addition panel here is then the force that comes due to the coexistence of the waves and the motion. That force has to do with the damping. That's the force we want to describe in the more detailed models. So that's what we're working on now. Control is another issue. I know Axel will pick up on that later in your presentation. But anyway, of course, when you have a floating wind turbine, you have dynamics that is sort of induced by the rotor and its action. What you see here is a turbine that starts up. It spins with the active control system, and you can see how the thrust from the wind actually sort of induces a mean offset both in surge and tilt. And in a moment we will do an emergency stop, and you will see how sort of the turbine sort of leans in to the wind due to that sort of sudden loss of thrust. We don't do emergency stops all the time, of course, with an operating turbine. But still, of course, the control is important because it governs what the forces they look like. So we have done tests with that. And I think for many of you, it's not a new thing that if you put an onshore or even monopile turbine controller onto a floating platform, you will get an instability. That instability occurs when you move sort of above rated wind speed. So above the rated wind speed, you see that suddenly you get sort of big motions in the blade pitch, the rotor speed, and also the generator torque. So you need to do something to sort of cure that instability. What can we do? One of the strategies is to what we call detune the controller. All of this happens sort of in the cycle of the low frequency pitch motion, typically a period of 20 seconds or 25. So if you make your controller very slow, so it cannot sort of react within that motion cycle, then you are safe. But that's the same as sort of compromising your ability to regulate the power of the turbine. That's why we have the controller. So it's not really a desired and final solution. Another possibility is to incorporate, say, the motion of the tower into the loop. So if you sort of feed into the control system the tower velocity, in the fore-aft direction. Put that into the control mix. You can also cure the instability. So here is a test where we have the instability, and then at 90 seconds we turn on this control feature, and that stabilizes the motion. So our goal in this test campaign from, say, some years ago was to show that we're actually able to do this in our lab setup. So we did make a diagram where we could sort of see, you can detune the controllers to make them stable. That's down here. You can also stay with the unstable controller and add the tower loop control, and then you can sort of start to identify these stability regions for the control. Then one could ask, what about the farm level? So if I have a floating turbine in a farm considerations, would there be control aspects I should think about there as well? So here is a picture of the wake behind a floating turbine where the turbine moves back and forth. And what you can see is that this back-forth motion sort of leaves a footprint in the wake. It actually helps the wake break down due to better mixing, but you can also sort of see a footprint of the motion. And what you could ask is it so that the turbine next to it or behind it, could that sort of feel that variation, which is at the natural frequency? Could we risk to excite some resonance down a row of turbines? So we looked into that. Here is a setup where we run the Mira solver. That's a free vortex code, so type of CFD, aerodynamic code. We coupled that with Hawk 2, which is our aeroelastic model at DTU. And in this row of turbines, we then look at the motion down the row. And what we can see is that if you are above rated wind speed, so in this case here, 15 meters per second, you actually get down the row, starting with the black turbine, the first, some motion, ending with the purple turbine, more response. So it is possible to see this interaction. Of course, something to think about when you run a farm. And then out here to the right, you sort of see in a more schematic form how that resonance happens, in this case of 15 meters per second. All right, so the last part of my talk is about what we will do in the lab to sort of extend our lab facilities. That's something we do together with DHI in this Float Lab project. We want to build a new wind generator, and we are also building a new model scale wind turbine. The wind generator is this one. It's a 5x5 unit generator. Each of them are 1x1 meters. It will allow us to generate a shear in front of the rack here, and also it will allow us to actually make a turbulent field. And that's what we're really after, the turbulent field, because that contributes to the low frequency response of the turbine. And we also want to have sort of turbulence that is non-uniform in space. Our pilot unit looks like this. So last year we built the first unit. We did tests where we can sort of correlate what's the fan speed, what's the output wind speed, depending also on the screens we put in the system to sort of kill the unwanted turbulence. We want turbulence, but we want to be the ones deciding how the turbulence looks like. Turbine-wise, we are making a 1 in 70 version scaled of the IEA Wind 22 megawatt reference turbine. This happens in a wave basin. You need to apply Froude scaling to make that work. That puts a lot of sort of demands then on your design. For example, the RNA, so the top mass on top of the tower, 3.5 kilo. So you need to design sort of inside that. But more importantly, the Reynolds number goes down. And that means you will actually need to use a specialized airfoil to get a lift that can give you the thrust you want. So you want to match the mean thrust. You need then to look at airfoil data. This is the low Reynolds number airfoil, and you can see it's not able to generate the same lift as the full-scale airfoil. And that's not because it's a bad airfoil, it's the best you can get, but that's how the physics is when you lower the Reynolds number. So you need to play with that, and the way to achieve a good thrust is to then make the thrust, the chord, bigger. Aerodynamic damping, that's the other part you want to match, because this is about dynamics. First get the force right, next get the damping right. And I have colleagues who have worked with that. they have sort of used this measure here, the slope with respect to blade pitch of the lift coefficient in the transverse direction, as a measure of the damping. You can play with that. It turns out you need to sort of optimize dCl by d alpha, so the slope of the lift divided by the lift itself. And that gives a little bit of freedom. So we have a design now that has sort of the right thrust and a quite good damping. It looks like this, so you can see it is sort of 1.78 times thicker than the geometrically scaled airfoil. That's the best you can do in this condition here. Match the thrust, match the damping with a 25% difference. Still the right order of magnitude, so not too bad. So that's where we are in the project now with our results. So if I were to summarize, what did I talk about now? I talked about directional spreading in storm waves, the effect of that. I talked about damping from heat plates, our analysis of that. The control aspects that we are sort of taking forward in the new setup, where we plan to make the first tests now in May and June. And we do have an open lab invitation, which is out there. Go to the DHI website, have a look, send an application. Then we offer with DHI 2 weeks of lab tests in the new setup if you have something that you think is interesting to test there. And that is my last slide. Thank you very much for your attention.
Thank you very much. I think we've got time for one, maybe two questions. Is there any questions from the audience? Two in the front. It's like we planned it. 2 questions. Good.
Thanks, Henrik. This is Dennis Mata from Ramböll. So we're often involved in design activities for foundations, and I guess particularly the damping topic you touched on is quite interesting, because these are typically the parameters you need to calibrate. So maybe from the testing you've done, and especially this dependency on the sea state, of course, I mean, when we set up our models, we typically use one value there. So I don't know, any guidance or so for like the more practical design aspect when you look at these results? Kind of just what is a recommended way now to deal with that?
I think that the simplest thing one can do is one can simply tabulate what if you have one coefficient, what value do I need as function of significant wave height to get a good match? What we want to develop is an improved force model that actually takes into account this interaction between the surrounding wave motion and the damping. Morrison, with the relative motion term, has some of that, but we have seen it's not everything, so there's more to it. So there are some potential flow effects that we would like to take in and see if that sort of can fix it.
Thanks a lot.
Thank you.
Thank you for a very good, interesting presentation. We are working with different analysis program, OrcaFlex, but in particular 3D float.
Yeah.
And one of the missing links in the modeling is the field data of, if you have, for instance, a regular wave, it's not the same at point A and point B.
Yeah.
So we calculate in a conservative way, having a correlation of 1. So it is exactly the same wave shape there and there. It doesn't matter if the floater is a very small spatial spread, but if we have a couple of 100 meters, that makes some impact.
Yeah.
So my question is, do you have any research program to collect field data to get a better resolution of the metocean data in that respect?
Yeah. Maybe that's 2 questions. So the first one, do we have a project where we look at full-scale data? Then yes, we have collaborated with Stigsdal Offshore. And we have analyzed, also together with the University of Western Australia, response data from the TetraSpar demonstrator, the Norwegian, say, it's placed in Norway. For the bigger mid-ocean part, I don't have a lot there because I'm sort of more local to the floater. But I know DHI does a lot of work in that area. So maybe that could be a place to talk and discuss. Thanks for the question.
Right. Okay. Thank you very much. Henrik. Next, we're moving on to the relevance considering structural flexibility in model tests, floating offshore wind technology systems. Marijke Leijmeister is here to talk about that from the Fraunhofer Institute for Wind Energy Systems, IWES. Marijke, the floor is yours.
Yeah, thank you. Good morning. I just continue with the topic of wave model testing. Thanks, Hendrik. The motivation for my presentation today is when we look at the development of the wind turbines, we see that the wind turbines are still getting larger and larger. And this has an effect on the structural flexibility. So it brings the topic of structural flexibility more into the focus because this flexibility effects is more relevant and affects also the overall system response, loads, motions, and so on. But if we go to the model tank tests, which is a relevant step in the design development of new technologies, we see that currently the models are rather representing a rigid system. Right now, there's work ongoing on modeling the floater in a flexible way, so to consider the flexibility structural characteristics within the floater model, but what to do with the wind turbine. In this picture here, we see a representation of the wind turbine in a model scale, with having the turbine modeled with the 3 blades. We saw it also in the presentation before. But there you need to face some challenges with respect to the scaling, still to represent the correct aerodynamic behavior of the wind turbine. And if you even have to consider that you want to model the right structural flexibility, that's hardly possible. There's another way for representing the wind turbine. I don't have a picture there, but you still have the rod representing the tower. And at the top of the rod, you don't have the 3 blades of the wind turbine. You have a frame, and some force transducers are acting on the frame and are transferring the loads which are normally generated by the wind turbine onto the nacelle point, I would say. So with this, you can represent all degrees of freedom of the loads and motions of the wind turbine. But for this, you need, this is a simulation in the loop approach, because you need to have the knowledge of the force which you need to transfer to the transducers. And these are generated in a numerical model which runs in parallel to the model scale test. And due to the model scale, you have a faster time due to the lower scale. And numerical models are able of being real-time capable, but aeroelastic numerical simulations are more time-consuming, and with this additional time-scaling effect, it's really a big challenge to make the models so fast to capture also aeroelastic effects in the numerical models. So this brings me to the question of the presentation today, to assess if the structural elasticity of the blades and the towers need to be considered in model scale tests of wind turbine systems, and to which degree, because we have the tower and we have the blades. Do we need to consider both, or maybe only one, or for which cases? So that's my motivation of the presentation today. How did I do this? So that was done based on a simulation-based sensitivity study. As I want to capture the effect of having increased wind turbine sizes, where the structural elasticity effect becomes more and more relevant, I investigated 4 different reference wind turbine systems with increasing megawatts class, so using the NOL 5 megawatt, IWT 7.5 megawatt, DTU 10 megawatt, and the IEA 15 megawatt wind turbine. And then I considered 3 different degrees of structural flexibility. One is a fully rigid system. The second one is having a flexible tower, but rigid blades. And the third one is having fully flexible system, so the tower and the blades are flexible. And for the floating system, I was considering 2 different design solutions. Of course, there are many around. We have heard it already yesterday. But I was using the concept of a semi-submersible floater and the concept of a TLP. The reason for this is semi-submersible floaters are at the moment most common system designs and are also expected to be most of the floaters in the future. And they are using catenary mooring lines, and their dynamic behavior and motion characteristics are different to a TLP. A TLP is quite specific with respect to its motion characteristics because it's representing more stiff system because of the tendons. Yes, and for the dynamic motions, which I want to investigate because the floater is moving, I considered the specific eigenfrequency area of the floating systems and also specific frequency values from the wave spectra. Now, I have always talked more on flexibility of tower and blades, but what about the floater? In the modeling, I completely disregarded the floating system itself. I only imposed the pitch motion with specific frequencies and pitch amplitudes on the tower base and made the wind turbine system pitching as it would be on a floating system. Why do I not consider the floater itself? Because right now it's already ongoing that the floating support structure can be modeled with the structural flexibility characteristics. But the floating system is kind of represented because the 2 wind turbines have different control strategies. We heard it in the presentation by Henrik that you need to tune your controller based on the pitch response of the system. And for the TLP, the controller is very comparable to an onshore wind turbine system controller. But for the semi-submersible, the pitch eigenfrequency is more and more important and is considered in the tuning of the controller. So with these aspects, I have a design of experience with a lot of simulations, 147 simulations. And so to summarize, I have in total, I don't know where to point, but I think you can see it. Okay, great. So the 3 different flexibility types, fully rigid, flexible tower with rigid blades, and the fully flexible one. Then the 2 main floater categories, TLP, it's really difficult to point here, TLP and semi-submersible. And for the pitch periods, as I said, I used the eigenfrequencies of the floating system. So those are different for the TLP. Therefore, we have 1 to 5 seconds for the TLP. And for the semi-submersible, we have 20 to 40 seconds. And in between, what is common for both systems, it's characteristics, frequencies of wave spectra, 7.4, 9.2, and 15 seconds. And then for all systems, I have considered 3 different pitch amplitudes, 2 degrees, 5 degrees, and 7 degrees, which are in the operational range of common systems. And it's simulation-based study, so I performed numerical simulations in time domain using in-house tool at Fraunhofer IWES. It's based on Modelica programming language, and because there are so many number of simulations, I did it in an automated manner using a Python framework, which is coupled to the modeling library. And for the analysis, I evaluated critical system parameters during the full operational wind speed range. So meaning I simulated a stepped wind response from cut-in until cut-out wind speed. And what are the critical parameters? So those are listed here: generator power output, rotor speed, aerodynamic thrust, blade root loads, some forces at the flange between the hub and main shaft, and tower base loads. why are those maybe critical system parameters? So the first two, the power output and rotor speed, are mainly getting some information to evaluate the impact on the power takeoff and in the end also the revenue. Then the aerodynamic thrust. This is an parameter which is expected to cause the largest influence on the ultimate and fatigue loads, as well as on the floater motions. And then the last three parameters, the blade root loads, tower base loads, and the loads at the hub main shaft, are also considered to be design drivers in terms of fatigue and ultimate loads. So the simulation was performed for different wind speeds, it's in time domain, and it's with imposed pitch oscillations. And the result, what you get, is some time series which is showing some fluctuations. It's not a sinusoidal response. For this reason, I first made sure that I reached a steady state response and evaluated then the last 100 seconds of the time series per wind speed and parameter. And from this time series, I directly can generate the mean value. So I already have one important parameter, the mean value of the response. And then it's also interesting to get to know the amplitude of this response, but it's not sinusoidal. And there are also many cross points with the mean value, which you can see here in dotted lines. And there are also some small distances between the crossings, which are not really to be considered as intersections. Therefore, I set a criterion: if the time interval between two cross points is too small, I disregard this intersection, and based on the remaining intersections, I first take the absolute value, and then I can average or take from each time interval the maximum value and average this, and this I used for the oscillation amplitude of my motion response or parameter response. So I have two main parameters which I evaluated, the mean value and the oscillation amplitude. And now to come to the results. So first, to look at the general influence of the different structural flexibility types. In general, the degree of structural flexibility mostly affects the oscillation amplitude of the system response. So mostly you have an increasing oscillation amplitude with increasing degree of structural flexibility. Increasing degree of structural flexibility means from fully rigid via flexible tower and rigid blades to fully flexible system. In all the future charts, I have blue for the fully rigid design, green for the semi-flexible one, and red for the fully flexible one. And then there are also seen some additional behaviors, but more rarely. For some parameters, there's also an impact seen on the mean response, and there are also sometimes different impacts and deviating behavior seen dependent on the wind turbine system and dependent on the specific wind speed. Then I also investigated the varying pitch excitation, what is the impact on this? So for the fully rigid system, there's not really an impact if you change the pitch amplitude or the frequency of the excitation, excitation of the pitch motion. But for the flexible system, for both the semi-flexible one and the fully flexible one, you see an impact. And if you vary the pitch period of the excitation of the pitch oscillation, you mainly see an impact on the oscillation amplitude of the system parameters, and most impact is seen during the and the effect of the wave spectrum. So in the area of 7.4 and 9.2 seconds of pitch oscillation excitation, you see the highest impact and the largest oscillation amplitudes. If you vary the degree of the pitch amplitude. So we had 2, 5, and 7 degrees of pitch amplitude. There's in general higher oscillation amplitude with higher pitch amplitude of the excitatory force. And the significance of this impact depends mostly on the system parameter which is investigated. And now the main question was, how does the flexibility effect becomes relevant if we go to larger megawatt classes. Therefore, I specifically compared the results from the 5, 7.5, 10, and 15 megawatt wind turbines considered. That was the wrong button. And I evaluated the results in a normalized manner. So I had the amplitude value and the mean value of the oscillatory system responses and calculated the ratio between this, and later averaged over the different wind speed steps investigated. And those are the results for all parameters. And now I zoom into each single result. First, for the power, we always have the 3 different flexibility types represented in blue, green, and red. And we see that there's, in general, a significant difference for any flexible system and the fully rigid one, and the difference is increasing from 10 megawatt onwards. But there's hardly any difference in the 2 flexible system designs, so either fully flexible or only with a flexible tower. For the rotor speed, it's quite similar as well. The difference between the flexible and the rigid systems are minor compared to the power, what we had seen before, but the difference increases again from 10 megawatt onwards. But there's also not that big difference between the 2 flexible system designs. For the rotor thrust, the systems are quite comparable for smaller wind turbine classes, but again, from 10 megawatt onwards, there's a deviation between the fully rigid system and the systems which consider flexibility. Then I have the blade root loads, and here represented by the flap-wise bending moment. And here it's a completely different behavior. We see that the fully rigid system, the blue line, and the semi-flexible one, the green line, are quite comparable, but there's a big deviation compared to the fully flexible one, but the deviation is smaller for the largest wind turbine class. So that's a completely different behavior. But now for the other parameters, like the drive torque at the hub, it's again similar to the previous system parameters. There's a difference between the flexible systems and the rigid one, but the difference between fully flexible or semi-flexible is not that significant. And here, the difference the increased difference from 10 megawatt onwards is a little bit visible, but not that strong as well. And then I also have the tower base loads here presented the side-to-side force. And there we also see that the flexible systems show different results to the fully rigid system. And here it's also more significance of considering the flexibility of the blades. The general trend is similar for both flexible systems considered, but there is still some deviation between the 2 flexibility types. Yes, so what now to do with these results? Because we want to give some recommendations for model scale tests, for technology developers which want to investigate the system, also with some having the economics in mind, because it's not that simple to use the fully flexible system in the model scale tests. Therefore, I categorized in the two main class of loads, which are normally investigated, the ultimate loads and fatigue loads. And for the ultimate loads, it's in general can be said that the structural flexibility of the tower is mainly relevant. And from the parameter side, it also has the highest impact on the rotor thrust and tower base loads. On the opposite, the fatigue loads, there we can see definitely some additional effects of considering also the blade flexibility. And not all parameters are affected, mostly those parameters which are affected by this aeroelastic coupling. So we saw it in the blade root loads, for example. Those are parameters which definitely are affected by considering the blade flexibility. And in general, regarding the wind turbine size, it's highly recommended and important to consider any type of flexibility when you go beyond 10 megawatt of wind turbine. And so in the end, to summarize, the tower flexibility should definitely be included in the wave bassin tests, and that is also from modeling side feasible. And to still be time efficient and able to consider blade flexibility for specific parameters, it is recommended to use the results from the base bassin tests and later to feed these into numerical models and additional simulations which specifically focus then on fatigue load investigations or specific parameters which are affected by these aeroelastic coupling. Yes, with this, I want to thank you for your attention, and I hope we still have maybe some time for one or two questions.
Dankeschön, Mareike. We've got a question at the front there. I have to say, looking at the lines with the movement on it, and having been part of the team that was commissioning Hywind and seeing how much those turbines move in real terms, and speaking to engineers refusing to climb the tower. Flexibility is on paper, I can understand that. But if you're the engineer having to do the Instandhaltung, you're scared. Yeah. Ricardo.
Thank you very much, Mareike. Just one question. When you started this work, was the Narelle 22 megawatts already available? And if so, why didn't you use it?
No, I started this work about 2 years ago or more. It was already in development, but there were still some bugs to fix, so it was not yet the final stage of reference wind turbine which was suitable for being still considered. But maybe for future research work, yeah.
Makes sense. Thank you.
Any other questions from the floor? Okay. Thank you very much.
Thank you.
Next up, we've got Dennis Mata from Rumble, and he's going to talk to us about the implications of wind turbine selection in different phases of floating wind projects.
Yes, thank you very much. So I'll discuss a little bit, I'll say, the turbine topic now, I guess, from our perspective. So being, I guess, more like on the one hand side on the design perspective, but also a bit from the project development perspective and some of the currently being developed pre-commercial type of projects. So very briefly on Rumble. So we're an international consultancy company. About 18,500 employees. In floating wind, we're now active since 2007, so for quite a long time now. And we're an independent consultant, so we don't have our own foundation concept that is IP protected or that we bring into the market, but we work both on engineering topics and on project development support, a set of some of the currently commercial scale projects in earlier phases, but also bid auction supports. And the presentation here is a bit inspired from some of the things we see in both from the engineering side, but also from the project development side right now in those ongoing projects. So what's motivating the talk? So I guess generally we're all pretty aware in this group here that floating projects are different. So you cannot really use a major oil and gas project template, execution template for them. You can also not really use the bottom fixed templates for like working through such a project. So basically, we're really exploring there a bit of a new area now with these now upcoming commercial scale floating projects. So there's no template. There's a large number of interfaces, larger than in the other types of projects that are much more well known. We have very limited lessons learned, but I mean the biggest project is Hywind Tampen, which is less than 100 megawatt. We have still limited consolidation of technologies, a lot of innovation in the market, and highly increased complexity of the engineering part. And we see once the projects are awarded, there's a lot of pressure then on schedule. So it's a lot of also schedule driven in the projects. And obviously the wind turbine and selection of wind turbine, modeling of the wind turbine, integration into the project execution schedule, all that has a lot of relevance and for those commercial scale project developments. Now, a couple of initial thoughts, I'll say, to a bit set the frame for the presentation. So obviously it has quite an impact on the design schedule. I go into that when I talk a bit about the more T&I related topics and the coupled loads analysis part. Technical risk is an obvious one. The turbine here has a key role in that aspect. The execution plan T&I is obviously quite influenced by the turbine selection. The contracting, consenting, and all the whole topic of actually getting a turbine OEM on board. We heard a lot about that yesterday, so I'll skip that here a little bit. So out of that presentation, it would be just a topic of its own. And of course, we have the continuous topic that also was touched upon yesterday of kind of changing turbines during the project. So maybe you went in with a relatively high rating in your bid, but now these turbines are actually then not available, or you cannot get actually that specific unit. So you have to deal with that. So when we look then at the turbine definition in the different phases and take a design perspective more, let's say when looking at maybe more from the foundation package design side, what do you need, what do you want in the different phases? So in the conceptual pre-feed phase, typically you don't have the OEM on board. So you're working there with those generic type turbines, and you need a good general picture still already on load levels, on where do your frequencies sit, general masses. And then if you move a little more to like pre-feed level, you also already need a control system that you get a picture of your fatigue loading. So that's quite important, and all of that is still kind of covered typically by generic calibrated models. So quite an important topic there to have these relatively well defined. Second stage, so when you go into more like the late pre-feed feed phase, you then have to use coupled models. That means the turbine OEM in some way needs to be on board, or at least you need a lot of information of the turbine that you're modeling. Also the tower definition, come to that later further, is very important. And then obviously in detailed design phase, it's mandatory that for the verification, certification, that you have the wind turbine manufacturer fully part of your design process. When we look then at what's the turbine impact then on the project execution planning, top is basically a bit of a simplified way how it's done in bottom fix. So it's rather separated, so you can relatively easily separate the foundation package, the electrical package, and the turbine package. So you put your monopile in, you lay your cables, and then you have the operation to actually install your tower and turbine. So it's like relatively separate tracks in the logistics sense and the planning. For floating wind, it's quite different. So there you have your turbine package and your foundation package already coming together at the quayside when you integrate both. Then the whole, let's say, T&I process, so the towing to the site or to the wet storage area, we're pre-commissioning, all of that is combined with the foundation. So you have certain limits that your turbine imposes on accelerations, on motions, on loading, also on the processes of lifting and all that, and it all is highly connected actually to your foundation. And then in addition, you also have the hookup of the dynamic cable that's then relevant on the site. So it's just much more integrated, much more interfaces to consider there, also in the project execution part. So that makes kind of your definition and decision for the turbine all the more important. So wrapping this relatively quickly up, so in the early phase, I mean, definitely what we recommend is working a bit more with envelopes. So there is just a lot of uncertainty. So very difficult to pinpoint in early phases what exact turbine are you going to using. So you have to somehow work with envelopes, also on the consenting side. You should still have a good idea generally what turbines you want to use. And then sensitivity studies are also key there, so to get a good idea what is the impact if something changes. And in the later phases, of course, the securing this early commitment, then latest in FEED, to really have a very specific turbine on board and use that. That's very important, but well, no, it's also very difficult. But it is really important. Otherwise, the longer in FEED you have uncertainty, the more difficult it becomes, and the more risk you put also on the schedule and on your technical risks. Talking a bit about integrated loads analysis and the importance. So why is this generally important? I mean, in design loops, typically, the integrated loads analysis part is something like 4 to 6 months. So, and you often have 3 to 4 of these loops. So it has actually quite an impact on your overall project schedule, this topic. So you want to make this as efficient as possible and as effective as possible. We have to do this in floating wind because it's basically, you have to consider the nonlinearity. So you need this model that considers the substructure, all the hydrodynamics, mooring system, flexible tower, the wind turbine in a coupled system. Otherwise, you don't get a good picture on the loads, and it's also required by the standards. So this is why this is mandatory here. And it's different from bottom fixed because you need a model really having it all together in the time domain in one single model. So what do we see right now being done in the market for this ILA process? Is typically 2 scenarios. Either you have one party that's kind of the lead party there doing all these analysis and then providing load information to the other. It's typically then the turbine manufacturer who would run these models and then provide the loads to the substructure mooring designers. You still will have the turbine, the foundation designer still will need some model in-house for internal optimizations, but the calibration can be a bit more reduced and the accuracy requirements are not that high because in the end you will certify basically with that one model that's typically then owned by the turbine OEM and where you plug in basically the foundation model created by the foundation designer. And the second scenario is where you run it in parallel. So basically the foundation designer and the turbine manufacturer both have own models using different tools, but you have to calibrate them in a way that they're giving as close as possible similar results so that the certifier is accepting that and that you also minimize your risk that differences are now driving a technical issues. So, and then it's a lot also about what data can be shared. And we're seeing there are different models, different willingness or openness to share information from turbine OEMs and substructure designers. But this is the scenario we see now a bit more prominently currently being followed. So key questions you need to ask then in your project relatively early on is who's contractually responsible really for that loads analysis, or are both parties responsible? How do you deal with that? What are different parties willing to share? What are the IP considerations? There are some workarounds with black box kind of encrypted models and all sorts of different things you can do there, but you need to think about that early on to avoid any, again, schedule risks. Also, which load cases are run on which side? Do you run everything in parallel, or can you make a reasonable split to again make the process more efficient? Also, how do you integrate the model? So is it all compatible, or do you have another, I don't know, 3 or 6 month period to just get the models together and run them together? You need to think about that quite early. And then obviously it all comes together in having an optimized overall plan, how you deal with that whole ILA process. And on the right, you see a bit of a small example that you have. And as I said, keep in mind, each of these loops is typically 4 or even 6 months in duration. So you want to really have a good plan for that. Otherwise, you run into quite some issues in your project schedule overall. These are, again, a couple of takeaways, what you can do. So really define well your employer requirements, your scope of work. Make sure you align early on that ILA strategy. Also allow for some flexibility in the processes, because things will change. Communicate early with your certifier. What requirements do they have then for the calibration? What accuracy do you need to achieve? Things like that. Make sure those generic models are really accurate enough in the different phases. Once you choose one scenario, stick to it. So don't change between the different ways doing it. And talk to each other, so have workshops really with the OEM and the different involved parties, the substructure designers, so really manage that very closely and well. Have a clear scope split defined so that things are not duplicated, but also responsibilities need to be clear in that overall process. Last topic I want to touch on, last 5 minutes here, is the turbine tower. Another key element, I guess, that's influencing. We heard now from a more technical perspective, I guess, the influence on the flexibility. But maybe from my side, a bit more from a project development perspective, what's important there. So it's basically about this, this kind of small picture there that you see here. So you need basically a separation of your first global tower fore aft side modes from your 1P and 3P blade passing frequencies. So otherwise you get excitation if you're too close to that, and then you get fatigue in your tower, in your whole system, and you have to have this separation. This is influenced by, mainly for floating wind, by 3 different ways, or you can influence that. So it's the turbine characteristics, obviously. It's the tower itself, so tower geometry, the tower properties, and it's also the floating foundation. And I'll just now talk about that a bit in the next one. So the turbine is influencing that, where that frequency is basically placed. Due to the how fast the rotor spins, and the larger the turbines get, the slower your RPM levels become. And what that ultimately means is your window for the soft stiff configuration is shrinking. So it's getting narrower for the larger turbines. And there's some ideas on maybe different tower materials achieving that, but typically you're already there for the large turbines, having quite a lot of challenges to be on the soft stiff configuration. When we look at the tower itself, it's influenced there by, you can play with the diameter, with the wall thicknesses of the tower, also tower length to come to the desired configuration, but then you have all these manufacturing constraints, you have height constraints because of your energy production or also environmental concerns where you have to have certain blade clearances, etc. And then lastly, and I think that's really a key, so if maybe one item is taken away from this talk, is probably that one: how does the foundation influence this topic on where that frequency sits, basically. So it's two factors. So one is the inertia of your floating foundation, and the second is the structural flexibility of the foundation. So basically, the higher your inertia of your foundation, that's both mass and added mass. So it has a hydrodynamic kind of component to it and the structural component. The higher that inertia becomes, basically the lower your frequency, fore-aft frequency gets, and the more difficult, basically, then it becomes to achieve a stiff configuration. And the other effect is the stiffness of the structure itself, the foundation, and the softer, basically, your structure, which is typically in these eccentric semi-sub designs the case, the softer your structural flexibility of your foundation is, that basically is again leading to the fact that you have more difficulties than to achieve stiff configuration, because then you need to make your tower stiffer and stiffer, heavier, larger wall thicknesses, and and this combination, basically, that's one of the key factors that's now leading to what we touched on yesterday, but this consolidation to these 4-column star-shaped concepts. So it's basically a combination of these three factors, and especially how the foundation and this effect of inertia and structural flexibility, how that's influenced where there your frequency separation is. This is really the key why we see now these 4-column designs, at least in the steel domain. So this is one key factor there, and it's really important to be aware of that. And the bigger the turbines become, now the more prominent this topic is actually becoming. So how you deal with that on the tower? It's clear it has significant influence. You need to consider it early, so you need to have a relatively good early definition of your tower. Already at a sufficient level of detail, you need to do analysis. So this whole, let's say, the whole eigen analysis, frequency analysis, that needs to become very early. If you are too long maybe working with some rigid assumptions, you may get big surprises at some point and then have really big issues in later phases. Again, it's highlighting those sensitivity studies that could help you also to understand what's that influence. So coming to a conclusion now, last couple of seconds here. So I said I outlined now different areas where the turbine definition or turbine-related processes are influencing a project. As usual, early planning alignment is key with the OEM. Make sure you are able to manage changes. We've seen this now all the time, that turbine definitions change during a project lifetime, from the auction phase to then the later design phases. Make sure employer requirements, scope splits, all that is also clearly defined. Responsibilities are clearly set. Your calibrations are well done. You work with sensitivity studies, and just be really aware of these effects I outlined before, on that the larger the turbines become, some of these topics just become increasingly important. And I guess final statement, I mean, we're now in the middle of, I guess, looking at different approaches for all of that. And I said there's not really yet a template, but we're really already in the middle of it. And I think in the next few years now, with some of those early commercial projects being developed, there will be at some point then also be some more standardized processes related to that. But right now, I said it's still a topic that's a lot of discussion and different ways to do it. Yeah, that concludes my presentation. Thank you very much.
Thank you very much, Dennis. We've got a couple of minutes for questions, if there's any questions from the floor. We've got 3. We'll start at the front, I think, because your hands went up faster.
It's quite unreasonable to have the wind turbine manufacturers responsible and supplier of the tower. It's a legacy from land-based. It just makes it more complex to plan and complex to. When do you think the interface will be the most natural to take responsible for each and every part, the float, the structure, all the way up to the nacelle, and then the turbine manufacturer taking care of that? That is a necessity, but when will it happen?
Yeah, I'm not sure if we have some turbine OEM representatives in the room to comment on that. But indeed, it's very common practice, and it's indeed some kind of a legacy that the tower is typically part of the turbine supply package, and there's obviously also some revenue generated by taking that package. And of course, there's also some turbine-related equipment in the tower that makes gives some reason why the tower should be in the turbine package. But for floating wind specifically, indeed, the influence is so significant on your overall system that it's actually has more influence than on the floating foundation, that indeed, from a more neutral perspective, I fully agree that it's probably better to put it into the foundation package part. But as said, there's also some openness of some turbine OEMs to discuss that. I mean, we're now seeing also some a bit non-traditional designs with, I don't know, dual towers or lattice towers and things. So there are some things going on, but right now the standard is still tower is defined by the turbine OEM, and then you basically, as a foundation designer, you have to work with that, what you're provided. And there's not too much flexibility. Well.
Sorry, just because we've got online listeners, can we get a mic?
Yeah, so a little bit chicken egg story. Currently, volumes are too low to really develop a floating specific setup, turbine and tower. But at least, yeah, we are making adjustments to the. So I'm actually Erwin from Siemens. Yeah, so adjustments are made, and indeed, also the tower is really different from what we have. Capacity requirements. Also, you cannot really say for one tower setup, you will cover all floating projects. That's also not possible. So it's indeed a bit challenging how to solve this. And also, if you look at spar floater or semi-sub, it's all, yeah, the requirements are very different. So you cannot really have one solution for all. If you look at the tower, at least. So more volume would help.
It's quick, Ricardo, just because.
Yeah, I'll make it quick. But probably we'll have to engage some more colleagues on the audience. I think the big question is we need the information. The resources are limited. the amount of engineering hours that can be put at an early commercial stage is very low. So how can we solve that problem? Because we need information as a developer.
Yeah.
You have a solution, Dennis? That's my question.
Yeah, I said like what was currently in the practical in the project done is you try to work with those hopefully very well representative and tuned generic models to the extent you can in the earlier phases. I mean, it's even more difficult, right, for the turbine OEMs, because in floating projects you often have these competitive phases. So it's actually then you have basically 4 projects in parallel. So a turbine OEM would need to support, I don't know, 3, 4 different designers. So that makes it even less possible or attractive. So therefore you need some ways to deal with that. And then of course in the later phases, then it's really more about this topic on who takes responsibility of the coupled analysis, what information is shared, and how do you deal with IPs, and then it becomes more like more practical. But I think that is both can be somewhat addressed. But of course, the more information you get, the earlier, the better your calibrated initial models are, based on maybe a little more information in the earlier phases. The more you avoid surprises than once the turbine OEM is really on board. So. Yeah.
Very brief, can we execute basic design certification without the OEM on board?
I guess the formal basic design, as it's defined by DNV, I guess you can use a generic turbine for that. But for a proper feed, I guess when you want at the end actually order materials, you need some involvement of the turbine manufacturer. Otherwise, you're running a high risk that things will then suddenly change once they're on board.
Thank you.
It's fantastic debate. I know, Henrik, you had your hand up earlier. Unfortunately, I think we have to leave it to the coffee session to talk about. But really appreciate the debate. Very, very useful, very insightful. Please do continue this at the networking session. Thank you, Dennis.
Thank you.
We'll move on to Axel, please. Axel Viret is a professor at TU Delft, and she's presenting today about the accelerating the deployment of innovations through large-scale hybrid infrastructures.
Yeah, thank you very much, and good morning, everyone. Indeed, this morning I want to talk about a case study of a project that we started a year ago, which is called Hybrid Labs, and which really aims at accelerating the deployment of innovation through large-scale hybrid infrastructures. So this will really, I think, complement some of the talks that we heard already this morning. I think this is a given for everyone here, but this is really the context and the starting point for our Hybrid Labs project is that, of course, we want to accelerate the energy transition in the coming years. But this is not actually only about the energy transition. Here in the Netherlands, we have a North Sea agreement. This is also, of course, relevant for other countries in Europe, in the world. We're actually talking about 3 different transitions that needs to happen simultaneously. The energy transition, but also the offshore food transition, so how we can produce offshore food sustainably and in a profitable way, and also an ecological transition. How can we make sure that in doing all this, we also restore the marine, for example, the marine biodiversity, so the ecological ecosystem around it. Of course, if you look at the North Sea, and on purpose, the image here is on purpose very crowded. You see that this is a challenge. It's really a puzzle because you have these wind farms, sites, offshore renewables, maybe more accurate farms and sites, but you also have, of course, shipping routes, nature protected areas, and many other stakeholders at sea. So, of course, floating wind gives more flexibility in designing your system, in facilitating these 3 transitions, but it also comes with a lot of challenges, that some of which I will talk about in this presentation. It's about accelerating innovations. I'll also show a little bit more later. I'm not going to give details. At the start, the project, as I said, started a year ago. We are actually still going for 6 years, so we have the luxury of really have time not only to develop innovations, but really hopefully to see them also implemented in the waters. We've talked, and of course the key topic of this conference and also my own research area is about floating wind. But actually in Hybrid Labs we cover more broader innovations. We look at other technologies such as floating solar, and which share some of similar challenges and opportunities as floating wind. We look at control system, both for floating but also for fixed turbine, how you can mix the wake faster with novel control strategies, again relevant for both fixed and floating. And we work a lot with ecologists that look at how we can enhance, again, nature, food production offshore with some of these new technologies. Now, again, as a context, when we look at floating wind specifically, as we all know in this room, the challenges are all over the places. From a design perspective, of course, we have many design node cases, much more to consider than for a fixed turbine, and that means, of course, challenges in running all these coupled simulations fast, but also there is a fundamental question of the validity of some of the models that we use there, and that transfer from a fixed turbine to a floating turbine. So these are, from this point of view, actually two different challenges. One is in itself the speed of running these simulations in a tight time frame that our O&Ms have, but also actually the validity of the modeling techniques that we use. And the supply chain challenges, I think, is obvious, the manufacturing, but also the port infrastructure that is needed. Installation is, of course, done differently for floating turbines, currently with towing to site strategies. Again, there are a lot of trade-offs compared to fixed, whether in terms of the floater design that you use, but also this distance to port, the water depth, and the place, of course, the port infrastructure that you have. And then, of course, the operation and maintenance strategies with no controllers being needed, as we saw already this morning, and the O&M strategies there. So in Hybrid Labs, we actually cover these challenges, but if we want to develop these innovations, we need a way to not only model them, but also test them experimentally. And that brings me to the concept of hybrid testing, which was already quite covered in the previous talk this morning. But that's a core to Hybrid Labs. So I do want to spend a bit of time on what hybrid testing actually means. So you see here a picture of one of the wind tunnels that we have at TU Delft. But again, in Hybrid Labs, we work with different set of facilities. And so, of course, when you want to look at some of the, for example, the loads on the floating turbines, or a new control strategy for the rotor, you need a way to test this in an experimental facility. You need wind, but in floating wind, you also need wave currents, and so on and so forth. And in a wind tunnel, you don't have these physics. So as already explained this morning, one way to do that is to emulate digitally all the physics that are not present in the facilities. And you can do that by placing the turbine on what we call an hexapod. So this is a platform that is able to move, and the motion of that platform is driven by a numerical model. And that numerical model essentially simulates all the physics that are absent, but is fully coupled to the aerodynamic loads that you need. So essentially you need to consider a certain sea state for your digital model, but you also need to instantaneously measure the wind loads that act on your scale turbine, and with both information compute, again instantaneously in real time, compute the resulting dynamics of what your floater would experience, the floating turbine would experience. So you need models that are obviously accurate, but also extremely fast. You need to react instantaneously to the actual wind load in your tunnel. So that's what we call hybrid testing. It's really or hardware in the loop, software in the loop. I mean, many different terminologies exist, but it's a hybrid between a physical model, a physical experiment, and a numerical model. I have here videos of how it looks like. We saw some wave tanks, so I think that's nicely complementary. We see here the picture you saw before, which is our OpenJet facility. It's actually the test section you see on the left-hand side, so the wind blows from left to right. We have a floating turbine that moves quite fast because we are operating at a scale down. It's a 140 scaling here of the 10 megawatt DTU wind turbine. As I said, it's fully coupled. So we have a realistic sea states, measurements on the turbine, and then the resulting dynamics being computed instantaneously. We also do wake research and visualization. Unfortunately, we only have one Hexapod at this moment. So as you can see, the downstream turbine is still fixed, but that still allows us to understand what's the impact of some of these wakes dynamics that are different for floating on the loads, for example, on a downstream turbine. Now, of course, as we already mentioned this morning, what is nice about hybrid testing is that this principle can easily be translated into different types of facilities, covering, again, different physics. So in a wave tank, you can have a scaled version of the floater and then emulate with a numerical model the missing wind using a winch or propeller, again, driven by a numerical model. So exactly the same principle. So 3 years ago now in Delft, at TU Delft, I'm based at the Faculty of Aerospace Engineering, so we have the wind tunnel, and we thought, well, actually this principle of what we are building as hybrid testing can be, again, done in the different facilities, and we really built a floating renewable lab that is essentially an upgrade of facilities across faculties at TU Delft, covering these different physics. Wave tanks, I mentioned, geotechnical facilities, different wind tunnel, actually for testing different turbulence inflows or screens of fans that we also heard about this morning. We decided to extend all these facilities with hybrid testing. And then we said, actually, we are collaborating a lot with partners, of course, in the Netherlands and abroad, and again, we could actually do the same with our partners. So we decided to, that was a build-up to what our Hybrid Labs project became a reality, is actually partner with many different facilities due to the funding scheme, mostly in the Netherlands, or heavily only in the Netherlands, with some little partners also in Ireland, developers there, but to really compare results of different hybrid facilities. So you can see it from 2 points of view. One, you can do hybrid testing in different wind tunnels, again, of different scales, sometimes covering different physics, and then see, okay, how small or how big my scaling needs to be, or can be. So you can compare different hybrid testing in different wind tunnels, but you can also, again, compare a wind tunnel hybrid test with a wave tank hybrid test, as an example, and even learn and include physics from these two hybrid testing facilities. And when you're lucky to actually have real data, you can also compare this hybrid test with full-scale data. And again, as a vision, this is really what we want to achieve in Hybrid Labs, is basically embed this real data into the numerical models that can then really enhance the fidelity of hybrid testing. And we don't do that much in Hybrid Labs, but of course, once you have also the full turbine scaled, as you saw, so the screen of fans with a scaled turbine in a wave tank, that's also the last you see here on the right, that's also an option of what you can compare with. So that was, again, how Hybrid Labs was started. So we partnered with industry partners, with developers in the North Sea, some also involved in Ireland, as I say, on the West Coast, that will monitor data, actually starting from this year, monitoring data offshore. And the idea is that from that data, we can enhance the range of numerical tools that we have. So numerical tools, again, mimicking the aerodynamics or computing the aerodynamics, some focusing on hydrodynamics and so on. So you need a range of numerical models that can emulate the physics that you miss in the experimental facilities. And again, you want to use data to actually create surrogate models that can increase the fidelity of your numerical models, importantly without increasing the cost, because you don't have there the flexibility in a hybrid testing setup to be costly. With this range of numerical model, we can then use them in experimental facilities, exactly as I mentioned before, using this hybrid testing philosophy. And so we have a network of hybrid testing facilities working together and learning from one another. So a lot, and over this basically 3 pies, pieces of pies, is really about the infrastructure, the hybrid testing infrastructure. But of course, we want to accelerate innovations, and so that's why we also develop in parallel to these innovations, again, working with our partners, to be able to test these innovations in these hybrid testing facilities. We also do research on the supply chain readiness, so the bigger picture of how we can make sure that these innovations actually are scalable, make it to the market, and then, of course, help the partners, help society to scale up these innovations so that they can be put in the water once they are installed at our sites. Measurements are taking place, and again, that closes the loop. We can use these measurements to further improve the whole infrastructure. So as I mentioned, Hybrid Labs has been going on for a year and will run until January 2031. It's a Dutch-funded project funded by the National Research Council in the Netherlands, so it's actually heavily fundamental research that we do there, but again in very strong collaboration with our partners, and that is really key, is this co-creation of working on helping the partners, helping the industry to really scale up these innovations. And we have 19 early stage researchers who started still relatively recently and does the early stage also of the research here. And of course many PIs, so many staff, permanent staff working in this project. This is not the most pretty slides that I have, but just as a summary of the type of facilities that we have, just to give you a bit of an idea. And of course, if you want to know more, feel free to reach out. So we have 3 different wind tunnels in the project, 2 wave labs, wave current labs, 2 geotechnical centrifuges to test loads on anchor system, 2 structural labs looking at fatigue load, but also corrosion on these structures, 1 environmental facility, 2 power integration system labs, so looking at grid integration, hardware in the loop, also at that, in that field. Installation is also key, so how to look at also floating installation, for example, and 3 offshore demonstration sites. And that's very much driven also by NWO, but our philosophy is impact-driven research. And so we've set the goal and the ambition to really have societal impact. And that means really have a role on accelerating innovations. And that's why this is also why we think that closely collaborating with our partners is essential in accelerating the pace of development and deployment, but also facilitating the 3 transitions that I mentioned, and also, of course, also as a university, of course, help training people to work in this field. As I said, we do fundamental research, and we really look at a number, you can imagine, with 19 PhDs and postdoctoral researchers, we do a lot of different projects. But it's, as I said, a lot about hybrid testing, which means really being able to build this, increase the fidelity of the numerical models that we look at. It's also about doing these actuations in hybrid testing in an innovative way. And maybe on the other side as well, it's a lot about the co-creation, which brings challenges, of course, technical challenges, but also we work a lot with social scientists, for example, on making sure that the technology that we develop can also be adopted also by society, by policymakers, just as an example. And so participation of citizens is there also key. Yeah, I think I will skip this a little bit. It's a lot of text, but of course we are organized in different work packages. And in addition to this, what you could call scientific breakthrough, it's also about development of physical models, of numerical models that can be actually transferred to different facilities. So also there the co-creation is important, having models and tests that we can run in different facilities in a way that can be really compared and that's definitely not straightforward. I just want to spend the last 3 minutes on a few examples of the things that we are looking at. I talked about aerodynamics a lot. That's of course maybe because that's also my own background. But of course these turbines, they are subjected to unsteady loads. We see this in different projects. So another NWO project as well that we're running things numerically, and we want to use hybrid labs also to test these things more experimentally, where we see that if you look at the aerodynamics on these turbines, you see just fluctuations. Of course, it depends on a lot of the parameters, but generally speaking, you have more unsteady loads than on fixed turbines. And again, that requires first some fundamental understanding, but then a way to potentially control these turbines to mitigate these unsteady variations, and that goes back to then integrating this high fidelity knowledge into control frameworks, so fast models again. I do want to mention ecology because this is a big part, of course, of hybrid labs as well. In the monitoring that we do, it's a lot about technical data, load measurements, but it's also about the surrounding ecosystem. And so we work there with our colleagues from Wageningen University, who are developing also innovations in the way biodiversity can be monitored. And so with various different sources, from DNA sampling to video, 360 video recording, and also the citizen science part of, so we have quite some research there on how then to use these novel monitoring techniques also to engage with citizens at large. Of course, it's important, I stress this, the system level approach. So we do a lot of research also on the multidisciplinary design, analysis and optimization frameworks. So essentially looking at these trade-offs. What if my water depth is different, my distance to port is different, my floater is different, what impact does this have on the O&M strategy, for example. This is ongoing research, and research we will strengthen in hybrid labs in the work package 4 on the implementation. But then again, now we add also colleagues, for example, at the Breda University of Applied Sciences, who are expert in, again, making 3D virtual realities of this model. So how we can there also link these different frameworks with getting engagement, specifically in this case, with policymakers. And that's my last slide, and again, maybe the text is not so relevant, but as I mentioned, we have a consortium of 37 partners. You can see their logos here. So it's a big consortium, and they are really engaged and co-creating with us, which is extremely important. We have a long-term vision of really seeing hybrid testing as really replacement will never happen, but kind of a really substitute for full-scale testing. And so we really want to do, of course, innovation acceleration, but also in the way hybrid testing is seen for by certification bodies, as an example. So if you see room in any way for hybrid labs or for partnerships, additional partnerships on how to achieve some of these long-term visions that I stated here, you're of course more than welcome to reach out to me in the sessions also afterwards, in the break afterwards. And with this, I'd like to thank you for your attention, and yeah, I hope we have some time for a few questions.
Thank you very much, Axel. We have time for, I think, one question, if there's any burning questions. So it's an incredible partnership of a lot of companies that you're working with there, and I spotted the whole value chain as well, from the foundations, the mooring lines, all the way up to the turbine. But is there a perfect turbine partner that you would want to be working with to try and create this partnership to the next level, or bring it to the next level?
Yeah, we already have the perfect partners. We have Siemens, and so some of which are in the room. So, no, we already work closely with Siemens, actually, in many projects. Of course, we also have a geographical, we are close by as well in Delft and the EEC offices, as an example. So we've been working with Siemens quite a bit. And yeah, I think this is, of course, that helps us. But of course, as a consortium, we want to accelerate innovations and to have broader impact. So we are always open for further collaborations, of course. But I think what is essential here is maybe going back to the questions before. Of course, we do know that these co-creations are extremely difficult in practice, right? But we see this as really a way to to have more collaboration, have more information sharing in, of course, a way that respects IPs for everyone. But I think this hopefully can come back in a few years with also the fruits of this collaboration shown.
Excellent, thank you. Well, speaking as a former supply chain director for a floating wind developer, one wonders whether Siemens would be willing to sell turbines now that they're part of the TU Delft exercise, as they weren't last year. But hopefully, we're moving in the right direction. Thank you very much, Axel.
Thank you.
Next up, we have José Azcona Amanderaiz, Technical Challenges in Floating Wind Energy Deployments, and he is the Head of Offshore Wind Energy Area for CNER.
Thank you. Okay, thank you. My name is José Azcona. I'm leading the offshore wind energy unit within the wind energy department in CNER. CNER is the Spanish Renewable Energy National Center. So we started with activities on floating wind turbines around 15, 20 years ago. On those days, these were the three main concepts that were considered. Those years, they were not nice renders as we have now. And basically what the community of floating wind energy in those years did was to analyze these concepts based on blade element momentum theory. For the hydrodynamics, we use Morrison formula or potential theory, and the control was basically onshore control with some minor adaptations for the floating condition. Nowadays, we have many different concepts. We have answered many of the questions that we have in those early years. But at the same time, we have many new questions, because as we approach to commerciality, to commercial projects, then we have to be more accurate in our analysis, and also because many of these concepts challenge current numerical models and current tools for the engineering loop. So in this presentation, I want to just tell a few cases of these challenges from our experience in CNER related to simulation models, control, structural analysis, wavefront testing, that I feel that are interesting and maybe nice food for thought. So typically the engineering cycle starts with simulations. So we have many different complexity models for the hydrodynamics, using blade element momentum for the hydrodynamics, for example. If you want to model the wake, then you can use Free-Borchers models, even CFD. And for the hydrodynamics, you have Morrison approach, linear potential, CFD also. The point here is that you have to adequate your model to capture the critical dynamics that you want to analyze with a less computational effort. So relating the hydrodynamics, you may make questions when you are setting up your model related to if I have a slender or not slender bodies, if linear dynamics play an important role, what is the importance of viscosity and damping, and some other challenges coming from hydrodynamics is the large motions of the rotor that interact the rotor with its own wake interactions, the yaw conditions that blade element momentum theory does not capture well, and also aeroelastic instabilities. One example of a critical aeroelastic instability, if you have run load analysis, probably you are familiar with this one, is Irling condition in storm conditions. These are basically the cases from the guidelines 6.1, 6.2, 6.3, where there is an edgewise instability of the blade that is transmitted to the tower, and then you have very high loads. Typically, this case may determine, is sometimes the same driving, and may determine some of the extreme loads. In this video, we have a model using wake theory. We are modeling the wake, but if you compare the results of this, model in orange here with typical VEM, you can see that there is a huge difference in the predicted tower top acceleration. So if you are using the typical blade element momentum, which is the standard for the load analysis, maybe you are overestimating this effect. Relating the hydrodynamics, typically we use potential models, but you have to keep in mind that in some extreme sea states, linear wave theory are not enough, for example, for the analysis of wave breaking, slamming, green waters. So our approach to solve this is to use CFD coupled with OpenFAS, because also the wind turbine dynamics may play a role here. We call this OF2, and it is like a multi-fidelity tool where we can model the aerodynamics using them or also free vortex models, our review in-house model. And we use hydrodynamics we use CFD to model the hydrodynamics so that we can achieve a totally coupled simulation with a lot of detail and including on the viscosity terms and non-linearities of the hydrodynamics on the platform. So moving ahead to control, control for floating conditions have additional challenges compared with an onshore control. Basically, the platform motion introduces additional degrees of freedom with low frequency, which are tricky to control. The control behaves better with higher frequencies. There is an increase in the fatigue, and the control has to try to deal with this. And also, these concepts are more prone to present the misalignments with wind, and also the control has to ensure the safety in harsh conditions. You have probably seen some concepts now that are approaching to commercial. Even there are some prototypes, at least in Spain, that use this approach using a single point mooring, which is basically that all the mooring lines are connected to one single point so that there are not a stiffness in the yaw motion of the platform. So this allows the platform to align with the mean wind direction if you have enough drag. But you have to keep in mind that sometimes if you don't have enough drag, these systems may misalign with the wind because there is some part of the rotor moment is projected in the vertical direction due to the tilt angle of the shaft. And although this projection is very small, the mean is not zero. And as you don't have a stiffness at all in the yaw degree of freedom, with enough time, as you can see in this video, with enough time, the system will misalign with the wind. Our approach to solve this issue is to implement IPC control, individual pitch control, in order to make the system to keep aligned with the wind. You can see on the left we have the baseline controller, and with enough time you have a yaw misalignment, and on the right side you have this individual pitch control that allow us to keep in the direction of the wind. From the point of view of control, this also multi-wind turbines concepts, that there are several concepts, is also very interesting because you have to add an additional layer of control. We call this in CNR coordinated control library, and this basically coordinates the two individual controls of the two wind turbines, so that if something happens in one of the turbines, for example, an emergency stop, the other one has to react consequently. And this also opens the door to introduce a control of this system based on differential thrust of both rotors. This is something that we are looking at, but it is quite challenging because you have to be very sensitive with your control in order to be able to introduce the adequate differential thrust between the two rotors. You have to keep that differential thrust for enough time, and there are a lot of disturbances. And also you require a more complex model in order to verify the accuracy or the efficiency of your control, because these two rotors are very close and there is an interaction between the wakes. So you need to model the wakes, and you need to model how this wake interaction is affecting the thrust in both rotors. Okay, structural analysis. This is quite a hot topic in our customers, I think, now, because as a certification phase approach, you need to take care of this issue. The challenge is that, of course, you have many different domains here involved. You have to apply all the engineering knowledge since the hydrodynamics until the structural dynamics. You have to do calculations with hydrodynamic meshes and then transfer all the information to finite element momentum meshes. There are a lot of simulation cases involved that are required by the guidelines, and this is a high cost in CPU and memory effect. Here I want to show you this structural analysis that we have performed for Veridi. Veridi is a Spanish engineering company. They have developed hexagonal shaped concrete platform. They don't use pretension of the concrete, and as you can see, they have here these external tanks are not flooded, and they wanted to check that the water tightness of these tanks. And to guarantee that water tightness of these external tanks, they want to check that there is no reversal in the bending moments on the walls. Because if the bending moment in the wall is always in the same direction, then you always have a section of your wall in compression, and this ensures the water tightness of the tank. And they wanted to check that it was not needed the pretensioning of the concrete to have a very cost-effective platform. So what we did here was, well, we performed the integrated analysis of extreme DLCs using OpenFast, and we identified the critical cases. And then we map the pressures to the hull. To do this, many commercial codes do not include this mapping of the pressures, so we develop our own in-house tool, which is called Pandilo, Panel Distributed Loads. It is based in linear potential theory, and it is very efficient from the point of view of computation, but it works as a post-processor, so it is also very convenient because you can run your load cases, identify which are the critical cases, and then focus on mapping the pressures on those cases. So once we have the hull pressures, then we transfer the loads together with the other loads coming from the integrated analysis, the aerodynamic loading, moorings, hydrodynamics to the structural mesh. This is quite a detailed structural mesh because they are very small pieces of concrete and also some pieces of steel to reinforce the concrete. So you have to be you have to provide quite a detailed finite element momentum, finite element method mesh. So once you perform the FEM analysis, we obtain these bending moments diagrams. This is the horizontal one, and this is the vertical one. And to do the analysis, we look at certain sections of the platform. For example, when looking to this section, we analyze which were the envelope of bending moments in this section, so which are the maximum and the minimum bending moments in that section. And we concluded that as you can see in this plot, there is not a change in the sign of the bending moment. So the maximum and the minimum presents the same sign. There is not a change in the sign, with the exception of this area here, which is the top of the platform, and where corresponds to this zone. And here we don't have a very large bending moment, so this is not critical. So the conclusion is that it was not necessary the pretension to guarantee the water tightness of these tanks. So this was an example of ultimate loads analysis. When you move to fatigue, you have to look not just to certain time stamps. You have to perform a detailed analysis of the hydrodynamics, and you have to obtain the stresses in the structural states of the material for all the time series. You have to apply, the rainflow cycle algorithm to evaluate the fatigue. So you have to analyze not just certain time stamps, but you have to analyze the complete time series. So that is very challenging from the point of view of computational. So our approach here if this is basically the workflow that you apply in the structural analysis, you perform first the integrated simulation, then you calculate the pressures, and together with the rest of the loads, you perform the finite elements analyze. In order to accelerate this, we have introduced here artificial intelligence algorithm, basically neural networks. I know there is a hype with artificial intelligence, but they are useful, really useful tools. So, for example, to calculate the pressure, distributed pressure in the surface for one case, we have applied these neural networks. You can see here the results using the potential theory, and here on the right using these neural networks. Here, this graph is the total force resulting from all these distributed pressures. And as you can see, there are no great difference. We can achieve a very good accuracy using these algorithms, but the difference is in the time of calculation. So for one load case of 3 hours, we need 1 hour of computation in one regular laptop to obtain all these distributed pressures in time. But if we apply these neural networks algorithms, we can do it in 21 seconds, so it is a huge difference. So this is the approach that we are taking for fatigue analysis. Several speakers have talked about hybrid wave-time testing. This is an area that I like a lot because we started very early with this topic. In 2011, we performed the first hybrid testing. Basically, the topic has been exposed. Basically, there is a conflict in the scaling of the hydrodynamic and the aerodynamic loads when performing floating wind turbines scale testing. You cannot scale both forces at the same time. So one approach is the redesign of the rotor for this low Reynolds, or the use of wires. What we did is to use a ducted fan to introduce the force during the test. So this ducted fan is driven by a simulation of the rotor dynamics, and this simulation computes the rotor loads in real time, coupled with the motions of the system in the wave tank. So as we started with a ducted fan, so that means that we introduce only the force, one force, the total rotor in the test. But as we start performing different tests, we perform tens of them for many European designers. We realized that it was needed to include also the rotor moments because our customers request us more detailed analysis and more detailed test cases, and also because these rotor moments are relevant in the dynamics of certain platform designs. For example, this is an example of a hybrid wave-time testing that we perform for X1 wind. This is a downwind turbine with single-point mooring system that aligns with the wind using the drag of the platform. And we performed these tests like 1 year ago, more or less, and we use this drone that we built with drone components, and we introduce the rotor moments using differences in the thrust that is introducing each of these propellers. This is quite challenging for the system because it requires, it is more, the actuator propellers are more demanding in terms of amplitude of the forces and also in frequencies. And also it is needed a very accurate calibration, because if you introduce a certain imbalance, then you will have a problem in your dynamics. This is an example of what we get in this test. In red, you have a case where wind and waves are aligned, and in blue, you have a case where we introduce a misalignment of the wind, and you can see how we were able to capture the dynamics of the system and the platform aligned to the equilibrium position between the forces coming from wind and from waves. And yes, last slide, we are also applying these artificial intelligence techniques for the operation and maintenance methods, basically for applications related to health monitoring system. This is how we plan to monitor the stresses inside the materials in a real in a platform operating in sea state. We are able, thanks to these neural networks and feed it with the sensors of the system, we are able to evaluate the stresses in real time, so that we will be able to monitor how is the life consumption of the asset in time, and give indications of when it is advised a monitoring or revision of the system. And we also plan to use this for the evaluation of different failures that may happen on the mooring lines, such marine growth or loss of stiffness, whatever. So with this I conclude. So as I mentioned, there is a variety of concepts worldwide with a wide range of development of TRL. They have many common challenges, but also very specific challenges that we have to address with our engineering loop. Co-design, as has been mentioned several times, is crucial. You have to take into consideration when you perform the design all the aspects related to hydrodynamics, aerodynamics, but also to the transport, installation, the commissioning, circularity. We are conscious that we have still a low track record. We don't have too many installations operating in sea, and we need that in order to improve our reliability and also probably to reduce the cost. And there are other many challenges that can have an impact on reducing the cost of floating wind turbines: industrialization, standardization, transport, circularity, and of course social and environmental aspects. So thank you very much for your attention.
Thank you very much, Jose. Any questions? We've got time for two or three questions.
Hello. I was wondering, you mentioned the yaw control in an earlier slide. In controlling the yaw, also the yaw control of the wind turbine generator plays a role. Did you get any relevant information from wind turbine suppliers on how they would approach such a controller?
You mean the single point mooring or the multi-wind turbine? The single point mooring.
The multi one is a bit too far out there, I think, for now. But
single point mooring. Well, I think this is a common challenge in the community. It's hard to get detailed information from OEMs.
I agree.
For that particular case, the analysis was with a generic wind turbine. I think it was the 10 megawatt reference wind turbine.
The standard controller?
Yeah.
Okay, thank you.
A nice presentation, Jose. Just a question on this AI-enabled load mapping. I mean, where I guess we are and others are working on different, I guess, approaches there, and it's a very relevant topic. I don't know, like, my question would be more related to the reliability. I understand you kind of train that mapping, basically that AI system or neural network to map the loads based on some training data, and then you apply it for other results. And also in our discussion with certifiers, so I just can expect a lot of questions and on how reliable is it if you replace it completely with that mapping for, let's say, a full load case set. So I don't know if you can comment a bit on that.
Yeah. So here we have two levels. We have the potential model and then the trained neural network. So for the potential model, it is validated according to the theory, and we have so we are full confident. If you are confident with linear with potential theory, then it is the same formulation with more detail. The problem comes when you have to analyze lots of hundreds or thousands of fatigue cases, and you have to analyze all the time steps of these cases. Then this is research. I mean, this is our proposal. We plan to use these neural networks not only for the pressure but also for the tension, in order to be able to be very fast. And of course, we will require a lot of validation to be sure of what we are doing. My impression is that if you are working with more or less linear models and you are training your neural networks with enough cases considering all the directions and whatever, I think that you can be quite confident with the results.
No, thanks. Yeah, very interesting approach, definitely. Thank you.
All right. Well, thank you very much, Jose.
Thank you.
So we're changing tracks slightly with the last presentation taking us up into our networking break, our coffee break. And we're going into the industrial approach to making floating wind, offshore wind relevant. And a tip for the insiders, if you're really nice to Kenneth, he might give you one of his lapel badges, which I managed to get.
Sorry, I continue.
If they're really nice to you, you might be able to get a badge.
Yeah, we have a few pins left, so okay. First of all, thanks for having me again. I was last year, held a speech also on the same event in Berlin that time. Quite interesting. I spoke about Goliath wind that time as well, and that was just before we had submitted the NOVA application. And 3 days later, we were awarded 175 million euros of grant from the Norwegian government, which is a significant boost to the project. So I'll talk a little bit more about that project, but also the importance of those kind of incentives to kind of enable activity in the supply chain, and also get things going in the floating wind industry. I'll say a little bit about who we are, what we do, how we approach this industry, and also the kind of type of projects we have and how we put our philosophies into practice. I can also mention that we have Jon Nysæter here, my colleague, who's our technical alibi for the day. So feel free to reach out to any of us later if you want to discuss anything. Just before I start, I'll just say a little bit, there's something going on in the industry now with consolidation. We see that there's a lot of players kind of having second thoughts on floating wind. I started floating wind 4 years ago when you could list a PowerPoint basically on the stock exchange and raise a lot of capital. There's kind of been quite a change in sentiment since that. We see E&P players moving towards E&P. We see typical renewable majors maybe moving a little bit more back to bottom fixed, taking a pause. We think this is temporary. We don't think it's necessarily what's going on in the long run, but we see that some are pulling out. This creates what we call a vacuum. Because you have a lot of early phase, or you have an ecosystem that develops floating wind. You have a lot of early phase developers that sit with projects that they made consenting and grid for and kind of matured the seabed and so on. And then they need more, what you can say, heavy capital, industrial capacity and those kind of things to drive the projects forward when you come to technology, more advanced technology, when you get into supply chain and you're supposed to make cases bankable and develop business case and so forth. Odfjell Ocean Wind has kind of taken, to some extent, that position. That's also where we see we are relevant and where we team up with different players in the value chain. So our approach, what we are doing, we're basically doing 3 things. I'm responsible for our project development activities, where we take equity in projects. We realized that we need to have a hands-on to this approach. We started as a floater designer. We also do some what you can say, EPCI management and supply chain project execution based on our experiences. But we see that we need to have hands on the wheel because this is a nascent industry. You cannot take bottom fixed approaches into the floating wind. It's a completely different technical discipline. It's also at a completely different level in terms of how mature it is. So we have seen that we need to have an active approach. We need to be in the projects, we need to be in the boardroom, and there's so many dynamics and so many changes, meaning that we have to take an active approach. And ref what I mentioned initially, we see that there's a new ecosystem being established within the floating wind industry. We see that we can team up with early phase developers. The early phase developers comes with grid and consenting and supports on the business case, while we come with, as I mentioned, the technology and supply chains to bring these things forward. And then also a reference to what I saw with Westwood yesterday, which I think was quite interesting, the reflection on Norway versus Japan. As you can see, we have quite a lot of Japanese investors in our company. The Japanese have a significant need for developing floating wind because they don't have a choice. They need that for energy security perspectives. They don't have much supply chain, they need to learn, so they need to be brought into the projects. Norway, maybe a bit the opposite. We have a significant supply chain and we can bring a lot of things from the oil and gas industry, learnings that we can bring into the Japanese. But whether there will be a big, large Norwegian industry within floating wind is yet to be seen, because we have already a surplus of power. So that kind of mix is quite interesting, and I've seen that firsthand. I was in Japan a few weeks ago, where we had a significant delegation that has just been built on a few years with Norwegian and Japanese collaboration, just being established with that. So I think when you see the new ecosystem, that is something I think is key to see how we can kind of blend the right players together. I will also mention another thing, and that is I was part of a panel debate when the UK launched their industry growth plan. And there's another factor in this, because when the big players exiting, the vacuum created also requires risk capital. And what I see the UK is doing, I think they're doing some right moves. They're bringing in the state into the project. So they're enabling institutions like the NWF and GB Energy to take equity position and be part of de-risking the projects. We have seen a similar thing in the oil and gas in Norway, where the state has participated to be part of de-risking and establishing industry. So this is also a possibility for the state to not only hand out grants, but be part of taking the equity and also reap the benefits, because they will also be part of the revenue. That has worked very well for the Norwegian oil and gas model. We see it now coming also as part of the ecosystem evolving within floating offshore wind, which we think is quite encouraging. We think is also needed in order to realize this industry. So where do we come from? 50 years ago, the oil and gas industry was established in Norway. Then the Americans came dragging with their rigs from Gulf of Mexico, and the Norwegian kind of scratched their head. Okay, this is not going to work here. We need rigs that are robust for the harsh environments that we have in the North Sea, and also later up in the Norwegian Sea and so forth. So that kind of brought Odfjell into the floating wind industry, and we've been part of that journey from the late 60s and until today. So today we are still operating 8 units, 4 that we own ourselves and 4 that we operate on behalf of others. And we have been part of developing and maturing all of these as we have that experience. Then in 2020, we also bought a company with floating expertise. So basically the team that designed the Hywind Tampen and founded Inocean, so senior industry specialists that have more than 20 years of floating wind experience. We brought that in together and have combined that into Odfjell Ocean Wind. So we have kind of both the experiences from the floating domain and also the floating or the wind domain. So we like to show this because this is what we think floating is about. Floating is challenging and it is not necessarily for everyone. It's a completely different discipline. What you see here is one of our drilling rigs that's being mobilized down to South Africa to drill one well and then mobilize back up again to North Sea. Because Odfjell is the only company that's qualified to do that job. The marine riser you can see here is holding a BOP in position 2,000 meters down to the seafloor. That's a 15,000 PSI rated BOP, and it's in 6 to 7 knots of surface currents that you can see here, so it's almost like operating in a river. The rig is not moored, it's in DP mode. So that is kind of the skills that we bring into the floating wind domain, having operated for the highly demanding customers like Equinor, Shell, and so forth. That's what we bring into the floating wind domain. So we have developed our own floating floater design. back in 2021, we started to work with Siemens Gamesa because we saw, and I think this was highlighted also by the gentleman from Ramboll, the importance of working early with the OEMs to make sure that you do things properly. So we brought in DNV to have the kind of maritime certifications processes, but we also brought in Siemens Gamesa, and we've worked extensively with Siemens Gamesa, having access to the turbine and so forth. We started working with 11 megawatt. We put the tower in the corner and started to work with that solution. We saw 2 years ago, after working quite a lot with Siemens Gamesa, again showing the importance of working, we saw that this may potentially work for 50 megawatt, but it doesn't scale. So we saw that we had to move the turbine into the center. And that was quite an important change because we had to move it because we need to make a product that's relevant not only today, but also for scaling on the turbines, and we see the development and so forth. So having that experience, to be one of the few companies having access and a fantastic collaboration with the Siemens Gamesa team, has been very important in our kind of basis to develop our floater design. And then we're also very into this structural integrity. So, for example, when we have operated at our operating units, we just retired, a few years ago, we retired the steel rig. That operated for 37 years before we retired it. And it was the market that retired it and not the condition. So to having also this operational philosophy on how you can have these to last for a long time is also embedded in how we work. So we do this multi-locational approach because we see the enormous amount of engineering hours that this requires just to do the same exercises. Whether you're building 5 or 500, it's the same engineering resources required to qualify. So we have mapped all the locations and met ocean data where we operated with our rigs, and we also added typical hotspots like Celtic Sea and west coast of Ireland and so forth, and areas where we see that there is a potential for floating wind. And we have developed a multi-locational approach more into this product basis. So having a broader design envelopes, meaning that, of course, you get a little bit of a higher weight and so forth, but you get something that works everywhere. And when we designed our drilling rigs, we didn't design them for one location. We designed them for working in a broader envelope. So this kind of philosophies that we bring in on a product thinking and also to qualify something once is something that we think would be key, because it will also save a lot of time because you can have a qualified design. Then we've also seen that we start with, rather than start with the easy location and then go to the difficult one, we start with the difficult one and then we go to the more kind of benign areas. So we have, until now, we have had a harsh environment design, but we are now also maturing a deep sea benign, more adapted for these kind of Mediterranean conditions where you don't have these extreme weather conditions. So that's something that we will come up with relatively soon. You will hear more about that going forward. So the way we work, we have this floater and mooring design at the core. That's our philosophies in terms of how we also put the operations and those kind of things into this from at the start. We also, the way we work in the projects, we also look at, okay, what's required from a bankability perspective and looking our way back from the requirements from insurance and so forth and looking back to what is required. Then we build a supply chain around that kind of part where we are the EPCI manager. So we try to build a supply chain that can deliver our technology so that we have kind of a product, but also a delivery model. And then we also add this kind of operational part, and where we also believe we should be very well positioned, since we also have this, what we call license to operate. We both operate in the UK and Norway. So we have this kind of operations part that we also bring into this. We have two projects. First, we have the Goliath Wind, which is a demonstration project, and then we have also the Utsira Nord application, where we are part of a consortium. So this is our current positions, but I can also say that we are in active discussions looking for internationalization, so we will probably expand more. We have long-term owners that want to kind of be in the floating domain, so we are looking to expand more internationally, and there's more things coming. But for current, we do have these two projects in our portfolio. The Goliath Wind, just to start off there, Norway is a little bit special. It's the only place where the oil and gas has been using electrification. So the oil and gas industry is actually electrified with power cables, meaning you already have the infrastructure in place, which is a fantastic opportunity. Many of these are AC cables. So there's 1.6 gigawatt of cables that you can basically put the wind farm into and then deliver power to shore. So you don't have to build anything, the grid is there and so forth. So this is a fantastic opportunity from a project development perspective, where you can actually just connect to a platform. So the project that we are developing is the Goliath Wind, and there's quite a lot happened there since the last year. I mentioned initially, we have received this grant of 175 million euro. We are continuing to mature this project with 4 to 5 units. It will depend on the VTG make, 4 to 5 units linked up to this FPSO. So there's an oil and gas FPSO that is powered from shore. So we utilize the existing infrastructure for that one. We have also done all the EIA, or environmental impact assessment. We were the first project now to submit concession application in Norway, actually before the bottom fixed project. So we expect to have now the concession in place for late 2025. We have the grid confirmed with Statnett, which is the national TSO. We have grid confirmed with the regional TSO. So the only thing lacking is to get the final grid with the oil and gas facility, which is a process that is ongoing, but the intention is that we will get that in place. So quite a lot has been in place. Supply chain, I'll come to our next one, but the project is maturing quite fast, and we are now on target for a COD in 2029. Supply chain, very important. We have developed or worked quite a lot with the supply chain. We realized to find that EPCI is quite impossible. The risk premium is too high. Competence is not there to deliver EPCI. So we have ended up with a multi-contracting model. That was also discussed a bit yesterday on the different sets, but we have ended up with a multi-contracting model where we have been on RFQs on more or less all the packages. So we're kind of evaluating the feedbacks here. And again, the government and the Enova is very important in order to get the engagement and see that you can enable the supply chain. So we have gotten a significant amount of interest and high quality in the bids and so forth. And that's also very important in terms of maturing the project and seeing what is possible, and also when you enter into these bankability discussions and so forth. So when's the time to scale to the gigawatt projects? We think that if you look at the projects that have been done, there's many good projects, a lot of good learnings, but the largest VTGs is it 9.5 or something like that? That's the largest VTGs that have been deployed in the water. We think that before we scale on size of the parks, we need to develop the relevant technologies, and what people are talking about now is 15 megawatt plus. So we need to demonstrate that through smaller projects. We also think it will be challenging for the public opinion to be able to have to put up so much support for large projects that have so much uncertainty. So we think that you have to de-risk this through test and demonstration projects before you move to the larger one. So this is what the Goliath Wind, we think with Goliath, the key things the Goliath will do. We will demonstrate the relevant turbine sizes. We will demonstrate floating wind in the harsh environments, which is key because that's where the wind is. That's where a lot of the projects will come. On the bottom right, we will demonstrate supply chain, and we will also demonstrate the floating wind in a multi-locational perspective, meaning if you can use that as a product or a kind of a delivery setup, you can significantly reduce the time required to mature a project to FID. And that also has implication on capital cost, de-risking, bankability, and those kind of elements. So we see that there's a significant reduction. There's of course a higher cost per megawatt probably on the smaller projects, but the learning and the effects it has on the later project is quite significant. We see convergence, that has also been talked about, steel, semi, center tower and so forth. When we see a convergence on technology, we can also start to talk about industrialization, because then those who are going to build this and build the factories that will last for a long time, at least they have an idea of what is going to be built. So we think that the convergence also creates an opportunity, but you still need to have projects because it's simple. The supply chain won't work without projects. So we have started, we have this is long-term vision on the factories, how the end game will be, but we started to team up with, or have worked quite a lot with Prodtex, which does automated fabrication, robot welding and so forth, so quite interesting technologies that we see can be applied. On the right-hand side here, you can start to see one of the fabrication lines for braces. We think we can start to implement those kind of technologies. We start in the small, we start a little bit with assembly sites, we start with doing smaller technologies and small steps further, and then gradually expand this. But we think we need to use these test and demonstration projects. Once we have projects, we should also use them to develop also the fabrication part, because we think that if we are going to do the journey with bottom fixed had to do 10 gigawatt before you saw costs falling significantly. We've only done 200 megawatt in the floating wind. So we think that we need to do more projects, get more learnings, but you need to have projects because that's when things happen. There will probably be some scaling as well, but to have a solid project pipeline, deliver projects, we think that it's possible to reduce the LCOE and then make the floating wind not great again, but relevant. So I think that's 40 seconds left, so I'll stop there. So thank you for the attention.
Thank you, Kenneth. We've got a couple of minutes, so 2 or 3 questions. One from me then, if I may. You talked about trying to design a solution for the worst locations, so I'm assuming highest wave action and worst winds and stuff. Does that then translate into a heavier, more expensive structure as well? And then how do you balance that value proposition against, say, very light, very flexible structures that are coming in at low cost?
Well, I think the way we do it is that we create this broader envelope to kind of qualify the solution for a broader set. And then that will be a trade-off. What do you do? Because if you are at one of the most extremes, you will probably go with the standard solution. But if you have a location and also maybe a volume, there's a full opportunity to do a project-specific optimization on that one. And that's also something we are looking at, for example, for the Goliath, to more optimize the solutions, I think. But the basic here is to kind of qualify a general solution that can be applied. So you basically have the product, and then you have the optionality, and you can assess from case to case. And then we see that when you get to the Mediterranean, it becomes such a stretch. It's kind of a different ball game. So we need to kind of we have found out, okay, let's create a specific version for the benign, and then we can do a variance within that.
Thank you. Henrik.
Hi, I'm Henrik from DTU. Thank you for your presentation. I'm curious to see your solution, which is a welded steel solution, and I like to see your considerations on the manufacturing, but still I'm curious, how long time will it take to build like a 50-unit farm eventually, and what has been your thinking about this technology versus bolted solutions that can be connected at the key?
Mm-hmm. I can first take the bolted versus welded. Welded is what we have done, and we believe that is from a long-term duration and operational perspective. From the way we see it, that's kind of what our philosophies support, and that's kind of what we will work with. So that's kind of embedded in our philosophy. When it comes to this wind steel, I think that is, of course, a very good question. But I think you can find inspiration from oil and gas on many things, particularly on how to do it technically. But then on the industrialization part, I think we have to look at other places. So what we have done is, for example, to look at, okay, how does Airbus do it? They produce 600 a year of this A320. And what they do is actually they create this system where they have different assembly sites, so several sites that you can do assembly, and then you have different parts being produced at different sites. So what we could do in Europe, for example, that we foresee is, for example, we could have a brace factory in Norway, we could have a column factory in UK, and we can have some other stuff being produced other places, and then you could have assembly places at all places, so that you could have this kind of universal setup, so that you can always deliver locally. But I think that if you're going to make it relevant and legitimate, we think that you have to have some kind of thoughts on how are you going to do this locally. And of course, it's not easy, but I think you have to have that vision, but you also have to, when you do the projects, as I mentioned, I think we need to kind of build in this local thinking and start to do these kind of things at smaller scale and gradually develop it. Because if this is going to be relevant, it will need to be eventually local.
Great. Thank you.
Fantastic. Okay, we got a question in the back.
Yeah, thank you for your presentation. Mareike from Fraunhofer IWES. You mentioned for your design that you started with a 11 megawatt design with a wind turbine in the corner, but for the future you use the wind turbine being centered in the floater. Can you maybe briefly list the main reasons for this decision, why the wind turbine in the corner would not be a suitable floater design for scaling up?
Can you help a little bit, Jon? Now I need help from the technical friend.
Thanks. Yeah, I think there are several reasons for that. I think one is when you install and you want to install it floating, you want to have it as centered as possible in order to so that it sinks evenly down and doesn't tilt when you install it. But I think it's also when you go to bigger turbines, you find that if you have the tower in the corner, you find you need a lot of buoyancy. That is for nothing, because you need to have as much ballast in your the two other as your turbine weight. So you actually end up with having a lot of buoyance that is really unused in a way. I think that is the main reason. That's what we saw.
Fantastic. All right. Any more questions? Oh,
well, was good reasons, but there is another reason. In order to make it stiff, it was not possible. No matter how much steel you put into the tower, you couldn't make it stiff enough. That was one of the reasons. So you spend a lot of money to make it stiff when you move into bigger turbines.
Very good. Fascinating debate. I think let's have it over coffee.
Yeah. I'm not a structural engineer, but my understanding is that when you go, as was said here also earlier, that when you go to bigger turbines, sooner or later you need to make your tower stiff, and you cannot work with soft stiff anymore. But I'm sure there are many thoughts around that. So I'll leave it with that. Thanks.
Thank you. Thank you, Kenneth, again. Okay, so networking break now. When we come back at 11:40, that's 20 to 12, we're going to hear the concrete point of view, as it were. So if we can be back in here sharpish for 11:40, thank you very much.
I guess when I said sharp-ish, I should have left the ish off. But nonetheless, we're coming in dribs and drabs. So I think I'd like to introduce the next speaker. Manuel, my dear friend, is going to come and speak about the concrete options, the solid options for floating wind designs. And yeah, the stage is yours.
Thank you very much, Alex, for the introduction. Oh, thank you. I have some special supporters. I can see. Oh, Luis is missing. Where is Luis? Okay. My name is Emmanuel Capano, and I'm the Chief Commercial Officer for Saitec Offshore Technologies. I'm very glad to be here today with you guys. And I will start with a brief introduction of our company. Saitec is a Spanish company that was established more than 30 years ago in Spain, in Bilbao. And since then, we leverage our international presence and we work in different geographies from Middle East to Australia. As an engineering firm, we provide engineering services in different sectors, from transportation to energy. When it comes to energy, I'd like to stress that we work only in renewable energy. We started with onshore wind, and now we are working in offshore wind, and that's why I'm here today. When it comes to offshore wind, we wanted to introduce our technology that is an innovative technology. And when we start to work on this concept, we were thinking to use a different material, and we look at concrete in terms of CO2 emission and also in terms of cost. It's a cheaper material, but also if you look at the volatility of price of steel, you know, today we are planning project that maybe will be executed in 7-8 years' time. So crunching your numbers in order to understand what will be the price at that time of materials with such volatility, I think it's quite challenging. And I think it was important to expand the supply chain. So we have already still having another material like concrete could be beneficial. And at the beginning, our focus was mainly in Europe. And so we start to look also at the capacity of production that we have in Europe, the capacity of the supply chain. Yesterday, there was a presentation from ESB that was showing that in Ireland, perhaps the capacity in fabrication in steel is more limited. And on the other hand, they have the capacity to do this in concrete. And this applies for most of the markets that we've been studying. Our floater, well, it looks like a catamaran, basically. We have twin horizontal hulls made of reinforced concrete. They are connected between each other with concrete beams, and they're sitting on a heave plate, submerged heave plate, that is also made of reinforced concrete. On the top of the hulls, we have, the hulls, by the way, are shell structure. On the top of the hulls, we have a transition piece that is a key element for the integration of the tower on the floater. And everything you see under the transition piece, with the exception of the single point mooring, it's in our patent. It's quite strong concept, innovative concept, and we have an international patent for it. The single point mooring is outside of the patent because it's something that was used for many years in the offshore industry and allows basically our floater to weather vane. On the right side of this picture, you see the baby brother that is what we have now in the water operating in Spain. And you see the next generation with larger turbine, like 15 megawatt type of turbine. But to get to what we have right now in operation in a test center in Spain, I want to say that is a long journey with several challenges. And we started this journey more than 10 years ago. We got our patent in 2014, and then we did all the most important relevant tank testing in order to understand better our technology. And I have to say that this type of work is still continuing. Last summer, we did another tank testing in Madrid for a type of turbine of the size of 15 megawatt capacity with specific condition like typhoon condition. So we keep studying. This doesn't stop. And to reach to this point, I think I want to stress some elements that sometimes the focus is always on the technical side of the project, but I think it's very important to understand also the complexities of the procurement of this type of project, because when you have a one unit type of project, there are certain complexities in order to get the supply chain in place. And let me say that procuring a one unit turbine is very, very challenging. And another important factor is funding this type of project was briefly mentioned earlier. It's complicated. We see that, for example, in countries such as Norway, earlier was mentioned in the presentation of Phil, they got a grant for the new demonstration project that they will have in the water in Norway. And this is an excellent opportunity to see a demonstration project of a certain size with large turbine. But they had an important grant for the government. And I think last year there was, Windcatcher got another grant from Norway, I think about 100 million euro. So funding is complicated. We don't have deep pockets, I can guarantee. And in this project, we have two partners. One is RWE, a German utility company, and the other one is Kansai Electric Power. And it has been a fantastic journey with them. And I have to say that we had a very good collaboration with both companies, and they brought in also an important experience and expertise in terms of offshore wind assets that they have, and in terms of project execution, because these are quite a complicated projects to execute. And I want to say that as a company, Scitech, in this specific project, we ran the full EPCI by ourselves. That's why I gave you this brief introduction earlier on about our company, because we have this type of skills that allows us to do this type of work. And I think in the presentation that there was earlier, it was mentioned that for floating wind, I think the technology provider have to play an active role. I think it's very, very important. In this case, we ran the full EPCI ourselves. And to stress even more the complexity of this is, we start this project in 2020. We did the FID, and then the procurement was supposed to start March 2020. And everyone knows what happened. So this had an important impact on our project. Procurement strategy, goodbye. We have to redraft it completely. We were lucky because our solution is in concrete, and when it comes to the floater construction, we have very good network with the Spanish contractor, but they need to completely reorganize themselves to start the construction. So we start the procurement after summer, basically. And it was very complicated. And then we had the war in Ukraine. So doing this project, having these two type of events, nobody can think of those in 2019, I'm pretty sure, because the planning of the project started in 2018. So as you can see, there are a lot of factors that you need to put in. It's not a mathematical equation. So you need to have also different resources within your team capable to liaise and deal with this kind of things. When it comes now to the project, we installed the floater. It's a 2 megawatt wind turbine. We installed it in a test center, existing test center in North Spain. It's called the BMAP. In this test center, you have water depth ranging from 50 meter to 90 meter, and we are at 85 meter with our floaters. So as you can see, it's very close to the coastline, about 2 nautical miles, but goes very deep already at that depth. And when it comes to the execution of the project, I also want to highlight the fact that, for example, 75% of the budget was allocated to companies that were basically a 20-kilometer radius from the construction site. The construction site was in the port of Bilbao. I will show you in a bit. Concrete plant was 8 kilometers from the construction site. We are based 15 minutes away from the construction site. And I will show you now a video, because this is better than, I think, my words. And what you will see now is the port of Bilbao. And I wanted you that you keep an eye on this, because this is the space that we needed for one unit, 2 megawatt. So when we think of larger turbine, okay, just look at it. So in the port of Bilbao, we have an area in which we manufactured our hulls elements and the heave plate and the transition piece. We use for this work a Spanish contractor, Ferrovial. And now this is the video in which we are showing the prelay of the mooring lines. We use a Danish company, Maersk, for this job. And we did the onshore installation of tower and turbine. I think this was the first time that was done. And this is the float-off operation. We use a barge coming from Norway, BOA was the company. They did the float-off operation. And we completed the marine installation. And we use again a Norwegian company, Windstaller. They did excellent work. We were very pleased with them, and they completed the marine operation in August 2023. We then started the production of electricity to the grid in September of 2023. And this is also important to highlight that this is the first project that was connected to the national grid in Spain, because Spain doesn't have, let's say, an history in terms of bottom fix. So it's first floating wind asset. And for the characteristic of Spain, we will see only basically floating wind project. And now this is what we face in operation. So this was a video, I think, of the first winter, during the first winter. So Spain is not only Marbella, Malaga, okay. I live in Bilbao. It's not that different from here, just to keep in mind. Your retirement plan for Andalusia. And this was before last Christmas, in which we have the biggest wave, maximum wave height of 13 meter. And this came just before Christmas, our gift, let's say. And you can see from the camera on the hulls, the behavior also of the platform, very, very, very stable. And we plot some graph showing what has been the behavior in terms of acceleration in the nacelle. Longitudinal and transversal, as you can see, is around the 98th percentile is around 0.15, 0.16 G, so below the 0.3 G from the wind turbine manufacturer, and also rolls and pitch are well below the 10 degrees. We have having 98th percentile like less than 5 degrees. And this is, you get the stamp when you finish all this job. you get this certification that is very valuable. So this is a bit like the end of the journey that you started with your calculation, drawing board, numerical models, tank testing. And then you want to see this. Because yesterday we were talking of bankability, insurability of the technologies. If you want to the risk, you must get this one. So what you see in the video, just to let you know that we did a longer video, 40 minutes with the Discovery Channel. So if you scan it, you can watch it. And I think I want to spend a few words on what we are doing now, also in terms of environmental assessment of our floater in operation, because I think there is a pressing need in terms of understanding how these floating wind assets are, what is their impact on the ecosystem in which they are installed in and operating. I think this is very, very important because regardless the type of technology, you will need this type of information. You need to document your work when you will have the largest commercial wind farm. This is very useful in all your conversation with the other sea users and industries like fishing industry. So we have a DT-BIRD system in order to detect, let's say, monitoring the birds, tracking the birds, and also having a system that allows to minimize, let's say, the risk of collision of the birds. The same we are doing for the bats. We have both ROV equipment, so we can also do some monitoring for this. And I think it's very important what we are trying to do also in terms of biodiversity assessment, marine biodiversity assessment, because we started EDNA monitoring campaign. We see a lot of potential in this type of campaign. It's a cost-efficient, I would say, solution. And I think it's very important when you want to have a scientific discussion with your with the sea users, such as the fishing industry. And we will publish some results about the DT-BIRD and monitoring, I think, next month. It will take a bit more time for the EDNA results. I think this will happen after the summer of this year. And what I was saying earlier, the focus is on how to deliver this project. And I think this will tie well with the next slide, the next phases of this conference, is what we've been doing for delivering our floater. What is our strategy? We think when you have this type of size of project from 350 megawatt onwards, and you have this timeline for your construction, you must have some sort of construction hubs in which you want to have this floater to be constructed. And what we did in Spain, after a complete screening of the port infrastructure, we selected one port in A Coruña, northwest of Spain. And this port, I think, we got a concession for 25 years. This will be formalized at the end of the year. And we did the same application in another port in the Mediterranean. But still, we need to wait for the result of this concession application. I think it's quite important. We look at this, we select this place because it can serve, let's say, from Coruña, it can serve Portugal and north of Spain, but also the west coast of France, and going up to the Celtic Sea and Ireland. And maybe further, I don't know. It depends from the clients. But we've done an analysis, and we look at, we can serve important markets also with the hub in the Mediterranean, 10 days of towing distance. I know that time is running, so I want just to say that what you see over there, it's a picture, it's not a rendering. So it's an existing infrastructure, very well connected. There is a motorway, there is an ongoing railway new construction in which we are the project manager of this railway connection. So this is quite large area, very good draft, 15-meter draft, and very good navigation channel. And there is also potential for wet storage area. And this area is going to be used only for offshore wind. So we will have other companies that applied for different areas in this port. And well, this is what we are planning to do. We will have the precasting of our component, the assembling, and then the loadout, and also the storage, of course, of the turbine components. And with this, I have to finish because I want to finish on time.
Thank you very much, Emmanuel, for bringing us back on time. We do have time for one or two questions, if there's any. Marijke.
Yeah, thank you for your presentation, Marijke from Fraunhofer IWIS. You briefly mentioned the investigations for environmental impact. I know that there's close by to the demonstration an measurement buoy, which is fully equipped with measurement systems. But I don't know how long it was already installed before the demonstrator was placed there. So my main question is, do you use measurement systems directly on the floater for investigating the environmental impact, or do you use the data from the measurement buoy? And do you compare it with the data from the measurement buoy?
The measurement buoy, I don't want to be mistaken, but it was like 2016 or 2018 that was installed, so well before our floater. We are doing some comparative analysis, but we are carrying out also environmental monitoring in the close proximity of the floater. So we have also CCTV cameras and we are using the ROV to see if there are fouling colonies, let's say, in the close proximity of the floater.
Okay, thank you.
And the buoy was installed by BMAP, by the test center, the one in 2016, not by us. We installed another buoy also ourselves.
Well, first of all, thank you for mentioning a lot of environmental issues, so I feel less lonely today. No, the question is around the life cycle assessment,
Yes.
Because this is a discussion we had for quite some time in Italy about the full comparison in terms
Yes.
of CO2 and in general in terms of life cycle elements, and also recyclability or how can I say, solutions like rigs to reef, so leaving them like kind of sinking. How far have you gone into this sort of life cycle assessment considerations?
We are working closely also with other organizations, research center and university. And I think these 2 years of operation will be very important to understand, first of all, the impact of our floater on the marine environment and the ecosystem. And also when it comes to the analysis of the CO2 footprint that we have with our floater from the construction to the installation, we are working on this. And this year, for example, we completed the thesis with a student from university from Greece, Thessaloniki. And we are collaborating with university because this is a very ongoing exercise. And I think we want to also get the results from this eDNA assessment, that we will get this result after the summer. So I want to say that it is still an ongoing exercise. It's not completed yet, but we're working on it.
Fantastic. Well, thank you very much again. Thank you. Next up, Jilde Kimmel from EcoTLP is going to talk us through the only simple solution to deep water floating offshore wind technology.
Hello. Good afternoon, everybody. Well, thank you for having me. I would like to discuss a little bit about our technology, EcoTLP. In our view, the only simple solution. And I think not so much the only, but the simple aspect is one of our focus points. Basically, I want to go right to the start of what floating offshore wind is all about. And I think it's important to understand where the complexity lies and why do we see 40 different floater designs. Basically, all the floater and the mooring should do is provide a stable platform that is that allows the wind turbine to generate energy. So what does that mean? Basically, we have a very high static moment because of the wind thrust load. So a static moment should be counteracted. On the same time, you want a stable platform that minimizes motions in the nacelle due to all the fatigue issues and constant power production. So basically, these are quite contradicting requirements because the static vertical stability requires high stiffness, but minimized motions typically requires low stiffness because a high stiff system has higher vibrations. And I think this is the basic principle, the counteracting forces that are the challenge to be solved by floating stability and floating offshore wind farms. And looking back at the history, I think we see basically three types of floaters. Obviously, there's the semi-subs, which is stability from the water plane. There's the TLP, which has stability from the mooring system. And there's the spar, which has stability from gravity or metacentric height. And these are historical designs that we had from oil and gas. And oil and gas is not floating offshore wind. Standardization was not really an issue there because most of those units were single build units. Also, they were not cost critical. In oil and gas, cost is less of an issue as it is for offshore wind. I don't need to tell you that. And basically, it's good to learn from history, but not automatically copy it, because these floaters don't really have a good answer to these contradicting requirements. So, new requirements demand new solutions. Well, the actual considerations that we have to take into account, I will call them considerations, you can call them requirements, but I want to separate between the key requirements and these considerations. Obviously, floating wind, we have to look at cost, so CAPEX and OPEX. CAPEX for the floater and the mooring is approximately 30% of the LCOE, and OPEX of the whole system, including the nacelle, is approximately 26% of LCOE. But looking at these, for the CAPEX, obviously we want to comply with some things. We have a basic design idea before we came to our solution, because just copying something from the past, I don't think work for floating offshore wind. To name some of the most critical ones, obviously to minimize CAPEX, you want to minimize the amount of mooring material. So that puts some considerations on vertical or catenary anchor lag moorings. In order to minimize CAPEX, we don't want to have big, large crane vessels that operate, that install offshore. So we want free floating stability without use of anything else. We want to be able to do localized fabrication regardless of the site, whether there is a steel shipyard in the area or not. And localized fabrication also means local workforce. I think, and that's where simple comes in, you want to be relying on known technology. People are going to invest billions of euros in these projects. It's very nice that there's a lot of innovation going on, but combining innovation is also combining risk. And in the end, a simple solution would always be a preferred solution, we think. We want to be able to do import wind turbine assembly. Well, that aligns with the free floating stability. And in order to make offshore wind, floating offshore wind work, series production is essential. Scalability is essential. So this is where we see that simple shapes that can be built in a high-speed process, or relatively high-speed process, is always preferred over production processes that have a lot of intricate details. Obviously, use of materials requires supply chain, and use of innovative, excessive, or very new materials will always put you in trouble. So we want to basically use conventional technologies with materials and for instance, for mooring lines. Material prices and price volatility is also something. If you make a financial model and you look out for the next 5 or 10 years, which would cover a production sort of outlook at this stage, so production of the floaters. The impact of a high volatility price such as steel compared to a low volatility price such as concrete has massive impact on the financial models. And that at some stage will drive decision making at developers. So that is something to consider. And also we think that if you can save on very high, on mooring materials by allowing a soft mooring situation, so relatively soft motion, will also impact on OPEX, and it saves you on mooring prices. So on the OPEX side, we see similar type of considerations. So we want accessibility to be easy. We want low fatigue, so low motions again. We want inert materials near the water surface. Obviously, corrosion requires OPEX cost in the future. It requires inspection, maintenance, etc. So again, you can sort of sense what sort of main material we're going to use. There's a benefit of having inert materials such as concrete. Free floating stability allows for a major component exchange in port. Major component exchange is one of the tricky bits in floating offshore wind. Obviously, jackups cannot use their legs to reach the seabed. There's not a lot of vessels available that can do major component exchanges such as gearboxes or entire blades. Small mooring footprint enables you to optimize your plot size. We'll come back to that later. Upright stability obviously needs to maximize production. And that also ties into one of the discussions we had earlier, control of the nacelle and motions of the floater. They act together much more than in floating wind. And this is something that deserves a lot more attention, something I want to discuss with the wind turbine suppliers. So please come to me if you have ideas on that. And passive operation. We don't want active ballasting systems and such. Well, this is quite a lot of requirements. I don't know if you've done design exercises, but putting this together in a single design is quite a challenge. But obviously, we like a good challenge. We're engineers. So we basically found an ideal situation by using a hybrid TLP spar, which is our EcoTLP here in one of our simulations. Essentially, it is just a very simple, big circular cylinder with for 15 megawatts, approximate 40-meter diameter. And instead of naming all the issues and diving into what should be done or what are the problems, I rather present you the solution to all this, which is a simple solution, because simple solution, as I said, preferred over complexity. So what do we have? We have a concrete floater with the local fabrication facilities readily available around the world. So no need for yards, steel yards and shipping. We have low price volatility and good availability. We have low fabrication risks because it's a slip-formed production, series slip-formed production. High mass, obviously concrete will be heavier than steel, which is good because we want slow motions. Then we have a submerged floater. Obviously, we don't want too much wave loads. That's why the main floater is submerged. We have the relatively small sized floaters, so 40 meters compared to the semi-subs or TLPs. If you look at the yard space you need, it's much more efficient. Obviously, concrete has also some downsides. I don't want to just present the positive ends. Its reusability is low. Drafts during fabrication is a bit higher than a semi-sub. And hydrodynamically, it's not optimized. But that's a strategic decision because we think that scalability in production speed and production cost will drive it. Submerging it a little bit further overcomes this problem. Then further, we have, it's a ballast with high density fixed ballast. This provides the floating stability. We have a relative soft mooring, and the soft mooring allows for wave frequencies to be higher than our response frequency, so we don't get wave resonance. And the mooring has a slightly off vertical orientation. This helps static stability. Combined with pretension and buoyancy, there's some smart ways to improve your verticality. And compared to, for instance, spar and semi-subs, where you have catenary anchor leg mooring, we may basically focus on the deeper waters, so say 200, 250 meter plus. And there you see that in the bottom right, the amount of units you can place with the moorings inside your plot area is significantly higher if you have vertical or near vertical mooring compared to calm mooring. Scalable solution. It's simple and it's scalable. I think those two are the most important requirements. We use a slip forming method in combination with companies who've done this many times before. Slip forming allows for fast production. With 2 series, with 2 lines of slip forming, we can build 50 units per year. So at 15 megawatts, that's about 750 megawatts on a yearly basis. Obviously, you can also do more. And if you look at labor intensity and local presence of knowledge, this has a lot of benefits. Then it's a practical solution from installation T&I point of view. Fabrication import, don't need to tell you about the benefits that has. Installation is simple. Tensioning of your mooring system, obviously, just by ballasting and deballasting. And this is, and it also allows for major component exchange import if you wish to do so. I think it's also a reliable solution. Looking at the materials we use, the softer mooring and especially the concrete hull require very little maintenance, and also load and stress concentrations are very equal compared to maybe structures where you have a lot of arms and legs that connect into each other. These will typically always over time give trouble. If people are spending billions of euros on a wind park, I think everybody would prefer something that we know well and is a reliable solution. Looking at the reliability of the nacelle, we've done detailed analysis that's shown on the right, where we have accelerations and load cycles based on nacelle acceleration analysis. If that would govern fatigue in the nacelle, which it doesn't on all components, but on some, yes, we have a 10 times longer fatigue life than a typical TLP would have. So, an affordable solution. Why are we so affordable? I think we've been talking to various commercial project developers, and they were quite surprised by our relatively low price, mainly because it just makes more sense doing it this way. Obviously, we focus on the deeper water depth. So 50 to 150 meters, we might not be the ideal solution, but 200 and 250 meters and beyond, it's basically a very simple case. Why? For the deeper waters, most people consider the TLPs to be a good solution, or the spars, but obviously spars have installation depth requirements which are not always feasible. But if we follow this couple of graphs, with water depth, obviously we need longer lines. And our solution is relatively heavy, and as you can see, the inertia for a TLP is typically equal, independent of water depth. But we can play a little bit with the gravity-based stiffness versus the mooring-based stiffness, because mooring costs increase with water depth, while gravity costs increase with extra weight. Gravity stability increases if you add extra ballast or make your structure a little bit bigger. So over water depth, we shift a little bit between how much TLP and how much gravity-based stability we get. So that means that our floater stiffness increases with water depth, and where the floater stiffness for TLP is typically negative, so I just put it on 0 here. This means that the mooring stiffness that we require is essentially lower. At all times, up to 1,500 meter water depths, we do not see an MBL requirement or a minimum breaking load unity check much lower than 1. And obviously you want to get the unity check as close as 1 to possible, otherwise you're investing in mooring material that you're not going to use. With a TOP, for instance, you will see with increasing water depths that you see the mooring line is stiffness dominated and not strength dominated. In all, that results in the bottom graph, where you see a very strong dependence, almost quadratic dependence with cost for mooring materials for TOP compared to a very flat cost on the eco-TOP. And this includes the concrete and the steel of the floaters themselves. So this is basically a little bit the same explanation. Being below the wave frequencies doesn't generate a requirement to increase stiffness as you go into deeper water depths. Being above the wave frequencies requires you to make extra investments to maintain stiffness and avoid resonance. Just a little bit from our engineering approach. Obviously, we have all these models, all these dynamic models, but we also have more parametric models that allow us to simplify the dynamics and make a parametric model where we can choose between width, length, height, etc., depending on your site, and make a cost opinion on all these variables. So we have 600,000 combinations of, say, 40 variables related to wind turbine capacity or diameters, etc. And that allows for a very good cost optimization. So what do we see on cost? Up for 250 meter plus sites, we see that we are significantly 20, 30, sometimes 40%, and in deeper waters even more, cheaper than the other options we've seen. These have been flagged as concerns from the developers we're talking with about commercial projects, but as they're digging deeper into our cost models, these concerns are slowly dissolved. Means about below 2 million per megawatt on mooring, concrete, ballast, fabrication and installation, obviously not including the wind turbine or the tower or the power cable. We see relative low OPEX, and OPEX costs are not well addressed, I think, in the current phase. 25–30% of the LCOE will be OPEX generated. More interaction should be generated, should be established between the suppliers and the foundations, the wind turbine suppliers and the foundation suppliers. We don't have accurate models that can predict OPEX very well. I think it's not realistic, but we see low frequent motions in general, allowing for a more constant torque load. You can better control with active blade pitch control your motion variations. We see lower floater maintenance because of concrete, higher accessibility because of low frequent motions, and higher installed capacity. So per plot, you can put in more units, and that will generate more power. So it will also cost more units, but your plot area is used more efficiently. So about the project, I think I showed you about the cost model, and we can very accurately define cost, but historically we've seen that costs are always projected, and this is historical cost. The spread, this is fixed bottom wind, the spread is enormous. So I think a lot of the cost arise from unforeseen events. So making a simple design that has proven technology, acknowledging all stakeholders in advance, allowing for instance, local production, which enables more political support, makes it a lot easier to prevent these unforeseen events. You want raw materials at your site and control the batch processing yourself instead of being dependent on transport and fabrication yards for sub-assemblies, etc. So that reduces your supply chain risk, also your price volatility risk, which is often overlooked at this stage. And over time, structural damage risk is much smaller if you have big thick-walled concrete structures. I don't think I have time to go through this, but I think you can see the gist of it. Obviously, in the Netherlands we would say, wij van WC Eend, but it doesn't translate very well. We prefer our solution. So where are we? We are patented. We have done 2 series of model testing. We have ABS feed approval for non-site specific units in 250 to 1500 meter water depths. And we're ready for commercial projects. Thank you.
I think we can have one question. Is there a question from the audience? Don't let me ask a question. I have very strong opinions on TLPs.
Yeah, thanks for the presentation, Dennis Mata from Ramböll. So we have also some experience in more traditional, I guess, TLP design, and just wondering if you can comment a bit more on how you deal with the slack line topic. So we see that's often driving, and then of course one way is to move basically your legs further outward, but you have a very narrow footprint in that sense of your tendon system. So just interested in how you get this to work.
Well, we are specifically different from a conventional TLP in that our overall response is natural periods around 25 seconds for heave, 35 seconds for roll pitch. So that means that we're a relatively soft system. So we do slack prevention, so we do design on a 10% pre-tension, minimum remaining minimum tension, but we've done tests and also analysis. If we have a slack line, apart from it, maybe, but the retensioning effect, so the snatch load, there's no load peak on top of what you would normally see. It's not like a stiff line. We're 250 meters deep with soft mooring, so it's not a problem. Still, you want to prevent it, but slack lines is not really considered an issue. Obviously, if you go in very harsh environments, it would generate a lot of benefit to start to allow for it in very extreme events, because it would reduce the pretension, and with the pretension reduction, also your stiffness requirements reduce, and then your dynamic loads reduce. So there's a knock-on effect. The lower you allow your minimum tension to be, the more efficient cost-wise your mooring system will be. But from rules perspective, it's not desirable. Okay.
Excellent. Thank you very much. Thank you, Jelte. So taking us into lunch, we're going to move across to ports. And we have James Lawson Hall, offshore wind port policy lead at the Department of, I forget what the rest of that is, Net Zero is the end bit, DESNZ. And over to you.
Thank you. The very catchy and easy to pronounce title of my department. For those of you who were in Berlin last year, you may remember I gave a similar presentation to this, but I think one of the positives in the UK over the last year is that we've seen quite a positive development in the renewable space, particularly in the port area, in that we have a government who are very interested in the port space and drawing investment into that area. Just a very quick recap of some of the high-level points about floating offshore wind in the UK. Other people have presented this much nicer than I have over the last few years with some nice maps. But in terms of confirmed seabed exclusivity, the UK has one of the largest pipelines in the world. We have 80 megawatts of total installed capacity already. We have a commitment as well in the Clean Power Action Plan to radically increase the level of both fixed and floating offshore wind deployed. And we, as of 2 weeks ago, have successfully deployed part of the Floating Offshore Wind Manufacturing Investment Scheme grant. For those who aren't aware, that was up to 160 million that the previous government made available for port investment across the UK. We announced a 55 million investment into the port of Cromarty Firth up in Scotland, which is positive for bringing investment into the region. In terms of the wider floating offshore wind pipeline, as said, others have articulated this much better than I have. We have a pipeline of over 25 gigawatts of floating offshore wind. The majority of that is in Scotland as a result of the ScotWind and the innovation and targeted oil and gas leasing rounds, but we also have the 4.5 gigawatt leasing round 5 running in the Celtic Sea. And moving beyond this, there is potential within the northeast of England, and the government and the Crown Estate are working together to identify an additional 12 gigawatts in the Celtic Sea, and then looking beyond that, additional capacity across the UK for both fixed and floating through the 2030s. In terms of how that translates into port investment requirements, so as you can see, there's some outputs from the floating offshore wind Task Force Industry Roadmap report from a couple of years ago. These graphs are probably slightly out of date now, particularly in the Celtic Sea where things have moved slightly to the right. But that just highlights the level of port capacity that we need in the UK. That report estimated that we need up to 4 billion of investment by 2040 to support the rollout of floating offshore wind. That's split largely between Scotland and the Celtic Sea, but also I said if they're for the potential in the northeast of England, there is also capacity around there. And looking at FlowMIS in particular, we have one port that was taken forward in Inverness, so that was Cromarty Firth, and then we have another port at Port Talbot that we're working towards securing investment into that. As others have said as well, floating offshore wind places quite a unique set of requirements on ports. Namely, you need a much longer quay, you also need a much higher weight-bearing capacity to lift the components, you need deeper water depths, and you also have the relatively unique requirement that the ports need to be in relatively close proximity to the site of deployment due to the need to tow out, and the debate yesterday around whether you do in situ or tow back to port, operation and maintenance, but should you return to port, need to roughly be within a 3-day weather window, although I appreciate that is subject to debate. In terms of understanding the barriers to investment, we've done a lot of work with industry and across government over the last few years to understand what those barriers are. We as in DESNZ, co-chaired a task and finish group with Renewable UK that brought together public and private sector representatives to work through the complexities around the port investment, understand what those barriers are. The Offshore Renewable Energy Catapult also published last year their Port and Investment Manufacturing Models report, which identified the barriers to investment as well as looking at different ways that they could be overcome. But to summarize very quickly under 2 headings, broadly speaking, the 2 barriers that we're contending with are investment revenue certainty, whereby the CFD, which is the primary subsidy method in the UK, as everyone's probably well aware, has been very effective in driving down the cost of offshore wind, but that has largely been done at the expense of reducing costs within the supply chain, and that has therefore presented us with the problem that we now have a large-scale capital investment requirement for ports, and there is a need to overcome that. One of the main complexities is that CFDs are generally agreed 2 to 3 years before offshore wind is deployed. Anyone who works in the port space knows that port development isn't a short process. It can take anywhere up to or beyond 5 years. You're talking large-scale amounts of investment of up to or above £500 million. So in terms of securing that revenue, without having a CFD in place, developers are generally unwilling to commit to a port, which then means that in terms of bringing together the funding stacks needed to invest in that port, without the revenue certainty, it's difficult to secure that private sector investment. And compounding that, because you are talking these large-scale investment sums, it's not necessarily a case of a government grant will get you over the line. So using the FlowMIS example, the 55 million into Cromarty, Port Cromarty Firth is one part of the equation. Other private finances or public finances are needed to close that funding gap and actually build out that port in its entirety. And a third barrier, although less than, I guess, in terms of urgency in those 2, is the pipeline visibility and certainty. So as I said, we've got a very clear pipeline out to about 2032 in terms of projects, but there is a need for ports, if you're talking about repaying that level of capital, to have something on the books or have sight of a pipeline beyond 2032, covering the lifetime of any loans. So skip past that one because I've just covered that. So in terms of how we have been addressing that in the UK, so DESNZ is just one department that has an interest in ports. And ours comes purely from the offshore wind perspective, ensuring that we have the port capacity there to deploy offshore wind to meet our ambitions. There are interest in the Ministry of Housing, Community and Local Government, which is always really hard to say because it changes its name every few years. But they have an interest in the Free Ports programme. And for those who don't know, a very quick summary of Free Ports is they basically have tax and customs benefits within certain areas, and they also have seed capital available for investment into the port infrastructure, although that's relatively small in terms of the value of that. There are a number of free ports designated across England, Scotland and Wales. Within Scotland, they all have a green energy focus. Within England, there are 3, I think it is in total, that have a primary focus on offshore wind. In its previous guise, and I'll come back to this in a minute, the UK Infrastructure Bank and the Scottish National Investment Bank have also had a vested interest in ports, having invested into the ports of Ardersier, Tyne and Teesside, and there is also deals being explored elsewhere. The strategic investment model in Scotland has also looked at ways of bringing together developers and other partners around coalescing around individual port investments, and the Crown Estate and the Crown Estate Scotland both have an interest as well in terms of bringing investment into ports, with the Crown Estate in particular looking at how the supply chain accelerator can be widened to cover port investment. So, and then back to the National Wealth Fund. One of the key changes that this government brought in, as in the Labour government when they came in July, was the introduction of the National Wealth Fund. This basically transforms the UK Infrastructure Bank and brings in the British Business Bank in the first instance into a National Wealth Fund. And the idea behind this is it will catalyse investment into clean energy industries, support the delivery of the industrial strategy, which will be delivered later this year. In doing that, the government committed an extra 5.8 billion of capital on top of the the National Wealth Fund's initial capitalisation, and this is focused on into 5 sectors, which were announced in the manifesto, of which ports is one of them. The manifesto did initially have a 1.8 billion in there, and we're working towards how we can actually deploy capital across government. And to support this, the Treasury have published the Financial Transaction Control Framework, which is basically a document that sets out how government and the National Wealth Fund will work together. The idea is that the National Wealth Fund will become the primary vehicle for delivering financial transactions in this space, and departments will play into that. Although I am not an accountant, and the details of that are still being worked through at the moment for how that will be deployed. I am way ahead of time here and heading towards the last slide, but one of the other areas that we're exploring is utilisation-linked finance. So I'm going to caveat this with it is not a confirmed policy. We're exploring with the DESNZ blended finance team and industry and how this may work, working with a subset of ports to look at a real-world example of how this may be deployed. But the aim of ULF is to de-risk investment in infrastructure where it needs to be built ahead of demand. So that's looking at how we can link that to the revenue and investment certainty barriers. And it effectively works, like for those familiar with the UK student loan scheme, it's similar to that in that a public finance institute who we are working towards that potentially being the National Wealth Fund would deploy capital into a project expected to be a loan, and then that would then be repaid once a port hits a certain revenue threshold. But yeah, as I said, that is still very much in development. Would also be remiss as well to mention some of the other areas that government are deploying capital. The one that probably most people are familiar with will be the Clean Industry Bonus, which is effectively, it works in conjunction with the CFD, and it is basically a program where developers can bid for financial support to drive investment into deprived areas, focusing on net zero industries, and that does include ports as well. The first round of which is currently open until mid-April. As well as the National Wealth Fund, the government also announced Great British Energy last year. We're working very closely with them to understand what their priorities are. They obviously have a limited amount of capital that they have access to and need to prioritise. They have a really broad remit of delivering across the energy space. And also the government published the Clean Power Action Plan in December, which sets out the foundation for building an energy system that can bring down government bills, and that is the key driver of this government, is working towards the Clean Power 2030 mission, looking at how we can achieve energy security as well as driving consumer bills. And I am 8 minutes ahead of time, but that is the last slide.
You can definitely come again. Right. So, yeah, there'll be a couple of questions, but I'm going to take Chairman's prerogative here and ask a question or two. One of the things is about the deployment timelines for port upgrades. You mentioned correctly earlier that sometimes these can be bigger, longer, more complex than the actual offshore wind farms. But we've also a bit of a history
as sort of a change of tone and does it?
Fits in flow. So I'm talking about international port cooperation.
Yeah. Okay. Okay.
So it kind of fits in flow.
Yeah. Okay. Well, I'll put a link to the slides, but I'm just conscious, after some really. Sort of quite high level stuff, but it's quite granular from the ground up kind of approach. Is that questions? Well, I'll happily lean into that, but this is the boots on the ground. We expect what we do. I'll make that point.
Sounds good. Yeah, sounds perfect.
Not that you care, but I gather for events, but there's going to so you may not care.
Well,
I suspect you did. I had this feeling. Oh, really? Oh, it wasn't. Okay. Yeah, well,
it's only so far.
Wow. Okay. Yeah. Okay. Really.
Yeah, what he's working with. Jesus, to charge you, Chris.
All right. Okay. Right.
Yeah.
Yeah. Do you know with the we're fine. Actually, you know what? I really value.
Now you can have.
Well, no, they can talk freely. I think it's we still find that balance between times it's based finding a line that we are really supportive of them. However, step own concept through the light. That's what we've been trying to progress that. But you'll know some developers might push that back quite a lot, and others are get it.
Probably worth to put the
Do you know what? I don't know Emmanuel, and I would say hello, and that would be great.
Set up a call with him.
Cool.
Have a chat.
Yeah, and we.
The whole shooting bang.
I know he's also connected to Lucas Speaks. Because Lucas from Tugboat speaks really highly of you both, actually. I think that's where I know his name from.
He better fucking speak out.
Yeah.
They wouldn't have a fucking product if it wasn't.
Yeah.
I sat him down and basically say, right, this. Please stop trying to charge that.
Really?
Yeah.
It's because his model's quick. Oh, yeah, old school. Yeah, well, I mean, yeah, but I think that's my basis. Feels. We're doing our so it's like fuel. Well, yeah, yes, yeah. For your view, if you're at the talk about investment readiness about the goal.
Yeah, happy to. Right. Well, let me write it down.
Yeah.
3:30. Good afternoon. My task for the next 20 minutes is to make sure you don't fall asleep. That is the post-lunch slot. But I have great news for you. I have a relatively dynamic presentation. I might do some song and dance, we'll see. And then, no promises. And then we have a couple of presentations and panels to take us through to the end. We will have another break at 3:30, 3:35, but thank you very much for those of you who made it back. Anybody who's sleeping in the lobby, just leave them. So, my name's Alex Gaunt. I am the head of offshore wind for Fjordbase, and this is the first time I'm representing Fjordbase at this event, and I'm very honored to have been invited to speak and also to co-chair with my able colleague Ricardo the 2 days for you. And hopefully it's been enjoyable, informative, and useful so far. To continue that trend, I'd like to talk to you a little bit about the potential and the need for international port cooperation. Just for those of you who don't know, my last 3 years I was the supply chain director for a floating wind developer called Flaventis, specifically for the Sierco joint venture partner. And I left that company in December to join Fjordbase because one of the pieces of work that we did was around identifying the supply chain limitations that were out there. And I realized that the pace of port development was being outstripped by the pace of offshore wind development. And so I was very excited to find the opportunity of working with a port that I'd never heard of, but as it turns out, there's plenty of people in the room who have heard of it, that is capable to support offshore wind right now. And there's more of these in Norway, I stress. But Fjordbase is in beautiful Florø, 1.5 million square meters of prime real estate, as you would call it, an active base supporting Equinor's oil and gas activities, primary activities around OCTGs, concrete-coated pipelines, and 10 tons to 45 tons to infinite tons per square meter hard standing capacity on the basis of what granite can take, because it's in the side of a mountain. As you can see here, it's a significant stretch of land, 4 kilometers long, and it was bought by a UK infrastructure investor called Ancala a few years ago. They're a £4.1 billion cap infrastructure company. And is partially owned by SEMI AS. The strategic business fields, as I mentioned, oil and gas is the primary focus at the moment, but we have a huge aspiration to get into the offshore wind environment. And we spent a lot of time preparing ourselves to be ready for the Norwegian floating offshore wind rounds, which keep moving. And thus they brought me in to try and find some short-term offshore wind opportunities for this amazing port. It's amazing what the Norwegian mentality is in terms of moving towards net zero as well. So Fjordbase is targeting zero emission supply chain relatively quickly here and making immense strides already as we speak in terms of the decarbonization, going to electrified crane capability, and then moving over the next year or so into all electric vehicles on site, and so on and so forth. And there's some exciting stuff around ammonia bunkering and green hydrogen production as well, but we can talk about that another time. So, talking about international port collaboration. As I mentioned, my background, looking at ports, looking at the availability of ports to build my relatively few number of structures that I needed to build before 2030, 14 of them. It turns out that there is a lot of expectation in what we can do, but in the reality, not a lot that we can do all in one place. You'll have heard a lot of my comments earlier and some of the discussions on the floor around multi-port strategies and the importance of working together collaboratively across borders, but also locally, and trying to figure out what it is that's best that can be done in each location, whether it's individual components, mooring lines, anchors, or whatever that has a specialism area that can be brought together for the fantastic offshore wind, floating wind opportunity. So this is a chart I put together about 2 years ago, trying to estimate what kind of port facility I need for building my floating wind farm. And there's significant variances depending on the technology selection. Of course, spar buoys are not considered in this particular table, I should put as a caveat. But irrespective of whether you're building 4, 7, or 14, it's a significant challenge. It's a significant ask. And trying to find places that have this kind of quayside length, that kind of bearing capacity, local cranes with that kind of reach, lifting capacity, the draft coming up to it, particularly in places like the UK, which traditionally was around relatively shallow draft vessels and now need to look at expanding those. That is something that keeps me up at night. So why port international port collaboration? Well, as we're all here today, and we've heard time and time again today and yesterday, there is a significant offshore wind deployment portfolio and timeline, and there's a lot of floating offshore wind that's expected to be deployed in a relatively short time frame. And considering the amount of port facility required and the challenge for each and every one of these floaters that we're putting out there, we can't really afford to wait around until all the ports that are being enabled right now are ready. Plus, the UK and some other markets have a little bit of a history of not deploying in the timelines that they said they would before. And so we need to find ways to work around and work with these solutions. Now, I would stress that although port infrastructure delays threaten the UK's transition to net zero, it's not all doom and gloom. There is a lot going on, and there's a lot of good stuff happening. It's just a question of the timeline. And I think the thing about Norwegian ports is they're not here in Europe, in the UK, to take work away. It's about enabling. It's about working together in partnership with local port facilities to act as maybe a marshalling yard or a logistics yard, or focusing, as I said, on the mooring lines, the anchors, the chains, and tubulars or whatever, but trying to figure out how we can work together to together enable the offshore wind deployment rates that are necessary to achieve the net zero targets. Norway, as I said, is emerging as a future port hub for European offshore wind. The NNG project, help me out here, Stephen Nernergoff. Close, that'll do. Was quite famously in Norwegian circles, had a significant amount of Norwegian port involvement in its construction. That's not something that we publicized in the UK, but as we started doing our research, we realized that there's a lot of people out there who have an appetite to work with port facilities that exist now and have the capacity to support now. And this is one of those facilities. So the fjord-based facility, as it stands, is significant. It has the potential to support all avenues of floating offshore wind construction and assembly, but also wet storage and tow out and looking after it. So you can see here, the good people at Fjordbase and the Florø area have actually applied for wet storage licenses already, and you can see that on these animations. We're currently building a facility that will enable large structure integration, turbine integration, and we're looking as well at further expansion of the port facility to the south in the future. But we need to address the elephant in the room. It's a long damn way away, right? And I think with the colleagues from the insurance brokerage market, there's a conversation that needs to be had early on about what happens to towing these structures if they're fully assembled these incredible distances. Traditionally, with every floating offshore wind deployment scenario that came across my desk in the last 3 years, one of my first questions was, how far do I have to tow these things? Where do I get the anchor handlers? Where do I get the multicats is another question. Yeah, how do I have to tow these things? Because every time I tow it, I increase the insurance risk, I increase the risk of something going wrong, and the complexity of the handling and the deployment. And of course, that's just for the construction phase and the final deployment phase. What happens with O&M? I spent a lot of my career trying to put heavy lift vessels out of business. I also spent a lot of my career regretting heavy lift vessels being the most expensive, bar none, stakeholder in the offshore wind environment and causing significant issues. So how do we do major component exchange if we're miles and miles away from our home port? Well, again, that's where the opportunity for collaboration and local collaboration in particular comes into play. Because for major component exchange in the UK, we don't necessarily need the same acreage as we would do for the final assembly, construction, and commissioning. So there's an opportunity here to work together internationally in a collaborative environment whereby the front end is being deployed via the UK. The UK has those contracts, commits to those contracts, has the lead on the contracts, but is able to use the acreage and the facilities that are available with international partners. So is a multi-port strategy for the win? Well, I'm very firmly on the yes side of this argument. I really believe that taking a multi-port strategy approach allows us to look at what's available to us right now, what can happen in 2 to 3 years, and what can happen in the future with an infinite amount of money and infinite amount of time. I used to say to my suppliers, stop telling me what you can do with $1 billion of my investment. Tell me what you can do now. Because anybody can come to me as a supply chain director of a floating wind developer, and they can say to me, if only you give me 15 years and €1 billion, I can make you the best port in the world. And you'd be probably not surprised by the amount of times I had to have that conversation with people. And I don't have time for this. And the risks associated with building out a port facility can sometimes be even bigger than those building out a wind farm. Though I'd caveat to say that my wind farm doesn't exist yet. And that's basically it for me, hopefully giving us a bit of a run up to the day, but I'm happy to take questions at this stage. Thank you. Any questions from the floor? I can't ask myself questions.
Hi, Alex. Thank you for that. Daniel Sim from Aon again, one of the insurance brokers, as you know. Famously in the market, we've had a very large claim on a floating farm, which then had to recover most of the assets back to Norway to be repaired and then towed back. So that elephant in the room that you're talking about, that distance, you're quite right, and there's a lot of technical risk there that has to be mitigated. But as we have with renewables insurance, as opposed to upstream energy insurance, there's this time element to it. So that's another large exposure for insurers that they're looking to address, is if we're using Norwegian ports and there's a viable technical solution to mitigate that risk, there's still that distance, you can't shortcut the time to tow it back.
Yeah.
So are you getting buy-in in terms of that initial movement? Is it a fully constructed unit that's taking over? But how would you sort of propose to insurers that that exposure of time is being mitigated or worked around by using your base?
Yeah.
What's the offset to that risk?
Yeah, that is the elephant in the room, like we said. So I think what helps is to take a step back and look at the options available to us for major component exchange. Now, 99% of the O&M activities are done by an engineer with a bag of tools and maybe a box full of lube, right? So you have the crew transfer vessel options for the wind farms that are close enough to shore, and then CSOVs and SOVs when you start getting further from shore, and then maybe mothership CTV hybrid solutions for the vast majority of the interactions that happen. But if a blade bearing fails or a gearbox needs replacing or whatever, then we start getting into that realm of, right, what do we do? Time and again, I've been presented with, so nacelle deployed crane facilities, self-erecting craneage on the floaters, all kinds of very exciting and innovative opportunities. But time and again, I had to say to those fantastically brilliant people, unless your name is Vestas, Siemens Gamesa, or GE, I'm sorry, we can't do business, because I need that warranty coverage from the OEM who's providing me the turbine. Out of warranty, different story, but we're not there yet with floating wind. So then that leaves us with tow to port, right? Or heavy lift vessels, whom, I'm not super keen to work with. or wasn't. I should say now that I'm happy to work with heavy lift vessels as fjord-based. Yeah, so we end up in this scenario where we don't have a lot of choices, but we need to maybe think about it holistically again about that multi-port strategy approach. Where is the closest facility? If we're talking about, what is the cutoff point? Is it 7 units? Is it Scitech's 2 megawatt demonstrator? When do we get to the point that we need to deploy an O&M facility close to that wind farm and focus on the MCA, the Major Component Exchange, from a toe-to-port solution? And when is it make more sense to pay whatever Harima or whoever else decides that they want to charge us? And unfortunately, there isn't a golden rule on that. So what I would say is, looking at it from the Norwegian port opportunity, the opportunity to use that facility that exists to help with the construction and the deployment, I think is clear. That's low-hanging fruit. There's an opportunity there also to accelerate the UK offshore wind deployment rates, but then for the O&M, I don't see that being the most feasible solution for coming back the 600 kilometers.
But you're still reliant on the UK ports catching up to offer that O&M connection to your solution, right?
It's true. However, acreage takes a lot longer to put in place than heavy lift shore-based components. So if I can pile a piece of infrastructure to put a new Mammoth crane, or there's some fantastic UK startups, HLP, heavy lift projects in Edinburgh, for example, they may be able to put a crane on a facility that has deep water access key, but wouldn't be used for oil and gas decommissioning or the final assembly and construction of a floating wind farm. But they have that potential that you have a float up and use solution ready to go, but people aren't looking at it holistically. It seems to be, with port strategy, it seems to be all or nothing, and it drives me insane. So I don't want to do everything in one location, because if that one location screws up, that's my entire project program gone, blown out the window. But if I can do bits and de-risk it, a lot happier with that. But then taking into the risks around long tow and what have you. Thank you. Any other questions?
Hi, Alex. Johnny from OWC. You kind of covered actually a lot of what I was going to ask, given that my area of interest is O&M, and I would probably want you to keep some of your powder dry for our session later on.
Oh, I like repeating myself. It's fine.
But if you would indulge a little more on kind of what your vision for O&M could be with this multi-port strategy, that'd be appreciated.
Yeah. So I firmly believe that there's an opportunity to build a heavy lift port facility that is just that. It's a float up and use facility. I think it's overlooked as an opportunity for the ports, both in the UK, but when I'm thinking about the Norwegian future as well, and I think about the offshore wind deployments in Norway, there's also an opportunity to do both, right? That the O&M for the UK projects that are happening now in the shorter term, we focus on a UK-based solution, but then some of the heavy lift and assembly happens in Norway. But then on the timeline that the Norwegian offshore wind works, unless it accelerates, then maybe we're looking at heavy lift assembly and stuff in the UK, and then doing the O&M as close to those facilities as we can there. These cranes aren't fantastically expensive. Now, one of the big challenges I've got is that the cranes end up being rental-based long-term orders, and a lot of the crane operators don't want to sell me a crane. But that's just commercials. I'm sure we can find a way around that. But yeah, float up and use without needing massive acreages behind it with heavy lift, with extremely high hard standing capacity. I think that's a massive opportunity. Anything that's nacelle-based, anything that's climbing the tower, anything that's self-erecting on the floater, I love it, but it needs to have the right brand name on it for me to guarantee that the warranty is going to be honored.
Thank you.
Any more? Got one? Nope, we're actually out of time. Ha! I'm free. Thank you.
So after that excellent presentation, we're now moving on to the workforce. Phil Johnston is here from Celtic Sea Power to talk to us about building the floating wind workforce, meeting industry need, and embedding social value. Nice segue, I think.
Yeah,
I say it now. I say it now. I'm also conscious I've had too much caffeine and it's beginning to flag on the second day, and I've got way too many slides. So I shall do my best. And hopefully this is of interest, and hopefully also a fresher take as well. To explain a little bit about Celtic Sea Power, we were set up around about ahead of the development of the market, or at the same time as some of the vanguard developers. And we had a clear mission. We're owned by the council. Our mission is to ensure that development of floating offshore wind derives benefit, socioeconomic benefit to Cornwall and the wider region as well. But Cornwall is an area of England that's beautiful but impoverished. You know, we tend to get those who are familiar with going on holiday to the fancy parts. It's a very deeply poor place, and yet there's a huge heritage, marine heritage and mining heritage that can be pivoted into offshore winds. There's capability there too. So this is us. Basically, a team, we don't live and breathe flow, we do other things as well, but it's generally around the green energy transition. And we work across those themes of infrastructure, workforce, environment, and industry. Focusing today on workforce and a little bit industry as well, because they're interlinked. This is what we're about, so enhancing career prospects from a local. So this is where the beginning of the perspective change comes from. We'll tend to hear about what the industry needs, whereas actually we don't maybe hear as much about what the region wants and can deliver. And here we go about building a rooted industry. So it's supply chain development from one side, what the industry needs, but it's also, well, actually, these capabilities exist, how can they scale up? Which is my area. Just a quick nod to this project, Permagov, as well. We've got a lovely position. We're kind of we can operate as a vanguard, a facilitator, a de-risker, ahead of a lot of the activity in the industry, which means we can work across Europe, in this instance with Permagov, which is about marine governance across the way. So I'd give that a little nod and happily talk to other people, anyone that's interested afterwards. And here we go. I can't quite see my own slides. It's quite oh yeah, that's clever. And a timer as well, clicking away. Right, so Celtic Sea, for those less aware, is the other end of the UK from what Alex was talking about. Kind of largely between the typical Cornwall, tip of Wales, and out towards Ireland, and then increasingly as the Crown Estate set out to the south and west. So we've got a pipeline. There's always calls for it to go further and deeper and longer, but here we go. It's tests and demos coming through. It's a really, really key couple of months coming up. We're expecting some big news with the tests and demos. We're going to AR7. We have one that already has CFD, Hexagon. It's getting to finance, we hope. And also the Lyceum round winners. That'll be 3 winners of 3 times 1.5 gigawatts. So that's coming up soon. And also the intent for future rounds of 12 gigawatts plus has been more than mooted now. So it's there. The potential for wind is unquestioned. But what it is the Celtic Sea. It's pretty much a greenfield site. You know, there's not a great deal of infrastructure there. There is a bit, you know, Milford Haven, there is an important, you know, Welsh side will correct me on that. But for, you know, be corrected elsewhere in the rooms, it's a pretty virgin territory for heavy industrial deployment. We have to kind of see that as a positive and spin it. Now, just to nod to the industry thing, which happens to be my area, but it's linked to workforce, so hopefully it will come across fairly naturally, is about proactivity ahead of the market. One of the buzzwords we throw around is no regrets activity, because at the end of the day, offshore wind is a speculative market. You know, it's hard. I was talking to somebody earlier today. It makes great PowerPoint, but not a good spreadsheet, and it's certainly a long way from a signed PDF, right? So asking ports, asking colleges, asking businesses to invest on this market is too much, frankly, right now. So it's how do you kind of work in no regret activity? You know, it will work for offshore wind, but actually it could pivot to defence, or maybe the other way around, given the new state of the world that we're in. So that's a key element. We want a proactive supply chain. One of the early lessons, and it's no fault of the vanguard developers, I should say, but was we were kind of swamped. At one point we had 30 developer interest in the Celtic Sea. That's come down a bit since, as the risk kind of hit them. But it meant that it sort of spooked, it confused, the stakeholder fatigue setting quite early, and you've got a situation where you know, they kind of turned off this opportunity. They see the big numbers, but it doesn't mean much. Where are the contracts? Where are the contracts? Where are the contracts? So for a business trying to scale up, it's a lot of noise. So getting that proactivity and engagement was tough, because you've got a kind of a natural passivity, kind of impress me kind of approach from a lot of, you know,
And there's also, say, kind of some really solid, but pretty provincial engineering companies. And an industry that comes on pretty strong and has its wish list, but doesn't actually have a contract. There's also specificity there as well. They tend to sort of sign up to a supply chain portal and wait their turn. The better developers, the better supply chain companies are much more engaged, much proactive, really working to find those solutions, but also aware that this is a speculative market. So that's the premise that we come from. I'm highlighting that. So business-led collaboration was key. We set up this Piranha Hub, which is an online platform. Feel free to have a look at it and sign up. It's early days, but we'd appreciate feedback to try and enhance that productivity ahead of this flow market. That's de-risked against other markets too. And we also did something which we think is novel. Do correct me if others have done there. It's only a pilot, so you see the results in a minute. It's not groundbreaking, but it's significant enough in our part of the world, which is essentially to ask our UK private sector, how would you take on this challenge? We get lots of glossy reports, lots of saying what should be and how it should be done, but we're not really asking who is going to do it. Lots of whys and wherefores, but who will take this on? It will be the private sector. We want it to be UK private sector. We want it to be rooted in our region. So by asking companies to form consortia and spell out what essentially was for them an investment proposition, it's their report. It's, that will inform, that will hopefully raise their ambitions. It's run quite nicely because it ran ahead of the Crown Estate, ran an accelerator program, and 4 of the participant companies in this went on to win in that as well. So that sort of scale up, drumbeat of scale up is happening from the ground up, which we're quite proud of. And it's about supporting credible ambition. Is another one of the buzzwords we throw around. We can do. My background was conventional business support, but actually you've got to trust businesses to do what businesses want to do. Not all of them want to scale up. Many will want to go through grant innovation funding up the TRL level and down the TRL level when there's more grants. What we want here is capacity. We want to build that capacity. And the phrase was, and the outcomes here. You'll see a slight discrepancy because we've got a consortium formed off the back of it because I thought it was a good idea. But essentially, delivery plans, and that in itself highlighted where the private sector felt its capability lie locally, and then was anchors and moorings for Cornwall. Logistical services, which is a bit of a broad term, it can include things like draft reduction technologies, and operations and maintenance as well was a little bit of a catch-all, but you're capturing ideas there and also rooting it in the region. Crucially, the phrase locally led consortia of UK companies was important to us because it recognises that there are some smaller companies in our part of the world, but they've got ambition, but they understand they need to build in capacity from elsewhere, which obviously we're premising UK, but there's no reason that couldn't be Norway or Spain or wherever else it might be. That's fine. We lack balance sheet. That was a common refrain we got from our companies. They lack the financial credibility of the balance sheet to really go at scale and pace that's required of them. So they're always going to be stuck in that tier 4, tier 3 if we're not careful. The UK has a real gap there at the top of that hierarchy. So there we go. And the companies were really fond of it. I think the phrase that cut through for me was that it was pure business development support, which is actually quite rare in quite a crowded sort of support mechanism, support space in the UK. It's all about innovation, less about business development. So finally getting to the actual crux of the presentation. This was the social value piece that when the Crown Estate put out their ICT information memorandum to bidders into round 5. It was a pivot for Crown Estate. It was a slight turn of pace to really bed in social value. It was much anticipated, and I think it's fair to say a little bit disappointed by many disappointed several when it came through. Maybe it could have gone a bit further, but it's a clear sign of intent. That's the direction of travel. But what it came through was about workforce development, really kind of embedding social value into the region of the UK from these projects through essentially a metric of workforce, number of apprenticeships, and people who are NEET, not in education, employment or training, which has its many challenges, I should say. One of the interesting things, you see the percentages there, 10% NEET, 3.5% apprenticeships. It was interesting to see the split in the offshore wind industry, how they read that. Some of them read that as being just with, if we set up operations, that would be our percentage of apprenticeships of what, maybe a few dozen staff on the ground of their operation at most. Others read it as being of the supporting supply chain. So that was quite an indicative kind of that's a big difference. We obviously read it as the supporting supply chain, no question. So you got that open. Okay, well, this is the key point I want to make across the workforce is that when we get to what is a flow workforce, and you have to be careful how you say this with Jobs for Flow, is that we got a lot of headlines, There's lots of reports are saying, and they're very good, just not to do them down, they're very, very useful, but the word could was always doing a lot of heavy lifting. It could provide over 5,000 jobs in the region. And you, really? Is it? You've got 5,000 jobs to do. That doesn't mean I'm going to have 5,000 people with new jobs in Cornwall, for sure, or Southwest and Wales. So how do you actually turn that headline into something realistic? And obviously we work from the ground up, so working with the colleges, and it comes to the real granularity, which I'll scale with a couple of slides in a minute, of course, is the engagement, getting people who are neat to the courses, so transport, into housing is a colossal problem in our part of the world. So, they can't, all these 5,000 workers, there's an impression that they come to the region and they can't all live in the caravans. Actually, you've got people who are there, hopefully, getting better careers out of this, out of flow. So big questions really are the what, when's, where. What are the types of jobs? And that was, for the most part, it's mapping, modelling, and a lot of activity in the art consultants. There's a lot of stuff in this, all good stuff. But actually, these 5,000 jobs generally quickly get winnowed down from an industry perspective to being, we really need environmental consultants right now. We'll need turbine technicians later. Actually, most people who have a job in the region connected to flow, it will just be an engineering job for them, probably, in marketing, but it will just be a job for which the company has some market share of flow. So I think the industry there's a bit of double count, you've got to be careful of double counting with the industry there, and also the realities of how actually people enhance their career on the ground. And the when and the where, as has been a theme throughout this 2 days, a lot of question marks on that. We are at risk of having a surfeit of flow academies, around the world and in the UK. Shiny buildings, flow in the title. Where's the running cost to get the lecturers? Where's the engagement with the industry? Where are the people coming through? And especially if the timing is wrong. So it's better to be a bit more specialist, specialise in the areas of capability, anchors or what it might be. Building on those existing capabilities that are already there, scaling them up. If you talk to colleges, they're very clear what they want to do. They have their funding challenge in the UK. We're allowed to talk to national or international audience, so don't want to be too provincial. But essentially it's about scaling up that capacity and working with local skills providers to go along the lines they want to go already. Rather than reinventing the wheel and plonking lots of new professional qualifications around, which might act as a barrier. So it's about matching industry needs with regional wants. That's a key theme I want to get across. So when we first sat down, we came up with a slide now which is, I lovingly regret, but this was off the back of a lot of stakeholder engagement. We worked with developers from the early days and colleges and various skilled stakeholders. Essentially building up a picture of what needs to be done, borrowing some of the language from national initiatives and Department of Education, that kind of thing, LSIPs, local skills initiatives. Convene, curate, catalyse. This is what we had to do. Everyone agreed this is what you had to do. You had to understand the demand, and you had to link that to the supply, the left side and the right side there. And there's ways to do that. You've got, aggregated data, doing job foresighting, all sorts of really good stuff. But the problem was to link them together. It was reliant on actually someone how their career progresses, which I don't know about you guys, but for most people it's not linear. It is not, I want to be a wind turbine at the age of 7, and that's what I need to get there. You do this, you do that, you do a course, you meet someone, you do that. So understanding that is a career pathway. So how do you help someone in their career earlier on, or a teenager, or someone who's become economically inactive later in life, to kind of get back on the thread and really guide them towards offshore wind industry or green energy. It doesn't necessarily matter that much. You just want to guide them along, upskill them in a natural path. So that career pathway was the approach we really built on. And to make it stick, we made up the flow mark. And that is all it is. It's just a name, really, a buzzword. But the point, as you'll see in later slides, is it allows that linkage to happen. So it's short of an accreditation scheme. And there are other initiatives. Skills is fraught with initiativitis. There are a lot of initiatives. But I hope this will stick as a way of guiding people through an industry into from where they are now into a better career in green energy and ideally flow. So 5 minutes to go, and I'm hitting you with complicating slides. It's just to show the work went into it really about the granularity of characterising the provision that was already there in the training providers and in the locally, and matching them such as we understood them to be with jobs in the offshore wind industry, and crucially not maybe as the flow industry sees them, but in the sense of more capacity in local engineering or the supporting industries to offshore wind. So in broad terms, more ports people. There's going to, if ports pick up, they'll need more of that. So not necessarily that complicated, actually, but we need to go through that. Again, fairly familiar for people who work on skills analysis, crossover, let's go, that kind of thing. And then we set about the career pathway tools off the back of that. Again, not novel in itself, but the opportunity presented itself was that in our region, flow came on like a rocket. It was a great white hope. It remains so. So we're able to use that to convene stakeholders, convene colleges that all heard about it. Great, we're going to get 5,000 jobs, right? Actually, in practical terms, how about this X, Y, and Z? And then it started to go. And that ongoing engagement, my colleague talks about Team Biscuit's time with the colleges. You've got to go in. You've got to put the time in. We'll also stand up in due course when developers come. That engagement with the colleges will have been done. The college will know, pretty well. We've got most of them across the region now. So here we go, just a little, I think I'll end on this slide, but happy to take questions. Is that process of the FlowMark process, we call it, mapping skills supply to demand, matching the industry needs to the regional wants. So you've got a fairly familiar to many, defining industry requirements, working with the colleges I mentioned, and modelling the skills supply and demand. And in career guidance, we talk about guidance, progression, advancement. So really breaking it down and sort of, talking about teenagers who could go any which way in life, and maximising their credible local career paths. So it's a bit grand, but essentially you get out there and talking to careers advisors. The team have worked with Job Centre Plus all across Cornwall and extending that out to Wales and Devon as well. So that enables a multiplier effect. So we don't want to be another initiative that comes and goes. We want to embed this in the system. So that it's keeping it quite short as well. Just an awareness of offshore wind. Have you thought about this? But also engineering, turn them on. Trying to be reflexive and listening. Practical knowledge really came through as well. It's that understanding of what courses are available locally, which inform No2 Paths, which is an app which is about to launch. It's a funny one because we had funding to do something. We thought, that's a nice idea. So we'll see how it goes, but it's quite nice. It's basically a young person will pick up on it and go, this course is available locally. They can do that, and it progresses, that it tracks it. And then you can see that and hopefully usable data for the industry. But actually a lot of it was enhancing soft skills. So we talk a lot about working at sea, that Maritime Heritage talked about, I mentioned, was that there's a pretty hard, soft skills go, it's a pretty tough one. Can you drive a boat? Can you jump in the sea? And that's what that kind of thinking about that need for leadership, for teamwork, the ability to work at sea is a good example, was really important. And it's not necessarily caught by the system as it so is, especially as we lose our skills base. North Sea oil and gas is retiring and doesn't actually want to go back, nor does the younger generation. So that was a really key thing. So that came through, again, a lot of spade work and building into local training providers so they had the means to multiply it rather than it be here today, gone tomorrow. My favourite example of this is the career advancements, which by this point is kind of that letting go piece, right? You're starting to let them go. So we're lucky with the way our funding works. We had an underspend, I'll be frank, but it's one of the best things we've done, is we just paid people to go on courses. So STCW, so sort of a sea survival kind of course, and it was a nice way of just giving someone an instant certificate for if they wanted to progress a career offshore, so in offshore wind, or the cruise ships, or whatever it might be, or tourism, or working on a vessel. That's fine. Their careers have been advanced. Also, it was a way of finding out if it was for them. We've chosen courses, working our eyes is also on. They're practical, useful, but also if it's not for them, that's fine. They've learned something. There's a real uptake of people getting that first step. If it's paid for, and this is my sales pitch, I think the industry should do a lot more of this. Just pay people to do a course. Just do it. They don't have to be big courses, but it can just turn them onto something. They've got a step forward. Oh, that sets them off in a direction, offshore wind. So, but it'll say, again, I think it's a nice way that I see it of matching what's wanted regionally with what's needed by industry. I think I'll stop there. That's all right.
Thank you very much, Phil. We actually do have another 5 minutes for questions.
Wow. Okay, hit me.
Any questions from the floor? So I'll start off then. So one of the things that struck me there was this concern about the number of jobs created. and having spent a lot of my time over the last 3 years looking at grant applications, but also the way that certain governments measure the impact of investments, it all leads you to the conclusion that politically, the more jobs you can claim that you create, the more likely you are to be able to succeed in your grant application.
Yeah.
So how would you recommend balancing potentially politically motivated job creation statistic against the very valid point that you made earlier?
That's such a great question, Alex. Yes, to have a little whinge for a moment and then self-Lomark, is there's a gap there between the high-level understanding, jobs and GVA. What does GVA even mean? Someone here will know, I know. It's a very hard thing, but yes, that's the metric that's used for this type of conversation. On the ground, in reality, we're talking about pretty low aspirations where we live, frankly. So it can be really quite small. It can be, a few people went up on a work experience up a onshore turbine, liked it, and suddenly is interested in taking a sea survival course. It's that level of granularity. How do you capture that? We hope that Flowmark will provide some data analytics behind it to tracking. It's early days. It is what it is. It's one initiative of many, but it forms a mean, along with Skills Passport, which is a slightly different perspective of drawing in oil and gas into offshore wind, of you're building up data analytics of what people's actual career actually is, and their increase in salary, things like that. Can they afford, in our part of the world, can they afford to live in the big homes by the sea that otherwise are unaffordable right now? There are much more interesting ways of doing it than this exchange of press releases.
Thank you. Any questions from the floor? I could keep asking you questions until I go blue in the face. Mike's coming.
Thank you. In project in unrelated sectors, and in some countries there were requirements for local content, okay, that were attached to, for example, a round of public tenders. Is there anything like that is being discussed in the UK in general, and in your case?
I'd say it's not going to go away, for sure. And I think it's bubbling up a bit more, given we live in a new, the global supply chain has just been upended. I think with that conversation will keep coming. I heard someone very senior in the industry being very vocal about it, mandating it at quite an aggressive level. It has to stand up on its own terms. We talk about design to local interest in the concrete earlier, because we've got aggregates literally lying around on the ground in Cornwall. There's a great supply chain for concrete right there, and you've got Portland and Bristol ports that could take it somewhere. Really interesting. So it has to stand up. I think if you mandate it, you're never going to get above that mandate, right? To really entrench it in and really rethink where the UK value is in the supply chain, because it's said too little at offshore wind conferences. The UK is world leading at putting turbines in the sea, but not with the value behind it, except for insurance. I heard earlier today. It's good at that. But really building that supply chain, it can be prompted and cajoled, and I think it will be in the new world we live in. But it has to be on its own terms. It has to stand up commercially.
Thank you. One last one from me, unless there's any more on the floor. When we're looking at the training requirements, and you say pay to train maybe is a route forward, have you given much consideration to the international application of the certificates and the training process? Or
not yet. I think we're looking at a much more ground up, localized approach. It's worth. We're conscious to stop short of that accreditation. There are firms at GBO. There's systems for that, but we see that as much later in someone's career, where our focus is on drawing them through.
Because I could imagine a situation where you have 10,000 highly trained people, but no projects locally.
Well, exactly. That would be the word. If we've got 10,000 people through a GWO course, okay, great. But so what for Cornwall? If they've got 1,000 people who've got a sea survival course, and they can get jobs on ferries or in local cruise boats, where it might be, but also have a really good, a good course that's good, it's good base of soft skills. Fine, that's fine. There's no regret activity. That's what we go for.
Lovely. Okay. Well, thank you very much, Phil, for your time. Next, we're looking subsea at the cables. Øyvind Iversen from Nexans is here to talk about cable solutions for floating wind in a cost-focused time. and then we're back to ports.
Is there a pointer as well?
So if you point the pointer at the screen in front of you,
okay,
then you can see where the red dot goes. The pointer bit is the.
Oh, all right.
So you turn that around. There you go. But you can look at the screen in front of you and it appears.
Good. Okay. Third presentation after lunch. All awake. I'll try to avoid talking for 45 minutes because I'll probably be interrupted. I'm going to talk a little bit about history, at least from Nexans' point of view, for floating wind. Cables are costly, it's been said. Supply chain is stretched, we all know. Everybody has a long backlog, hence it's a bad situation for having a good deal, as is talked about these days. And talk a bit about the technology advancement and opportunities by looking at the design of the cable, survey, and some special design tweaks one could do. Especially then looking at the limiting bottlenecks and for the cost. Let's see. Go in front. This picture, in a way, sums up where we are. Let's see. Does it work? Okay, manage. This picture is roughly from 2018 in our production facility in Halden in Norway. We have one production tower. We have an old installation vessel from 1974. And basically at that time was two good installation vessels in the world for cables. Prysmian had one, also dead old, and we had one. And we had a couple of decent ones. Picture below is from when our newest vessel, Nexans Aurora. I think it was finished in 2021, and now we are building a second one. And so is everyone else. Prysmian, NKT, everyone is building vessels for the purpose. Picture in the middle is the same facility as to the left, but through the skies you can see another production tower being erected. Because we are like more than doubling the capacity, and so is everyone else. And it's still got a tremendous backlog. So the question is, are the skies dark or not? Picture to the right here is very interesting for current political situation and long-term situation for the industry, possibly, hopefully not. This is a plant that we have in US. It's in South Carolina, Charleston. It's the only high-voltage subsea manufacturing plant in the US. It's built mainly for US offshore wind, which is not huge for the time, for a period coming. And of course, it's also exporting to Europe, which is interesting. Bottom right, okay, it's a fiber optic and umbilical manufacturing plant. Bit on history. We delivered to Equinor's Hywind and Hywind Scotland. We didn't deliver to Tampen. We didn't have production capacity at the time being. This was repaired in 2024. I'll get back to a small detail on that afterwards. Because we've spoken about repairability. What do? Do you lose production if there's a need for a repair or service? And of course, this is not anything commercial at all. This pilot park, what you see down to the right here is part that normally consists of a dynamic cabling system. It's a bend stiffener, buoyancy elements, lots of work that needs to be handled offshore. It's anchoring system to hold the cable in configuration, something you definitely do not want for multi-cable systems. Again, for oil and gas, it doesn't really matter because it's lots of money in it and there's very few cables. Then it doesn't really matter. So what basically makes up a cable system? It's a bit more than this. Part of a structure of a floater or bottom fixed. If you start topside, termination. Again, for oil and gas and the early pilot projects, termination of the cables are by the manual work, having personnel offshore between 2 days or a couple of weeks per termination. And of course, that's not a viable solution going forward. You have to have something, a quicker termination. And also, we can see to the right here in this picture, it is daisy chained. So if something goes down, the whole string goes down. So hence, we did deliver for Equinor's repair for Hywind Scotland a method that would disconnect one of the turbines, joint to the next cable, and then lay down in the seabed. I'm not sure if that was used, but it was delivered as an opportunity. We are currently qualifying and doing type test for this type of termination for 145 kV. Other thing, as mentioned, bend stiffener, it is to prevent fatigue of the cable during the normal operation period and also extreme conditions. For the export cabling system, sure, it's fine to have, but for inter-array cables, if you end up having bend stiffeners due to the either lack of knowledge on how to design the floater or lack of knowledge how to analyze and design the cables, if you have 100 bend stiffeners, they are easily between 500,000 and 50 to 100,000 euro per bend stiffener, plus assembly, plus termination offshore. So bend stiffener you want to avoid, and they are also a thermal bottleneck. If possible, you also would like to remove the buoyancy elements. If you have 50 buoyancy elements, you have to assemble offshore. It's going to take a lot of time. And it's also awkward to install on some of the typical cable laying vessels. As mentioned, anchors definitely want to avoid. Forward. So I talked about the termination. In order to do the, get rid of quite a lot of these components, you have to have quite a lot of the material know-how, which I'll go back to on the coming slide. Materials. Most cables use copper or aluminum. Aluminum is of course cheaper, but its current carrying capacity is less. And also from a strength point of view, it's not that favorable. So aluminum alloy has definitely benefits, and also for inter-array, one needs to qualify inter-array cables with aluminum alloy for higher voltages. Again, to have cost down. It's not shown on this picture, but it's coming later. For another thermal bottleneck is when you approach the shore, because then you have either a trench or you have an HDD, and then it gets really, really warm. Hence, that is the bottleneck for most of the cabling system. That may make it difficult to actually get the power we want through. There's details coming on that later on. Survey is often overlooked. It's very important to do early on, because that limits the overall cost benefits you can achieve. Because often they give you can use this number for the thermal conductivity of the soil. So imagine installing cable in either a trench or you bury it along the route. If it's mud of some thermal conductivity or not, then it's more like a thermal flask around the cable. So if you use the wrong number, you end up having a lot bigger cable than you actually need. And it's going to be more expensive and difficult to install. So this is talk about reference projects. So we are currently delivering the world's first deep water 145 kV cabling system. This is for Chevron's Jansz project outside Australia. So it's roughly 140-ish kilometer from Barrow Island out to an unmanned oil and gas facility. Not oil, it is a gas facility. is a rather tiny cable compared to what we're looking at for export cables from offshore wind farms. It's only 400 square mil, and it's 145 kV of a dry design. But the technology is transferable to high voltages, and we have manufactured a cable of 245 kV and 1200 square mil, so it's substantially bigger. And for oil and gas facilities, also odd projects like the one to the bottom left of 4 times 1600 square mil copper conductors. Again, those have been in service for 20 years for dynamic behavior. So again, along the route, you will see you have either from OSS, dynamic cable. Along the route, you will probably have various cross-section areas of the cable, depending on the soil conditions and the water depth. Here it looks like a nice steep hill, but it's actually laying up a mountain, so it's almost like this. And towards shore, you will have the HDD, which is the thermal bottleneck. Next slide. So for dynamic cable, it's the same cable design as on the previous picture, by the way. In order to have something that's most cost efficient as possible, you need to have the material knowledge, like the material characteristics of all the individual components, from the copper to the steel, metal water barrier, friction between them. Also, when you do multi-project analysis, you can't use, say, 2 to 3 months on each analysis. That's far too long. So you have to develop methods to do that quicker. I spoke about thermal bottlenecks, and also the dynamic cable at the OSS is, for export cable, will normally be in a bend stiffener, and that's going to be very warm. So you have to do the correct type of analysis, and it's not straightforward, because otherwise you end up with a cable that apparently is too warm. So pointer again. And also, I spoke about, I mentioned the industry collaboration. One thing is that the hang-off position of the cable. For inter-array cables, it's relatively easy, but they can hang on the side. But for export cables, it's very favorable if you can have termination in the middle of the floater rather on one of the sides. So that's why in study work, we work with developers of floating systems. So as mentioned, the one you do not want is the bend stiffener for inter-array. Anchors, buoyancy, you want to avoid having a heavy cable, and you also want to avoid having a dry design, expect from the export cable. Basically all the things that are normally used in oil and gas, you want to get rid of. So when you design a cable, it's often easy to, okay, we send out the publication saying, okay, we passed a test according to CGRE or some other standard, which of course is very important to have done. Those tests are like, what you see here is a picture of a dynamic flex test. So you have a test program that is called Dynamic Flex Fatigue program, but it is not fatigue. You set up a test program in order to provoke a certain damage, but unless you have done something fundamentally wrong in your design, you're never going to fail this program. So what is the important part is to do the material testing. For example, shown to the right here. When we test copper materials, steel armor, metal water barrier, we put it in at elevated temperature to simulate operating conditions, and we do tension testing to simulate, we get to establish the material curve of the material. That, together with friction elements, is fed into analysis tools that are used for designing the cables. And you do a flex fatigue test so everybody can feel happy afterwards. But the important part is the small-scale testing. 5 minutes left. Okay. I mentioned survey. I have to speed up a little bit. What you see here, this graph, is the consequence of if you do not do your survey correctly. The dark blue is the resulting current in the cable along the route. So this, for example, could be 80 kilometer long route with different cross sections and different thermal conditions along the route. This straight line here shows the cable sections and different cross section areas. So if you see here, the straight line, the purple line, is below the blue line, meaning that the cable has not got capacity to transmit the required current for the soil data. So what you do then is that you alter the cross-section to make it bigger, then it gets, of course, more expensive, and it gets heavier. So from installation and transportation point of view, then you ended up with something that is perhaps more costly and more difficult to install than you have to. And also for installation vessels, they are also like a constrained asset. So we don't really want time to go back and forth with an empty vessel. See, and what you see here towards the end, this is typically towards the land take, where it often gets really warm. And if you again here the survey data is wrong, you may end up that it's something that's not manufacturable. So you have a cross-section area of 2,500 or 3,000 square mil. There are mitigating actions. Should be a picture coming. Okay. One of the things you have, you got losses in the cable. You got in the conductor, where you actually transmit current, and you got losses in the screen here, and you got losses in the armor. One common method is to reduce the armor to have the hybrid armor, so mixed steel with plastic. It doesn't have the same impact or impact capability, but it gives you reduced loss in the cable. Another thing that we have developed to reduce losses in the screen towards shore is something called single point bonding. As I mentioned, you have current in the screen of the cable. That gives you losses, and the cable gets warmer than it needs to be. So basically, when we approach the shore, we put on an isolating screen on top of the metallic screen. So the plastic screen normally is semiconducting, so it's continuously grounded on the length. But here, we want to prevent the current going in the screen. So it's grounded at the point, and then it's prevented to go in the section that is in the warmest period of section. So by doing that, one can increase the current capacity from roughly, one example, 880 amps to close to 1,000 amps. Hence, you get a lot more power transmitted through the cabling by using this technology. And we are also currently using this for ongoing delivery. Wet or dry insulation system. I'll do it very brief because it's 2 minutes left. The insulation system around the cable, it's either wet or dry. Wet meaning that water is allowed to diffuse into the insulation system. And for high voltages, it does age the cable. So you have to prove that it doesn't age the cable more than the duration or lifetime of the field. So for all the inter-area cables, there are wet design, and a number of suppliers have qualified 66 kV cables for that operation level. For 145 kV, Nexans have one long track record and one project. And we are currently also qualifying according to Stiger standards for wet design 145. It's 2-year testing is ready in roughly 3 weeks, so that's quite exciting. We've done accelerated testing, that was fine, that was 3 months. I have to speed up. So dynamic cable, got a massive track record for medium voltage cables up to 52 kV. Field proven for one project for wet design for 40 years. Qualified dry design by using a longitudinal welded sheet. And we made a prototype for 245 kV. installation. Here you see our facility again, then with the new tower. Not any dark clouds anymore, looking all gloomy. As mentioned, now if you don't do the survey, it gets expensive, it gets too heavy. And you want to avoid having additional chips because you end up designing the wrong cable system due to lacking survey. So summary and 13 seconds to go. So wet design is qualified in 2 weeks. We've done the accelerated testing according to SIGRAE. That is 3 months, 500 Hertz. That was done a year and a half ago. I have one system in operation. Quick termination for 145 kV. That is undergoing type test now. That's roughly 2 months, 3 months type test program. Dry design is manufactured, as mentioned. For normal export cables, it's qualified 525 kV DC and 420 AC cable. And the main cost optimization for cable system with current market is to look at survey and how can I optimize the design based on the asset I do have. Thank you.
Thank you very much. We've got 3 minutes for some Q&A, so you're not quite escaping yet. One question from me. You did a 52 kV dynamic cable in 1983.
We had a track record from 1983 going forward for medium voltage. The 52 kV was in 2008.
Ah, okay.
Yeah.
Very good.
Yeah.
And do you still offer dynamic array cables, 66 kV and stuff like that? And if not, why not?
Unfortunately not.
Okay. And is there a reason behind that?
Based at least on Nexans market strategy and manufacturing assets, it's the same assets being used for export cables, and it basically is more money in that rather than doing inter-array. So in theory you can still do it, but it's a bit more like a commodity.
Right.
So for the time being, given the current market, we can lean back and enjoy that.
So is there a danger of new market entrants taking away market share?
Okay, there are the other players that has entered that market. For example, JDR didn't have that technology a few years ago, but they and others have entered the market. So until roughly 2017, it is fair to say that Nexans were the leader in wet design cables. And we focused on that area, as well as doing umbilicals for offshore wind, oil and gas. But in 2020, management decided to abandon umbilical manufacturing as well as medium voltage manufacturing.
Okay.
Yeah.
That's a shame.
Indeed.
There's a question at the front of the room. Can we get a mic to Ricardo? Unless there's somebody at the back. Stop her running.
Thank you very much for your presentation. Do you see a market for dynamic export cable in floating wind?
Yes, fortunately. So we have running a qualification program with a client for roughly 3 years. We have a qualified 245 kV dynamic cable. So it's for the power from that wind park is roughly 800 megawatt. So we manufactured the prototype in August last year, and it has gone through it remains like roughly 3 weeks testing of one test, but otherwise it has passed all the material handling characterization, bedding testing, hyperbaric testing down to 1500 meter water depth, according to the test program. So that's one asset. And for other, it's early stage evaluation.
Thank you very much.
Oh, we got another question in the front.
So, just wondering, what's your thoughts on
standardization of cables and joints, the market being as demanding as it is, and it's so hard to fix the cables if it breaks offshore. So you foresee any standardization on these cables?
That was one of the tasks we were given by the client for this technology development I talked about. But since it was mainly for inter-array, we said so thank you, but no thank you. I see the driver for it, indeed. And given that it's so many kilometers, I believe it should be feasible to make it a standardized product. But good luck. It's a bit like we talked about for oil and gas for all years about how to make it standardized, but it often ends up being a specialized standard product. Because normally, if you can do some tweaks to it, you normally still do it because you save a little bit here and there.
So how's the waiting time then when you break a cable?
First, it depends on where in the world is, who's the client, is the vessel available, etc. So normally the time to repair a cable is depending on mobilization of the vessel and personnel. One have done it in a couple of weeks, but then you're just lucky that the vessel is available. But normally they are occupied, so broad term, 2 to 3 months-ish. Yeah.
When I broke a cable before, it was the cable jointer. We had a vessel, we had a spare cable, spare joint, but we couldn't get a cable jointer for 14 weeks.
Yeah. Sounds expensive.
Yeah. All right. Thank you very much, Oyvind.
Yeah, welcome. Welcome.
Right, taking us up to our final networking break before the last couple of presentations. Torfinn Gopas from Karmsund Port Authority is going to give us his point of view about port demand being out of sync with offshore wind port supply. Sounds like a fascinating topic. I'm very interested.
Thank you. Thank you for the opportunity to be here, talk about this topic. I'm quite new as a port the director and the CEO, but I started for January 1st, but I've been in the business for 20 years, so I know even though I only had 2 months in the job, I at least have 20 years in ports. So that's why my colleague Christine, who's been working with this for years, gave me this task to present it today. But I think we can give it a try. Oh, sorry. This is us. We are a public-owned port in Haugesund, where there's a lot of activity in wind. As you know, the Met Center is based there, and we have a lot of different in the supply chain and yards, which I will come back to, but this is us. We are a public-owned port by 6 municipalities in and around Haugesund area. We have been developing quite good the last years. We have some good politicians in the 90s that was what you call it, foreseen, that they saw our needs. So they moved us out of the city, but they managed to find an area that we still was able to expand and develop. It was close to the industry, it was close to the fisheries, it was close to the airport. So we've been investing and developing quite hard the last years, but not enough to handle the offshore wind demands, unfortunately, because there's a lot of other things going on as well. So this is the region that we're a part of. Very strong maritime region with shipping yards, shipping companies, and a quite good supply chain in that. So yeah, so we're based here with our main office here and our main port here out in Haugesund. But we're also building up a fishery port at Bømlo now. And we have the Able yard in the middle of the Haugesund actually, and also the Aker yard. So that's the yard Of course, we also have in Vindafjord the Westcon activities that are significant in oil and gas offshore yard. So there's a lot of things going on in the area, and that's kind of our approach into this as well. Being a public company, we have to both support and facilitate for these businesses in our region. We have public task, so to say. Of course, we're set up as a commercial company, so we have our revenue, and we're not publicly funded at all. We're 100% self-financed, as it says at the beginning. And we are now soon finished to develop this port, which is a multi-purpose port at the moment, but it definitely has this focus on logistics, containers, ro-ro. We're doing quite a lot smaller oil and gas projects at the moment, subsea projects. We have two mobile, LMM 550 cranes. So we have quite a significant, or in Norwegian terms at least, we have 300-ton lifting capacity there in the twin lift. So we're doing good activities there, but we see, as I said yesterday, now we're moving into a different ball game. And we were searching the whole region, the whole area, as I shown on the previous picture. Where can we find a spot that can do this? And we actually find a spot. This is our aluminium factory, Norsk Hydro, sorry, which is already situated here, has been here since the late 60s, has their activities, and it's an industrial regulated area. So in collaboration with them, we have done this area. Christine, as I said, has been working with this for years, working with the O&Ms, working with the developers, looking for the optimal way to do this. But as my headline is saying today, we're kind of out of sync. This is a 300-400 million euro project. And my biggest challenge is, of course, to finance that 2 years with the FID for me, 2-3 years before the FID on the projects that's going to use it. So there's kind of one of the key challenges. It's been said lately or yesterday, and kind of through the whole thing. You also had your approach to that, Alex. Of course, we can and shall utilize the capacities that we have all the ports today. But the thing is, the gap, as I look into the gap and the differences, they are so. The dimensions, they are so different here. If you saw Odfjell and their solution today, he compared their floater to the platform. So if you're gonna, and which more or less the same size, am I correct then? Than the platform that we were using in west of Africa? Yeah, more or less the same. So you build that platform that you can move around, do quite a lot with. But now for a smaller or for a mid-size wind farm, you have to build 30, 40, 50 of those platforms. We kind of set it in a little bit perspective what we're doing here, and that's definitely a challenge for us, communicating up with the authorities in Norway. And connected to the port discussion, they don't we're struggling to make them realize actually what these dimensions are. And there's been competing about the ambitions. That's no doubt about that. So we're up to, what is it, 400 or 500 gigawatts now, only in the northern part of Europe already. Then we're talking 25,000, 30,000 windmills or of these floaters. So we have it is a supply demand that is out of sync. This is 5 of the key points that came out of the report in Hague in 2023 that we have been addressing, and a little bit more into what the topic is for as also for today. How should we close the gap? What can we do to the? That's why I challenge the guys, or didn't challenge. I asked them or their view, how to finance this, and the answer is quite obvious. We have to find the collaborations, or some way between maybe, of course, public funding, private equity, some risk capital, or find a good package just to found it. We have to find the alliances. We've done some calculation on our project. Best case, we can do 5 to 7% of the market, or cover that with ambitions in the market today. So that's why we're cheering on all port initiatives, and will of course collaborate, because we don't really see how we can build an overcapacity of ports. That is, at least with ambitions and the way this is going with dimensions, further and further, or bigger wind turbines. We're struggling just to build sites or a supply chain that is big enough and efficient enough to handle this at this scale. So that's why we think a port and ports alliances and collaborations all through the market is very important to succeed in this. And even though we have a site that we've done with the developers and the OEMs have seen that we can do both 1 and 2 projects, it doesn't necessarily say that we have to do that. We might specialize in that port, but I think then we have to see a different approach from the regulators also. Local content is a huge thing here, and of course we understand that we have to that's what we on the project as well, but that doesn't have to mean that everything in the supply chain has to be local. Let's specialize, let's do and collaborate and do what's best where we have the competence. Even that was before me, if he's going to make cables in every country instead of every, it isn't. You're good at making cables at your sites where you're doing it. And of course, we might have to expand that to do that, but you can't make cables in every port in every country just to have that local content. So, and I think we need to think a little bit the same in ports as well. At least sit down together, do the best initiatives, and think it together. So we can find the optimized solutions for the port and the port infrastructure, and do our part to do this. So that's kind of my view on that, and how we can build bridges to close the gaps that we need in this supply chain. I'll leave it with that and have a few minutes for the questions.
Very good. Thank you very much. Yes, and the good news is there's competition. So, there'll be opportunities for even more cost reduction measures to get offshore wind off the ground quickly. So, questions from the floor? Or is everybody super keen to go get a coffee? And cake. I hope there's cake.
That was fun. Oh,
Is there a question in the back?
I thought I saw one in the back. But no.
No? Okay. I think you're free.
Very good.
Thank you.
Thank you so much.
Okay, everybody. Break now, and back in the room for 5 minutes past 4, please. I understand that some people are getting trains, planes, and automobiles out of here. Please make sure you return your feedback form before you disappear. The ladies at the back of the room will be willing to accept those from you. Otherwise, he cut me off.
heart starts beating, only love begins. Love calls and wanna know the score. I behind the sofa when it comes to my door. A burglar didn't break the seal. Looks like the heart takes time to heal. And I got love to give, yeah. Love to give. They say the future's unwritten, there are stories yet untold. The truth is we can change everything that will unfold. It's up to us to make the call, don't you know? Writing's on the wall. Writing's on the wall. Don't you know, don't you know, don't you know? They say our lives begin to end. Day we are silent about the things that matter most. Let's become defiant. It's up to us to make the call. Don't you know? Writing's on the wall. Don't you know? Don't you know? Don't you know? Writing's on the wall. Don't you know? Don't you know? Don't you know? The higher you climb, the harder you fall. It's up to us to make the call, don't you know? Writing's on the wall, don't you know? Don't you know? Don't you know? Writing's on the wall, don't you know? Don't you know? Don't you know? Writing's on the wall, don't you know? Don't you know? Don't you know? Writing's on the wall, don't you know? Don't you know? Writing's on the wall, don't you know? Don't you know? Don't you know? Writing's on the wall.
I know more than you think. All right. Thank you, everybody who stuck around. We're now into the final home stretch. And I'm very excited to introduce our next speaker, whom we have just jointly figured out where we knew each other from, which is always good. But Ferdinando here is going to talk to us from a developer's perspective on the port and supply chain readiness for floating offshore wind with a focus on Italy. And yeah, I think it's very much worth listening to, particularly as a developer's point of view, not an ex-developer's point of view. So here you go.
Thanks, Alex. Good afternoon, everybody. This is the last part of this excellent conference. I think everybody, I was talking to some of you, it's been very condensed. I mean, a lot of interesting topics. We are probably also a bit tired, so I'll try to be, hopefully, I mean, to present something interesting, and otherwise feel free to take a nap. No worries. I will not get offended. I mean, I will not be upset. One quick thing, I'm happy to see many faces that are known. With some of you I met a few years ago. To me, this means that despite the challenges in floating wind, I mean, we believe in it. People are not just jumping into other business. It is a good sign, and this also gives continuity to the knowledge building. So that's just a quick note. But let's start. So, by the way, my name is Ferdinando Samona. I am responsible for industrialization of the Italian projects portfolio of Bluefloat Energy and Nadara partnership. So I'm gonna, first part of the presentation, I'm gonna give an overview, high-level overview of the projects in Italy. Well, first, well, our projects, the partnership, Bluefloat and Nadara, and then just a general overview of the projects in Italy, and then I'll focus a bit more on the ports and supply chain. I would say more on the port part of the supply chain. So very quickly, who are Nadara and Bluefloat Energy? So Nadara, it's funny because they changed their name 3 times in the last 2-3 years. So it was originally Falck Renewables, then it's been acquired by the equity fund JP Morgan, and they changed the name into Renantis, which is probably the name that majority of you remember. But last year, JP Morgan decided to merge Renantis and another of their company working also in the renewable sector, Ventiant Energy. So from the merge of these 2 companies, Nadara is what has been created. Is a company with more than 1,000 employees, 4 gigawatt of portfolio, diversified in wind, solar, etc. Then Bluefloat Energy is an international developer specialized in floating. floating wind projects, developing floating wind projects. So they decided in 2021 to form this partnership, leveraging on the respective strengths, Nadara being very much knowledgeable in the local market in Italy, also in UK, and the Bluefloat being the expert in the technical expert in floating offshore wind projects. So today we have a project portfolio of approximately 12 gigawatt between Italy and UK, with a total of 11 projects. I'll give a bit more detail in the next slide. It's for majority of the project a 50-50 partnership. UK, 5 projects, Bellrock, Broshore, Scaraben, Sinclair, and Stromar, with the last one being also developed together with Ørsted. And in Italy, 6 projects. And the next slide will give a bit more detail on the Italy projects. Starting from the ones that are in the most advanced stage, on the top right hand corner, so Cailia Energia and Odra Energia, they are located in the region of Puglia, with a capacity approximately of 1 gigawatt, 1.2 and 1.3 gigawatt. Of course, this is the consented capacity. I think was a colleague yesterday saying the same. I mean, we are consenting a certain capacity and then planning to develop in phases. Quickly, the characteristics, or the main characteristics: water depth approximately 100 meters, distance from coast approximately 10 kilometers. So where we are with these projects, we have already presented the what is called the VIA Valutazione Impatto Ambientale, which is the EIA document. This has been already reviewed. We received the comments from the ministry, the minister who reviews that, the MASE, and we have already provided response to these comments, and we expect these projects to receive the decree, the VIA decree, so the award of the EIA very soon. Probably not weeks like Berium Bay. It was Galileo, Paolo from Galileo, but in a matter of maybe few months. And then we have other four projects located one in Calabria region, Minervia, and other 3 in Sardinia, Nora 1, Nora 2. I like to say in Italian rather than Nora 1 and Nora 2, and Tibula Energia. So we are a little bit, well, I wouldn't say behind, but we presented the scoping. We are planning to deploy the FLIDAR and do the offshore surveys in the next couple of years. For those projects, we are of course focusing let's say advancing, progressing more with these 2 projects for a number of reasons. So, yeah. Okay. This sounds like a political slide or marketing with the big numbers. But it is still worth mentioning some important number in terms of impact of these projects in the in the local supply chain and in general in Italy. So the investment planned for these 6 projects is approximately 18 billion. Of course, will be in phases again, it will not happen all together. We have recently commissioned a study to sort of scientifically define the impact of a number of job opportunities that these projects would create. I was talking with some of you in the coffee break that we've been asking to analyze in detail the direct jobs, so the jobs that will be directly created during the construction and the operations, but also indirect jobs that are the jobs related to the supply chain working around these phases, but also the jobs that will be created because of the 2 categories, direct and indirect, will earn and invest and spend money locally because of the services. It's called lavori indotti. I don't know in English, but basically is the further step after the indirect. So you have the direct involved in the phases of the project, and indirect the supply chain around, and then those created because these 2 categories will be locally spending money. And the number is impressive. We're talking about approximately 20,000 jobs, which I think is an important thing to highlight. Of course, we are very active in terms of local, regional and national stakeholder engagement, political stakeholders through Aero Association, very active in Italy and supporting the lobbying efforts to get, let's say, the rules adjusted and to make the business viable. Statutory consultees, WWF, Legambiente, these are very important. This has very important role, have very important role in Italy in terms of getting things done and supporting business. And then business organization, and of course, community engagement with university and etc. So I'm not a permitting expert, but I wanted to give a very brief overview of the permitting process, just to tie this with the current status of projects in general, not only Bluefloat Nadara, the projects in general in Italy. So where we are, where projects are in Italy today. So let's quickly and high level have a look at the permitting process. So the way it works is that you reserve the seabed and then you get confirmation through the EIA approval. You get the grid connection. You reserve the connection to the grid, then you submit the scoping. You do the surveys that are needed to prepare a robust EIA document. Then you get hopefully you get the EIA approved, and there is another step, an important step for the authorization of the project, but the EIA decree, so when you get the award of the EIA, this allows you or allows the project to participate to the CFD round. So this is a prerequisite. So that's really the big milestone to be able to participate to the CFD round. So what is the current status in Italy as of today? I think this slide has been updated in December 2024. There shouldn't be many changes. So we had in Italy more than 100 requests for grid connection. Approximately 50 gigawatt have been accepted. After preparing the scoping, 29 gigawatt have obtained the approval of the scoping, and out of this, 9 projects are at advanced stage of EIA, and this is the area where things get how to say. This is the group that you can expect to be the actors in the first round of the CFD in Italy. And of course, there is Barium Bay, again, the colleague from Galileo explained yesterday already, and they are actually very close to jump to the last group, which is formed by those projects who have already awarded the EIA, which today in Italy are only 3. So if we had a CFD round tomorrow, then there would be only 3 eligible projects to participate. 2 of them are bottom fixed, and only 1 is floating, the one from Divento, so COP and ENI and Cassa Deposito Prestiti. Name of the project is 7Seas Med. So that's down to the question when the first auction will happen. So we probably need to have a relatively large group of projects that can participate to the bid. That's one thing. But we, as you can see from the previous group, we have 9 projects. I have only 4 minutes, so I need to speed up. 9 projects in most likely to get the EIA in the coming months and therefore be able to participate to the CFD. Probably not all of them will get the EIA degree, but majority will most likely get it, and so we will have a reasonably large pool of projects that can participate to the first bid. So what is the point of showing the projects in Italy and the current status is that to go to the port side of the presentation, all these projects need a port. So very quickly, the audience is, skilled enough to know about ports and why we need ports. But very quickly to remind ourselves, we have in the top row the main components of a floating wind farm, and in the column the various phases of the projects. Well, I guess it's not a surprise. All these need ports. Wind turbine needs port for the integration. Floating foundation needs port for the assembly. Okay, someone may say, but you can fabricate and construct everything in the yard and then tow, fine. But let's say the base case, of course, different technology may offer different solutions, but the base case is that we need a port for the assembly. Then there is something that in the various conferences I've been attending, something that some very often is lost or underestimated is the need of a logistic base for mooring and anchors. These are big items in terms of volumes and weight. And it's not necessarily easy to use the same construction ports or deconstruction ports for those activities, because these require a lot of vessels to come in and come out, mob, demob, load out the material, go install it, come back. It's not that easy. So that's something very often underestimated. And of course, ISE, again, depends on the solution, but we need some storage and mob port. And okay, OSS is let's keep it on a side, but of course we need the O&M base as well. I'm not going to repeat the key port requirements. I think there was a good slide from Alex already. We know space, bearing capacity, there are key characteristics. Again, I hear a lot about these main characteristics, but I'm taking some notes. The way we want to represent it to give a bit better understanding of the ports that is not just about these main characteristics is the port universe is a lot more. Why is a lot more? Social, so when we developer need to make a decision on either private investment to develop a port or just a selection for our execution model, then we need to assess how likely is that the port can actually be ready and can be on time for what is needed. And there are social and political aspects, especially in Italy, very important. Local acceptance factors and cultural factors. Even in different regions in Italy, we have different way to approach it because different reactions, different perception of the business. Puglia, great. Sardinia, big challenge. Environmental constraint, aeronautical constraint, Brindisi, great port. There is investment that, together with Taranto, also because of decarbonization, the country is looking at, but there is a big challenge, the airport next to it. Cagliari, the same. Fishing constraints, navigational constraints, concessionaires. You need to talk to concessionaires, current concessionaires. You need to make a plan for long term. Port authority, some port authority are very well prepared, some of them are not. Trade unions, labor force, pollution. Some ports have, unfortunately, not very good stories. Security, accessibility, competition. So Nadara Bluefloat needs port for their projects, but there is competition with other developers. So again, another challenge. And then these are what we call the external factors that you can see in this universe as I think is the blue color. So this universe shows the key activities. Then the gray circle are the main parameters that everybody talk about, which is absolutely needed to talk about. We need to talk about those. But then all these external factors in blue, and then there are project-specific factors. Of course, depending on the technology, the ports needs to be developed or needs to develop a certain characteristics. So last three slide. I think it's adding time. Are you granting me time? It's okay. I can go for another hour.
Please don't.
It's okay. It's okay. Okay. No, thanks. Actually. So last three slides. Opportunities, challenges. 3 or 4 slides. Opportunities, challenges, and solutions. Again, this is specifically for Italy. So in Italy, we have a number of ports that are potentially suitable to become hubs for floating wind. What it means, if you don't have sufficient space or you have a lot of constraints around like cities, etc., then you can't transform a port in a big hub. In Italy, we have a number of them that are set that have the key parameters to potentially become a hub. Of course, some of the Italian ports are just dead, so you go there and there is nothing. So this is an opportunity to revitalize ports. Job opportunities, we talked already about that, and of course boost local supply chain. So the main challenges, so the first ones are not necessarily related to Italy, but it's general challenges, common challenge to any ports for our for floating wind industry. And in this conference, I think has been already discussed this point. We need to standardize as soon as possible. I think someone said already there are more than 100 of floaters, and it's great. I mean, I actually listened to very interesting presentation about floater concept. We need to keep working on that, but probably we need to look at that in phases. So for the next number of years of next projects, we need to start with something. I think there was the guy from Wood who said in bottom fix we started with a monopile which was small, and then it was becoming bigger and bigger and bigger and bigger. Fine, but it was still a monopile. So if you start from something, then you can make it bigger in the next project and next project. But one thing is making bigger, one thing is changing completely the design. That's a different thing. So, and I don't have the answer. It's difficult, and we are screening a lot of floaters, and we keep screening. We have to, and we will keep doing that. But somehow, the industry needs to find a way through that. Supply chain to understand the wind market, again, this is maybe more a local, in UK is probably well understood. In Italy, knowledge is growing, but still it is a challenge because you go and talk to some local realities, local areas, and they still don't know what we are talking about. And then third point is specifically to Italy. Again, I guess common with many other, few other countries, but specifically for Italy. So we said before, opportunities, there are a number of ports that are potentially suitable for floating wind needs, but all of them, and I'm saying all of them, there is no one, so all of them requires infrastructural upgrades, all of them. So we need to really start with that. Of course, investments are required, obvious. Government funds, private investments as well, but this is tricky because, I mean, we have been looking into that, but how to convince to invest, to do private investment if you are not fully aligned with government investment? You can't go another direction, so you need to have somehow a direction from the government. And then for the last point, I will spend the next slide just to give again a little bit more detail. So tight timeline to develop those ports. Why? In the first, in the top, in the first row, we have a typical Italy project timeline as of today. So we are expecting auction rules sometime in 2025. So there will be, so we expect that there will be a first CFD round and CFD award sometime between 2025 and 2026. Now, as of today, the rules, the FAIR 2 rules states that you developer have 5 years. Actually, we don't know yet to what, whether it is to first FPP, first power production, whether it is to first string or full COD. We don't know. But there is a 5 years time expectation for these projects to be somehow offshore operating. It is very tight. We are challenging with our lobbying efforts. We are challenging that. But if we consider that, then and we compare on with where we are with port upgrade timeline, the row below, then we can see that we need to start developing the ports, upgrading the ports now. because these ports to be ready is require as a minimum 2.5, and actually it is optimistic because it's not just the infrastructural work that comes at the very end of all the design permitting process. Developing a port is in fact like developing an offshore wind farm. So you need to get permits, you need to get a robust engineering work before you start working. Very quickly, again, I think it's been mentioned, the government is moving. I mean, they are doing something. We Italians talk always bad about Italy, but let's say also good things when we have a reason to do so. So they announced this bando, this basically they gathered already interest from port authorities to identify and select at least 2 ports in Italy that will be selected to become a floating wind hubs and receive fundings. It's not been 1 minute. Cool. It's not been announced yet which ports are selected, although rumors already point towards Taranto, Brindisi, and Augusta. So we expect this to be announced officially in a few weeks, and then funding mechanism will come. So we need to get ports ready, and then last slide, solutions. Of course, clear guidelines and timelines from government in terms of port funding strategy to enable private investment to solidify and align with this strategy. Early collaboration, of course, with all stakeholders, and close dialogue with all players on what is needed. So what the developer needs in terms of ports being ready, what is needed, and of course, act now. Thanks.
Right. Thank you very much, Fernando. I would like to ask Fernando, James, Vasilis from OWC, and Tarfin to head up on stage, where I'll join you for our first panel of this afternoon. We're going to do a half-hour panel now, open discussion. We're going to have a 20-minute panel now. James is going to abandon us halfway through. Okay. I mean, nobody's forcing you. Right. Thanks very much, gentlemen. Let's have a quick round just to remind people who we are, and then we'll go straight into questions. James, you want to start?
Yeah. So James Lawson, Offshore Wind Policy Lead at the UK Department for Energy Security and Net Zero.
Vasilis Markatselis, I'm part of OWC, part of the market stats team.
Torfinn Gerpås, Port Director in Port of Kamsen Port Authority in Haugesund.
Very good. So do we have opening questions from the audience? We're welcome to start that way, because obviously we didn't get a chance at the end of the last presentation. If we can get a mic over here, that would be wonderful. Thank you.
Yes, hello. Eric from Moorist. Question to the last speaker. The timeline you showed, is that your timeline or is it like Italian government timeline?
It is a timeline driven by the current CFD rules. So this will depend on when the CFD, the auction, the first auction will happen. But then it's driven by that, because once there is a CFD award, then you have 5 years. What has been shown is based on the fact that we expect to have the first auction, I would say in 2025, but between 2025 and 2026, to be diplomatic, let's say, to be, not to promise ourselves too much. But then once you have that date, everything is connected.
Thank you. It's a good question. I think it leads actually to one of our questions. We've heard a couple of times today from yourself, myself, and also from the others that when we're looking at the port investment timeline requirements to actually achieve the planned deployment of offshore wind and floating wind, we need to be investing in ports now. Now, clearly, the UK is leading on many fronts in terms of the FLOMIS and that sort of thing. But could there be more? And where do you think that the gap is going to be filled?
Guess that's coming to me. I think it's a good question. I think one of the big constraints on that, particularly from a government perspective, and I think it's the same across Europe as well, is that budgets are incredibly strained at the moment. So trying to find a source of that within government spending is somewhat difficult. From a UK perspective, we do have a government that is very interested not only in offshore wind, but in the ports question itself as well. And that's why we do have the likes of the National Wealth Fund, Great British Energy. There's another number of other public sector organisations that are looking. The question is, I guess, not necessarily in the UK, not necessarily about where a single source of funding comes from. It's how do you coordinate amongst all the things that are already there? Because as I had in my presentation, there's a long list of things that are already out there. It's how do you make sure that we're not just funding little bits of each port? It's how does that all come together into a funding stack to make sure that you're actually getting the capacity that you need rather than just having a few potentially stranded assets further down the line.
Thank you. Vasilis, from your research, which bits do you think should be prioritized? If you were going to...
In terms of port activity or... so I guess in terms of FLOMIS and OMIS to a lesser extent because that was fixed bottom, but FLOMIS focused initially on the integration activity because our understanding at the time is that manufacturing and assembly, it's much easier to transport components to one site and assemble them and then tow out from there. The immediate need is having that port that's in close proximity to the site of deployment. So the integration is first, then it's about how do you get the manufacturing and the wider supply chain on there, and then that's kind of when you get to the point of having a multi-port strategy.
Very good.
Yeah, that's well said. Just to add something, like all the countries, they are announcing ambitious floating wind targets and all that stuff. Fixed bottom floating wind is in the market. But my perspective is that there should be like port hubs to support offshore wind. That's going to be like Port of Nig and like in the Inverness that has already been mentioned. So we need a lot more port hubs that could serve not only floating wind but also fixed bottom projects like offshore wind in general. And yeah, innovation is a key, like as you pointed out very rightly in your presentation. So yeah, that's my perspective.
Okay. And do you think Italy is going to benefit from the potential of having a geographical cluster of port hubs, or do you think it's going to be an all or nothing approach like we talked about before?
Yeah, as I was saying before, there is a lot of potential actually for the port infrastructures in Italy. We screened almost all the ports, and it's incredible. There are areas with large space. Of course, bearing capacity, these things are completely out for all of them, except for some specific areas within some of the ports. But it's small areas that have been maybe reinforced for some specific work. But the space and the fact that nobody is using it is crazy. So, but you need the so yeah, it's about also political. You know, you need to understand how this development, port development, wants to be, which direction the government wants to take. There is no point for developers or even group of developers of just doing their own or building their own path. So I would say that it's more about getting aligned with the government plans and work together to again select maybe two to start with. And they can play a big role. We're talking about south of Italy, so potentially they can serve also Malta. I was talking with with Greece, of course, as well. Spain, yeah. I mean, I think there will be a point when we will have a sufficient number of projects where the ports in the country will cover their projects. But yes, in theory, in the meantime, today we have only Porto La Novelle. Only Porto La Novelle. So, yeah.
And obviously, you presented, Torfinn, the incredible investment that's being planned there, and that's a very definite need. Clearly, there is a responsibility as well to see that kind of strategic investment. How do you position yourself to make sure that you're the winner, though, that you're not like drowned in too many people saying we're going to do the same thing, and how do you also balance the coordination with local content strategies required with the neighborship and that sort of thing?
We have quite a different approach. We've been working a lot with developers. We've been working a lot with Norwegian government. We're also working a lot with the Scottish government and the things, the collaboration deal that they recently signature, and that's why we have a kind of eager approach into this and try to be active and facilitate some of those arenas that you need for these corporations to make it happen, because we know it's a lot of work. And in parallel, of course, we're working on the plan and the strategy and regulations for this is industrial, but it needs a little bit tuning on the project. So that's something we do in parallel. You have to go in full force.
Thank you. And maybe last comment before you have to disappear, but do you see the potential of there being parallel investment streams for neighboring countries' ports as a potential threat for the UK, or do you see it as an opportunity to potentially collaborate and make the most of it?
I think looking at the pipeline across not just the UK but across Europe as well is that I think there's great potential, as being said in other presentations, for collaboration between ports, and I think we're assuming that everything goes to plan with the rollout in both the EU and the UK, we're going to need all the capacity that we can get, basically. So I don't see it as a direct threat. I see it as an opportunity both to work together and also to learn from each other as well.
Yeah, I like the idea as well as the tit for tat, that if we're able to step up to the mark now and help the UK achieve their targets, then as Norwegian offshore wind starts rolling out, it goes the other way around as well. So yeah, I'm very hopeful that that's an opportunity, and maybe that is also an Italian, Greece, Spanish opportunity. What would you think? Do you think that it'll end up being loggerheads fighting with each other, or coordination?
I think that's very well said by my colleague here, but I believe not a single port can do anything, as has already been mentioned today and yesterday. So collaboration is key here, and we have been advising developers to use multiple ports to do the assembly, pre-assembly, whatever they have to do with to realize their project, basically, because there's not available ports right now.
Torfinn.
Yeah, just a short comment on that as well, because we got to remember we're building a continental, a European common energy market here. So we have to be able to lift a little bit the perspective from everything on local content and everything on local project. If we can find those synergies, especially now in the start, just to get things open up these bottlenecks, and in a theoretical event, if there are too many ports, then open up the competition or specialization within what you need. But at least in the start now, we need both the backing and the collaboration in everything to open the bottlenecks.
Thank you. Any questions from the floor for James before we let him disappear? Oh. Okay. Right, Mike's coming. Let's start at the back with Phil.
I'm sort of conscious that ports have other things to do than offshore wind. There's business as usual, and also defence increasingly. So I'm wondering how that can be factored in. So basically working with other sectors, is that potential to invest in ports which many ports will say it's rarely a bad investment. They are strategic assets long before offshore wind.
I can't remember who I talked to. It might have been you I was talking to earlier. But I think one of the challenges that we have in the UK as well is that from a ports perspective, I mean, we're a maritime nation, so you have ports that are well established. They have clear objectives. They already have revenue streams coming in. What we actually need to do almost is to convince them to take a risk on something like floating offshore wind and actually invest ahead of the need for it. And that's where the challenge is going to be. So whereas we're talking around a risk of overcapacity, excuse me, I think getting to the point of actually getting some of the ports to be able to do that is part of the challenge. And then it is looking at longer term how offshore wind can align with other things. I mean, some things may be incompatible. Having a container port and an offshore wind port may not work. But if you've got some other type of more compatible activity, whether that's like hydrogen, CCUS, another renewable technology, then there is potential long-term synergies there.
Excellent, thank you. There's another question from Eric.
Yeah, I have to ask this. I'm from More East, so we are manufacturing anchors and delivering mooring systems for offshore wind and oil and gas. But we are kind of close to maybe, I would say, setting up a factory in Scotland. But do I see orange flag, or are they a little bit red when it comes to UK versus Europe here? I mean, next month I need a visa with my Norwegian passport to go into UK. How would that be, to supply from the UK to Europe?
Ooh.
Yeah, I don't actually know how to answer that one, so I may have to take that one away.
No, I know. I mean, I've asked several people here during the 2 days, but we really need to find out, it's, because I want to set up in Europe somewhere so I can supply to the European market. I'm not sure about UK anymore.
Right. Ooh. Controversial. I like
yeah,
it.
that is definitely outside of my remit, so I'm going to use that as my excuse to dodge that question. But it's probably one more for either Department for Business and Trade or probably for DBT, actually.
Because it's a new license required, isn't there? It came into force, is it this week or last week, if you're going to manufacture something in the UK and then export it to Europe?
Yeah. Well, no. I mean, that's when we travel in. Everyone here does not UK passport, need a visa next month to actually enter into the UK. We want to manufacture somewhere in Europe so we can export to other European countries. Mm-hmm. And of course, we can be anywhere in Europe, but we want to be close to the market. And yes, we are talking to the Scottish authorities and all, close to, take a decision on whether we should do that or not. We talk about oil and gas, from Norway, Norwegian ports into UK and to and forth and so, but they are exempted. So that's oil and gas exempted when it comes to import, export duties and stuff. We don't really know if offshore wind goes into that category.
Another oil and gas exemption. I wonder if that has a cash value.
Yeah, so that is definitely outside of my remit. I'm not going to comment on oil and gas.
That's a good point, though. I mean, things are constantly changing, politically shifting. We're obviously in a very turbulent time, as the curse says, living in interesting times. So, it's a very, very good point. But we won't bully you. Any comments on that side of things and the changing political environment in terms of import and export, maybe a Norwegian perspective?
Yeah, we're kind of on the side, but a part of as well. So we're in between here. But I think it would be very difficult from at least the politician point of view with what we've just seen the last 8 weeks to avoid custom barriers or things like that. It is so definitely complicates things as well in a supply chain that has endless of, as you've shown in the map. That's only the challenges that we meet as ports, and you have a lot more than that. So yes, it's not going the right way, so to say. That we should in this.
Make sure you don't call your anchors Jack Daniels. Bertil.
it's a lot of money to invest in a port. Before you start the investment, you need to specify what to invest. How do you gather that information and make sure that it is enough long-term duration of that investment? How do you specify what to invest?
Yeah. What are the main upgrades required? What are the main pieces of infrastructure that we're going to need?
I can try to start answering at least. So we have some minimum requirements that are needed for almost any type of technology in floating wind, and ports are not ready to accommodate. So it's like we are starting really from the bottom of the minimum infrastructural requirements. It is a challenge to find the right balance between over designing, being over conservative. You can't, we can't pretend to have an over designed ports, because maybe in 20 years we will have a 40 megawatt turbine. I don't know. This is down to the standard, to the challenge of standardization. The way we are looking at it is in phases. So we will have a first, let's say, round of projects in the industry, and we can stretch the requirements up to a 21, 22 WTG. So the weights, the space requirement, the ring crane, the heavy lift. So the way we are approaching it in terms of the dialogue and also advice on how to invest, which requirements to refer to, is to take the sort of extreme already today. And then we expect that at some point we will have sort of stabilizing efforts in terms of pushing the boundaries of the technology. We have to. It will be also natural. So that's the requirements, how the requirements are derived today. But it's not an easy exercise. And there is also, a question on how to make sure there is a sufficient pipeline for the projects, for the ports that becomes that gets upgraded. So today, the way we are addressing it is making sure we have a dialogue with competitors. I think in another of my presentation, I was highlighting competition on some of the aspects of this project can wait. So we are working through, I mentioned Italian association like Aero, but there are different channels in different countries. And we have technical tables where all the competitors, COP, Galileo, us, we sit together and we set basically the requirements together. So that's how we are dealing with this aspect, which is, by the way, a challenge.
Yeah.
So just to add to whatever Fernandino, forgive me if I got your name wrong, Fernando said, from a consultant perspective, we look at the Flutter concept that the developer they selected, but also the project pipeline that exists, and we try to suggest, like in terms of like port upgrades and requirements, it's going to be like, what is the norm for that project, and then what is required for that project, taking into account all the other existing activities that the project has. So that's how we're approaching the port upgrades, or like the timeline that the port upgrades will take place.
And when we look at it as well from an investment perspective, I mean, I think sometimes the simple solution is let's just make lots of space. But as I was explaining earlier, sometimes the specialist pieces of equipment are maybe more important in the short term to try and get those ready and going so that we can make the best use of the space that we have available. I mean, I don't know which side of the fence you come on that one, so it'd be interesting to hear your point of view.
No, and definitely, but we see an upside in at least having a greenfield project because we have from the tunnel project that we're doing in the other part. We see we need that for logistics, and we have so much ongoing business. We could never achieve that there. So, but still, with the so unmature technology, we have to make some choices along the way here. And of course, also we have a potential of 660,000 square meters. We doesn't necessarily have to do all at once, so that's kind of maxing is in the first phase there. So and depth, we have very good depth, but now down to 24 meters for us. But we know that aren't sufficient for all concepts. So there are some natural limitations also. So that kind of rings with it. But a crane, yes. I would be skeptical to invest in at least long term for a one that can do 12, 15 megawatts when we see we don't know where it's landing yet.
And from a consultant's perspective, I see this. Obviously, you guys see hundreds of projects.
Yeah.
Do you see more of a trend now towards let's future-proof and aim for 40 megawatt turbines, or is it coming back to 40 megawatt focus?
I believe we have stopped suggesting anything that it's more than 21 megawatt. It's also like following the norm of the turbine OEMs and what they have been going through the last few years. And yeah, it's always a chicken and egg situation with the supply chain. Turbine OEM suggesting a bigger turbine, and then others will have to follow through. Like having a bigger turbine, it will require a bigger in-voltage inter-array cable. So it's a lot easier to build something with existing infrastructure rather than investing to expand the capabilities, rather than expand the existing infrastructure to allow for bigger units to be built. So,
yeah, it's a good point. I think so. And that takes us to the next question, unless there's any other questions from the floor, and that is around vessels. We're talking about the construction activities. There's a lot of construction activities related to the vessels that can come in. Clearly, X-class vessels for the deployment of large volumes of steel structures, whether it's jackets, monopiles, or whatever, starts becoming a constraining factor. 270-meter long vessels with 90-meter beam. So where do we see the next vessel iteration coming? Is it going to be the heavy lift vessels that drive the port requirements? Are we going to assume that the heavy lift vessels are just going to focus on those ports that they know they can work with, and we have to cater to the BOAs and the COSCOs of this world's X-class vessels? Where do we see the vessel trends happening in collaboration with what's happening with the turbine nonsense sense sine curve? Thank you, James.
Got scared by the question.
Yeah.
Would you like to answer?
Now, I gotta admit, I've not been back enough in this business to have that big, deep dive into where the vessel is going. But as we are trying to adapt for both on this terminal, and going more for the what you call lifting vessels, or these jack-up than maybe at least a ring crane now at this stage.
Yeah, just a comment from me. I mean, floating wind has been built also with the idea that construction happened in ports, so you don't need these large vessels. Of course, heavy lift vessels, jack-up can be a solution specifically for the turbine WTG integration. when you don't have other solutions, and I think it's been mentioned in the conference already. But I think in general is more about bottlenecks in availability of more standard, I wouldn't say standard, but more typical vessels. So anchor handlers, cable lay vessels as well. They're going to be busy. I mean, we have all the bottom fixed projects booking all the vessels. It's not going to be easy to find a cable lay vessel. And by the way, we need to install dynamic cables. We need proper vessels. We need vessels that can not only lay down, but also handle a number of ancillaries that are not usually present in static cables. So the question is more, is the, let's say, T&I contractors world investing sufficiently in new vessels to serve floating wind? And I think today the answer is no. By the way, I come from Maersk, you know, and investing in new vessels is a big decision. It's a lot of money, probably compared to upgrading one port. So we're talking about hundreds of millions. So I would kind of shape the question or the comment in a sort of not different way, but in a way to say, standard vessels that are needed. So when I say standard, anchor handlers, cable lay vessels, mainly these two categories, are we going to have enough sufficient number of vessels to serve this industry in the next 10 years?
Yeah, absolutely. I think one thing that hasn't been mentioned, I think, in the last 2 days is if we do have a tow-to-port floating wind O&M scenario, then we need a whole lot of anchor handlers, and I think that's sometimes overlooked. Although I have my strong feelings about heavy lift vessels, that's one boat, and if I need to have a fleet of 14 anchor handlers and multicats sitting around, then that's also a significant cost. But gentlemen, I think that we'll leave it there with the final 30 seconds ticking down. So I really appreciate your time, and please join me in thanking the panel. We've got one more presentation and then one more panel. And the presentation is from Louise Eftimiou from the World Forum Offshore Wind. And afterwards we will continue a panel session on the topic.
Hi, everyone. The room is still relatively full, so thank you for being here. Thank you. Thanks, Alex. Let me just get comfortable. Okay, so hi, everyone. My name is Louise Eftimiou. I'm with the World Forum for Offshore Wind, and today I'll be talking to you about the latest work of our Floating Wind O&M subcommittee on digitalizing the O&M phase. WFO, in a nutshell, is a nonprofit focused on promoting offshore wind worldwide. Through our events and working groups, we've created an international business platform where companies can get together to network, learn from each other, and advance their common and individual goals. Our members represent the global offshore wind supply chain, be that major developers, technology providers, insurance firms, law firms, etc. The Floating Wind Committee, which is what I work on, along with my colleague Agni Argiri, who is here with us, is basically a group to bring together the members to talk about this very topic. Across these 7 subgroups, we meet relatively monthly on a virtual basis to try to align on the key technical and commercial challenges. I'd argue we had a pretty good impact in bringing forth some of the major topics, one of them being, for example, major component replacement, specifically on-site techniques. I think we, with our last publication in the O&M group chaired by Ilmaz Bayati of Peak Wind, we were able to highlight these new technologies coming up and just legitimize them a bit further. Within the group, O&M group, we've decided to move away our focus from major component replacement to something broader. So this is digitalization of the O&M phase. This topic, digitalization, Industry 4.0, is pretty broad, but it's really all the technology that is key to helping and really transforming our ways of work and life. Within the renewable energy space in particular, it's really about reducing costs, integrating production technologies, storage, grid for a more affordable, performant, flexible, decentralized energy system. Obviously, digitalization impacts everything, and for floating wind, it impacts design, construction, installation. I think there was someone who talked about earlier today the using AI and digital twins for port utilization area, so that was cool. But we really focused on the O&M aspects of that. And so on the left-hand side, you see a kind of a summary of what it's supposed to do for floating wind O&M, and that's basically being able to monitor the asset better, increasing its reliability, minimizing downtime as an effect, but also making the operation safer for people, so either by eliminating the need for them to access the platform altogether or to do it at more favorable windows. And then finally, the fact that you have better oversight is supposed to help extend useful life. The key point I want to underline here, though, is that digitalization will be really helpful for enabling this holistic engineering approach we talk so much about in this industry. It's really about kind of combining different parameters, different stakeholders together to get a full picture of your asset. And in particular, digital tools will help improve the integrity management programs, which is basically better monitoring your key hotspots, critical areas that are identified in the design stage, ultimately getting real-time behavior, and then monitoring long-term degradation threats. And on that last point, historically in the offshore sector, we know long-term degradation threats are a bit tricky to monitor, and so digital twins will really help, and digital solutions, not just twins, will help solve this problem. In floating wind, we can categorize generally 3 main aspects of digital tools for the industry. You have condition monitoring systems, new inspection methods, and digital twin. Obviously, all 3 are linked. CMS data, inspection data feeds digital twin in the operational phase. Digital twins can inform inspection activities. Digital twins can also check on the CMS quality. And then between each other, the CMS replaces traditional inspection methods, and inspection methods can complement whatever your sensors are saying if you need to check something that's more sensitive, for example, cables. This is just kind of a broad picture of what condition monitoring system means for this industry in particular. It's about being able to track your asset performance in a way that you can identify a potential developing fault. So that developing fault is the key point. You're really having this technology to get a better understanding in real time and maybe even predict if something could and when could go wrong. I think all I'll say here is that there's a lot of innovation in this field. You have different sensors, gadgets, data acquisition feeds that are being developed, different companies trying to sell these solutions. I'll to say that there's still a lot of questions as to what exactly is the best combination of gadgets to support real-time monitoring. Does it make sense from a cost perspective? Does it make sense from an information perspective? Is the information that you're getting from some of these systems actually helpful and necessary? Moving on to digital twins. So this is a virtual, so we have a definition that we're developing. It'll obviously be longer than this, but for this presentation here, I'll just summarize it to the fact that a digital twin is a virtual representation of a real-world floating wind turbine, its individual components, and its environment. So the real-world asset and the digital twin are linked by data, so coming in and out of both directions. And I think the interesting point is that digital twins don't necessarily, well, their whole development starts before the asset actually exists. And this is kind of what we want to illustrate in this upcoming publication, to kind of map exactly when and where you are creating such a model and what it means for the whole project in general. So digital twins tend to be born out of in an ideal scenario, out of the design modeling exercises, and then from there, when the asset is finally in operation, it becomes fully a digital twin because it's being fed the inspection and the condition monitoring data from the system. And so I'll end this slide here by saying that the key kind of point of a digital twin is to help drive decisions. So if you have your numerical simulations from the digital twin model representing your asset in a very perfectly accurate way, and then you compare what that is modeling compared to what the condition monitoring system and the inspection data is feeding into it, you get to have on a dashboard, for example, a comparison between what is supposed to happen, what you actually see, maybe identify deviation, potential fault, and then that would guide either further inspection or maintenance or marine growth cleaning, whatever. So it's all about driving decision-making and being value-driven. We're working on how to kind of explain a bit in more detail how digital twins for the operational phase are formed. We've had about a dozen companies talk about their solutions within the subcommittee, each with different specific use cases, each with different ways to get that use case. And I think what I can just summarize here is that there are two main approaches. One that relies mainly on physics-based models, which, as the name suggests, understands, can kind of translate the external dynamics acting on the system with physical equations. And then from there, be very transparent, yet perhaps maybe more computationally intensive. On the other hand, black box models is the term for AI-based solutions that are helpful to map out inputs and outputs for, modeling the behavior of your system, of your turbine, but not necessarily understanding how that relationship works. So skipping a bit on the physics. All to say that this method here is more innovative, more new, but very helpful in achieving results in terms of like behavior and testing and maybe even bringing in more data to guarantee more accuracy. But because of this nature, it lacks physical meaning or interpretability for the internal states. Ultimately, a mix of both methods are used in the industry to make the best of both worlds, and we look forward to mapping out a bit more how that works as well. The uses of an operational digital twin are pretty clear. It's about reconstructing the dynamic responses and loads to improve structural integrity and reliability analysis. From that better understanding, you optimize power production of the individual turbine, and at a farm level, perhaps even optimize wake. And one key interesting benefit is the contribution of digital twins for advanced turbine control. So we talked a lot about that potential that need to improve turbine controls to fit the floating wind environment, and digital twins can be helpful for that. And then finally, thanks to that oversight, you get to improve your asset availability and conduct preventive maintenance. I mentioned earlier that digital twins and your digital solutions are supposed to drive decision-making processes, and this is kind of a map of what the capabilities digital twins could offer, using condition monitoring systems. And the floating wind industry will really see predictive and prescriptive maintenance as the main targets. Automated is the highest level, where you have a condition monitoring system, a digital twin informing on something, and then it automates an action from there without the need for a user to do anything. But in this industry, I think the main focus is on prescriptive and predictive maintenance. Obviously, a next question is how to scale all of this up. You're talking about a lot of sensors, complicated modeling that needs to be scalable and also simple to kind of compute. And the consensus in the industry is to adopt a sampling approach for these technologies, whereby you instrument one turbine pretty heavily, representing a specific cluster, and then using that information from that turbine to infer the behavior of the rest. So digital twins can be used for helping in that aspect, that sampling aspect, but they're also helpful to ideally refine the nature of the sensors you're using. And so this concept of virtual sensor is being thrown out a lot, which is really the idea of using sensors at one location to infer parameters or behaviors of places that are not directly monitored. So if you take the example of a mooring load cell, they're known to, monitor tension of the mooring line, but are also known to be a bit unreliable. And so one solution is to use sensors at the hull and convert that motion and position to mooring line tension. And you use a transfer function for that. There's obviously a lot of complicated technical details around that, but ultimately, the key aspect is that you have to be able to trust your digital twin, trust your modelings, your functions, so that it's accurately representing something that is not directly monitored. And so this leads to my next slide about trust. So to garner that trust for these digital tools, third-party verification is one aspect. We've had DNV talk in detail about their recommended practice. Their latest update was in December 2023. ABS also released a guidance note about digital twins in November 2024, and if I understand correctly, it's their first one. All to say that DNV echoed the need for the digital twin, the condition monitoring system, to be able to self-diagnose itself, and also the need to evaluate the competency of the user. So this is kind of a larger question with the incorporation of digital tools and digital twins in our ways of work. Is the user, the enterprise, is the workflow able to accommodate what the potential of these solutions are? And in this case, DNV did highlight the need to evaluate the user if it's kind of integrating that into the workflow correctly. And then one last point is that, interestingly enough, while this is about classification societies evaluating these products, we also see these societies incorporating these products in their other work, like design verification. Axelos and ABS partnered in November 2024 to use Axelos's modeling software and solutions for ABS's design verification work. So I mentioned that we've had a few companies talk about their solutions in the committee. They range from private companies, software providers, to research initiatives, to universities. All to say that there's a varying degree of expertise, experience. The ways of work, the offerings are evolving with how much technology is enabling. And I think it's interesting to see that typically the software providers kind of come from the design space, are offering digital twins, but we've seen companies who also sell sensors, who provide advisory on general O&M aspects, who provide advisory for installation or actually do the installation, and in more niche applications only provide analysis work for specific sensor data, and that's the case of the top right. This was a company who talked about how they can help analyze cable data in a specific, in a better way. Well, that was their offering. So the common denominator, though, for all of these companies is that they want to get involved early in the planning phase, because in specifically feed or pre-feed, because of course whatever decisions you're making from the design phase about your O&M strategy, about your condition monitoring structure, architecture, it impacts how much value these different solutions can actually provide. So I'll conclude in these last two slides about kind of the challenges. So as I don't think it was clear enough, but this is really an ongoing work. We really hope to help put this publication out in the next 2 months to build a better picture of what these technologies are supposed to bring for floating wind specifically. But this holistic view is what digital twins can offer, digital solutions can offer. But the challenge is kind of how to do that in a way that's not too complicated from a modeling perspective in terms of really getting that real-time behavior. That's the key challenge. Incorporating the condition monitoring and inspection data into the modeling too, that's also a challenge. And while doing this, being able to make it simple, trustworthy, and scalable. And so commercial challenges we see today, well, data sharing is one big one. We talked a lot today in the conference about turbine data being difficult to access. This is a key barrier to enabling these digital twins that can accurately represent turbine data. And then on another level, even linking directly condition monitoring systems to the turbine controller, just kind of streamlining that relationship better. And yeah, just integrating these digital solutions into workflows. It's still in the early stages today. Some projects are working on integrating that, but yeah, as I said, early days. And then more general issues about insurability for preemptive repairs. So insurance clauses tend to only consider failures as they happen, but is there a chance to perhaps modify those clauses to consider preemptive repairs, and so this was a topic discussed in our group, and then the overarching cybersecurity AI regulation issues. So yeah, I think that's about it for my presentation. This conclusion kind of recaps what I just said. So there's a lot of potential for these digital solutions. It's just still in the very early days, and the fragmentation of the business environment, you have so many players providing different things, makes it a bit difficult to understand how we can incorporate things optimally and so forth. And so I think we see early projects kind of testing around with the idea at the pilot scale, and it's still a lot to be solved for how we can deploy this commercially. So I'll leave it at that for now. So thank you.
So you're finished a little early. That's wonderful. That means we can start the panel a little bit earlier and save questions for the panel.
Sure.
So final panel session of the day. We've got a couple of new faces as well. So look forward to that. I'd like to ask Jonathan Love, O&M lead from OWC. Louise, you're already there. Bertil from Windeed is going to join us, and Arturo Anderson Chinbua from the Carbon Trust. If I can ask you up on stage. And I suppose I should join you. Or throw things from a distance. Right, first things first, if we can introduce ourselves and remind people what our roles are, and obviously we have some new faces.
Hi all, my name is Arturo Anderson. I'm a senior associate at the Carbon Trust. I manage the Offshore Wind Accelerator Logistics and O&M, which basically focuses on fixed bottom offshore wind, but with many parallels with floating, as well as many of our floating offshore wind JIP projects.
Well, you have all seen enough of me. I'm Bertil Moritz, founder of the Windeed company.
Hi everybody, you probably haven't seen me. I'm Johnny Love of OWC. I'm the O&M lead and also a senior project manager at the consultancy, and we support developers, owners, operators across the spectrum of offshore wind. I focus mainly on O&M concepts and strategy development, but we leverage the expertise across our company and our overall ABL group with services like marine warranty on major component exchanges and things like this.
And Louise, WFO.
So digital twins, it's a fascinating topic. In 2011, I was sat in an office, a dank office in Aberdeen, with a company, I believe they were called Sea Energy, way back when. And they had just completed a digital twin exercise for an oil and gas asset. And it was a generating asset, and they had actual like 3D videos of the inside of this structure, and you could go in and you're able to click on every individual component, and it would bring up live sheets of the latest status reports for everything. And then the whole thing disappeared, and nobody ever used it again. GE spent a fortune on it. And this seems to be a recurring theme with the digital twin exercise. Where are we getting it wrong? Why is the digital twin not taking off and becoming the standard requirement for any offshore structure? Where are we that we keep having to come back to, well, there's got to be some way that we can mimic what's happening offshore? What are our thoughts?
I'm happy to start. I mean, very briefly, if I were to guess an answer at this very big question, is that it's just really complicated, and it's, you know, the numerical methods, AI methods, computational power, all of this is new and has kind of come up really fast, and I think we need time to master that, if that makes sense. And obviously, as I kind of mentioned in my presentation, the ways of work are not really equipped to handle these correctly. And I don't know how we can transform our whole ways of life and work to accommodate this, but I think this is one of the major barriers to digitalizing these assets fully and using them. Yeah.
Would you say, sorry to hijack, is there an element of who owns and is responsible and can access the different data types? The whole IP issue, and you hear about, this is not my area of technical expertise, but data bricks, the data lake, and there's so much information, but we can't make head nor tail of it.
Yeah, I think that's one issue for sure. Like for floating wind projects, as the example, data is coming from so many different stakeholders, and it has to be captured in one system ideally, and that's still something that's not possible or yet. Ideally, you have your design model that's kind of has everything already, and then that can seamlessly become a digital twin later, but that's not what we see today.
I think basically that it's about aging. If you have alarms, you don't really need digital twins if it's a leakage or whatever. But if you don't have enough input data of what the real world is, you can have a model that predict how much of aging in terms of lifetime, of the fatigue lifetime. And then you can shorten or make it a longer inspection or lifetime. And biofouling is, for instance, one example where you don't know how much it will grow and so on. But basically, I think that it's more important to have this digital twin in the beginning because what can be tested in a test basin can improve the bundling of the whole system structure. So it's the information and knowledge-based increase of real big full-scale turbines can be supported by digital twin to make a better modeling.
I'll probably only add like a few points to what everyone has said. I think I definitely agree with Luis with the fact that digital twins have to be implemented from the very, very early stage. To give you an example, last year, the US Department of Energy roadmap for offshore wind came out. Not sure how valid it is at this point, but it came out. I did participate with some of my colleagues in that specific document, and digital twins were mentioned. But digital twins were mentioned with the idea of we really do not know how certain materials that would be used in commercial floating offshore wind turbines will actually react. So having as many sensors as we can, having as much information as we can in real life will kind of allow those digital twins to help technicians and help asset owners to sort of understand when they have to go offshore and maintain those turbines. However, one of the main issues that was highlighted from the very beginning is data means different things to different people. And when that happens, it could well be that two digital twins, exactly the same, being viewed at by two different technicians might actually react in a different way. So I think one of the things that was maybe, I think it was Luis who also mentioned it, like maybe the standardization of the results and having some sort of like AI-enabled and trained system that can sort of aid whoever is in front of the screen might allow to have a standardized approach to dealing with digital twins and hopefully have a greater use of digital twins by industry.
Alex, if I may make one more point.
No.
Just to build on Arturo's point there is that we're seeing developers asking for project lifetimes to be extended significantly beyond what we might be seeing at the moment. So to improve project economics, 25 years is, we forget about that. We talk about 30, we talk about 35, maybe longer. So it doesn't answer your original question about where have the digital twins gone, but perhaps it highlights the importance of understanding the long term of our long-term performance and health of these assets to make the economics work.
Let me just build in an additional question, Louise, and then I'll come back to you. But where do we see the tacit, tangible benefits for O&M to a digital twin as well? Just coming to that point, talking about extending the lifetime of the asset and that sort of thing. But how do we see that tangible benefit so that we can actually market the benefits of digital twinning?
So that's indeed still a question. I think the business case is not yet established. There's still a lot of education and discussion about that. I'm aware of a few studies who quantify the OPEX benefits of digital twins. One in particular for the CoreWind EU project talked about, I think, 15% per megawatt of benefits, but it was a very kind of simplified study. And then Peak Wind also has the numbers. I can't quote them right now, but quoting benefits. But I think we heard yesterday from Aker that they also are evaluating it, but are being a bit conservative on the actual benefits. So yeah, benefits are different from different studies and maybe not extremely high or visible as we'd maybe like. But I think the other point I wanted to add from the earlier question was if you were to ground a bit how these technologies are being used in floating wind today, I remember we had two initiatives talk about their digital twins for floating wind and how they were able to access existing project data to validate their system, but they couldn't do so successfully because the project data was just not enough. It was not good enough. There was issues with, missing data and accuracy. And I think this is where we're at. It's about like understanding what information we need already to then allow these systems to be validated and operate. So it's very beginning.
I'm not really that acquainted with the actual economic benefits. I mean, the only thing I can probably add is based on the work we did with the US DOE, they did believe that the savings would be quite substantial. Reason why they were sort of trying to push this from the beginning. However, because they haven't really built any floating offshore wind farm at this point, they really didn't dive into any of the actual economic.
And I'll just add, like, from a CapEx perspective, like to acquire all the sensors and all that, that's also still a question. It depends on the project was one of the answers we've gotten. It could range from, a few millions to tens of millions. I don't know, but yeah, I think definitely more work is needed to quantify it and then just explain that and share that.
Hopefully, though, enough to shave a few percentage points off the 26% LCOE associated with OPEX that our Norwegian friend shared earlier on. I think it's a good investment, to be honest.
If only developers could be convinced to spend more money up front to save money later. Ask me later. Right, moving on from digital twins. I mean, where do we see the big innovations in O&M at the moment? What do we think is going to have the most material impact on reducing O&M expectations? I mean, bearing in mind where we stand in terms of the floating wind deployment rates at the moment, we're still at the beginning. But what do we think is the big innovation that's going to take us? And you're not allowed to say digital twin. That's the last topic.
Sure. So based on some of the projects we've run through the Offshore Wind Accelerator, we sort of have an idea that the next frontier for us is basically moving from remotely operated vehicles, being that drones, being that like small vessels, which now have been trialed and tested with a mothership around, basically, passing on through a more autonomous type of robotic systems. There's a few projects which are now being undertaken by different developers, which whom we collaborate, that are trying to sort of work with the beyond line of sight, with the idea of having a system that is completely autonomous, but at the same time having someone that is able to sort of look at what the actual system is doing or control the system, but from shore. And that would actually have such a massive reduction in cost, considering that you don't need to have vessels, you don't need to have, obviously, all of the crew and all of the technicians that might need to go with those vessels. So that is the area where we see the most benefits. However, there's obviously I guess a regulatory aspect that has to be taken into consideration. And from what we have seen, especially in the North Sea region, considering that the UK and the European Union has different regulations when it comes to this, having an alignment between regulators of like different countries within the North Sea is probably going to be the next frontier for us.
Well, I go into some concrete specific stuff like tightening bolts, for instance. Well, there is a possibility to install flanges that doesn't have to be retightened ever during the life. Once this is done, you don't need to go into the tower and do the tightening. So that's already available, but the reluctancy of the service provider, because that's where they make their money. But one of the biggest thing that was put into the Economist 2.5-3 years ago was the problem of in situ replacement of very, very heavy parts. And there are some exotic things trying to climbing up or having 3 steps of various increased size of cranes. But in the end, it's interesting also to repair a yaw bearing. So you have to lift the whole nacelle down, and it's 800 tons. And there we have worked on a solution where you can mate a lifting device with a floater, which is quite complicated in the sea. Once you are mating them, you come to the same result as a bottom fixed, where you have a reference, so you avoid any relative motions whatsoever, which is necessary to have the accuracy 150 meters up. So I would say that is one of the innovations. This is possible to mate 2 big the floating devices, so you can have no relative motions, and then you can do in situ replacement of whatever heavy stuff you like.
Yeah, I like that answer also. I think there's an element of project specificity. I don't think that's a word, but specific to each project in this answer. Because of the different technologies employed, your floater type, your location, whether you're in the North Sea or the Mediterranean, you've got hugely different metocean conditions that you're contending with. And I think that speaks to ultimately trying to keep availability high and accessibility high. So being able to get onto the turbine when you need it to, rather than face long delays, and keeping that turbine spinning when otherwise it may need to be shut down. So we're talking about innovations to do with vessel technologies, walk-to-work systems on SOVs, or the Get Up Safe system to allow personnel to transfer from a crew transfer vessel in more extreme wave conditions. Not allowed to mention digital twins, but the condition monitoring and the predictive maintenance elements, making sure that you can take steps to proactively maintain your assets rather than react to failures and causing downtime. Quick connection, disconnection systems for cables so that you don't lose a whole string when you have to perform some maintenance on a turbine. There's lots of little small innovations, but specific innovations that add up to, I think, a great big picture in terms of keeping, like I said, accessibility and availability high. But it's completely different, I think, if you're out in the middle of the North Sea, or you're in a bit more of a sheltered position in the Mediterranean, for example, as to actually where the saving comes from, because the accessibility is different and your distance to port, for example, is different too.
I'm good. I think I talked about my point of view about the innovation, so I think you guys covered the rest.
So trying to combine the last 2 topics around the ports, but then also about the innovations in O&M. So where do we see the port operations having to be adjusted for floating wind? I mean, there's the obvious one of tow to port scenarios and having to have a big crane. We've kind of talked about that one. Is there any other areas that we need to be mindful of when we're thinking about planning for the future for floating wind? Bertel, maybe I'll come to you first as a designer of a floater. How do we maintain your structure most efficiently and effectively?
The best way is to avoid any need for maintenance whatsoever. That is the best way. But in the case where we, for instance, need to tow it to port, which should be avoided, it's important that the biggest cost in OPEX is lack loss of revenues because waiting for the weather windows. And the second thing is waiting for the specific vessel to arrive. So I think it's important to understand what the facilities are in the port. If there are facilities which can do the job rather than waiting for a specific vessel which are not there, you have always to monitor the options to minimize, which is the most important thing, minimize the two things, which is the downtime and the waiting time for a vessel.
I mean, if you can build something that doesn't need repair, that's definitely the best option. I can basically talk about like one of the projects we did a few years ago, and I think we had another project which literally just finished a few months ago that you can find it online, available to everyone, that looked into heavy lift maintenance for floating offshore wind and did some comparison between a tow-to-port heavy lift vessels, which I know you're not really in favor of, nacelle mounted cranes and temporary nacelle mounted cranes. And for instance, in terms of the actual cost of maintenance, tow-to-port, it is super, super expensive. We have a few different projects which are now running, which are looking into things such as a wind turbine integration into ports. And you're basically going to have like a similar issue to when you have to maintain a floating wind turbine. One of the things is, do you actually have a sufficient quayside to have especially more than one turbine at a time? If you don't, are you going to be able to expand your port size? I think someone mentioned this morning, or maybe it was yesterday morning, which basically might misquote that person saying that it was like prime real estate area where you kind of expand a port. However, there's a lot of risks when it comes to floating offshore wind if there's no clear pipeline and if there's times where the port is not going to be used. So it's a risk for the port developer. One of the questions I have maybe for yourself or maybe if some of the port operators are still here in the room, if there's maybe an option in which once a port has been expanded to cater to floating offshore wind, if parallel operations could take place in between floating offshore wind and some other industries that could maybe fill that void in between projects to ensure that there's a sufficient pipeline for actual ports to have that incentive to develop their capacity. You can answer later.
I think I'm a fan of the approach that was described earlier, Alex, with different ports being specialists at different things. Someone mentioned about trying to win. There's a huge prize to win for the ports. I think there's enough of that pie to go around, and we should focus on the sort of natural attributes and the infrastructure that exists and look to maximise that opportunity. My concern is that what's been deployed at the moment in terms of floating offshore wind is only a tiny fraction using, I guess at the time, large WTGs and large floaters. But what's in the pipeline now is on another scale. It's absolutely enormous. The 15 megawatt machines and beyond are huge. And that means everything scales up to the vessels that are required. The cranes, hook heights, quayside lengths, drafts, anchor handlers were mentioned, also the sizes of the anchors themselves, the chains, the mooring lines. It's all getting really, really, really big. And yes, there are ports with prime real estate, but let's try and maximize that to the best use of it to its fullest potential. Otherwise, Arturo is going to have to redo his study and update the cost model because the costs of vessels and all of these components and the lost revenue from bigger turbines is even greater, meaning this becomes a hideously expensive activity to have to undertake. So even more so, yeah.
I'm allowed to mention digital twins, am I? Yeah, because one thing is missing in digital twins is they're going to keep our crew and our technicians alive. when we move to 15 megawatt turbines on floating bases, your CTVs are gone, especially where you're putting them in the water. People are not going to be climbing that height on two moving structures. You're then onto SOV technology. You've got too few turbines to make an SOV efficient, but we're going to have to use them. If we're putting gangways across, we already use digital twins now to make sure people are safe going across gangways. But we need the dual feed. We need the information coming back from the turbines and the turbine movement, because this is not going to be easy. No matter the gangway manufacturers and the vessel manufacturers will tell you at the moment that they all can do it and it'll be easy. Trust me, you know, we're at 3.5, well, 3.25 significant at the moment on a gangway. That's a 7-meter wave potentially coming underneath a vessel. Now, we wouldn't get a green light at that condition, but we need to know those waves are coming. We need to know the impact that it's going to have on the turbine, and we need that 30 seconds, 45 seconds in advance. So yeah, when you're thinking of digital twins, please don't just think about maintenance, think about health and safety, because that's what they're there for, in my view. That was a bit of a preach.
No, that's fine, Stephen. The experience speaks for itself, and to share that experience, I was presenting at I'm trying not to say the word Ampleman, a gangway conference not that long ago, and there was a video of a floating wind farm that we all know and has been mentioned lots today and yesterday, and it was a glass calm. There was maybe micro ripples on the surface of the water, and the gangway operator refused to let the turbine technician get into the tower, because then the camera pans up and the tower is doing this. And there's no visible reason, like in terms of weather, it was about as perfect as it could be in environmental conditions. But when you're 80, 100 meters, 150, 200 meters up in the air, the conditions can be so vastly different to what you're seeing on the surface. It just terrified me. And having done my turbine and height training in a 50-meter tower and knowing how much that wobbled, I can only imagine. Anyways. Yeah. Anybody come back to Stephen's point?
I mean, I agree, and we had like a figure in my slide does include the safety aspect, and I do look forward to developing it further when we prepare the work. So thank you for the comment.
And I suppose, Stephen, as well, with the array of foundation structures types that are out there, the access methods for those is even more complex in terms of your walkway, the landing pad, transferring loads across. So yeah, it's not just a straightforward operation from A to B. There's a lot of variables. Appreciate that.
Yeah, I mean, I think like everyone else, I will completely agree. I used to work in health and safety in offshore wind. So I've seen many incidents considering like having walk-to-work gangways and so on. So, I mean, I do understand the industry is obviously trying to develop personnel transfer systems which are motion compensated and so on. But the idea of actually having two moving objects and people passing through them is actually quite scary, because especially when you see incidents happening just within the fixed bottom offshore wind, you sort of know that the potential within floating is going to be significantly higher.
I think it's very important that the design of the floater and the whole structure is such that it really minimizes the motions, because it should be ultimately as easy to service a floating device as a monopile. That is the ultimate goal, which is almost possible actually if you do it right. So it has another requirement on the immunity of the floater in the water, and that's a health personal health issues.
Thank you. Yeah, I just sort of reflected on your initial question. Why hasn't it taken off with the digital twins? And well, to me, it seems we have these big visions for digital twins. So everybody can agree to, the all-knowing digital twin, perfectly calibrated from day one, with all information sort of flowing into it. And then when we want to know something about something, then we look it up because it's all there, the information. And I think we underestimate what would that take to create an updated model with all the information from the designer, the turbine manufacturer, IPR protected things, with all the measurement channels feeding in, constant calibration without knowing what we're looking for. I think that's a big task. So I think that's maybe why it has been a buzzword for so long, because yes, would be so nice, and who can achieve that? And then on the other hand, one can think of much more pragmatic solutions. So condition monitoring. Am I able to detect a vibration that is out of the usual vibration spectrum? Yes. Okay. Then there's something I need to go and look for, right? If I hear a special noise in my house, I will also go to the basement and see, did I forgot to close something, right? That's my picture of it. So maybe that's a very trivial way of thinking, but interested to hear your comment on that.
Yeah, I mean, from my perspective, it's about data sharing, right? And I think we've talked about it a couple of times. You know, who owns the data? Where's the IP as well within that data? And are they willing to share it with other parties? And with the propagation and self-propagation of AI, how do you control that information sharing in the future? And you know, I think there's a related point around some of the O&M innovations that I mentioned briefly earlier. A lot of the innovations I see about cranes and nacelle-based stuff and things like that, it's brilliant stuff. And you know, I wouldn't be able to come up with these things myself. But as a purchaser of these solutions, they have to come with a warranty that is backed by the appropriate body. And if the digital twin is provided by a third party, whether it's a university or the Carbon Trust or somebody else, but they can't provide a back-to-back warranty with the Vestas, Siemens Gamesas, whoever's of this world, to say that, yes, I confirm that is my thumbprint. If that system tells you there's a problem offshore. How can I, as an ex-developer, granted, but how can I take that step, even if there is a potential 15%, reduction in cost?
And I just want to completely agree with your comment, Henrik, because it's indeed super complex of an operation. And this concept of like calibrating your model, feeding in data from different formats, different time series continuously, it's a lot of work. And as Henrik had said, you don't know exactly what you're looking for. It's just about getting that real-time behavior. And this is something that's extremely complex to do. So
maybe the car is a good example, right? I think modern cars, of course, they have many sensors. Mm-hmm. And of course, there's monitoring of these sensors. You need more oil, now you need to replace this and that. But I don't think they run a real-time model of what the car does. I think it's all based on something I can measure now. Then we have programmed the warning to come, right?
But that top-down warranty, right? So I buy a Skoda. Skoda says, I call them and say there's a problem. They look at the sensors and they say, VWAG, this is an issue with your part, or Samsung, it's your battery, or whatever. But I'm just calling Skoda, right? And that's in floating wind, even when we have an EPCI wrap, a turnkey contract, whether it's, I'm going to name names, Subsea 7, Yandandol, Boskalis, Saipem, Herema, any of them, you don't have a one-stop shop. At the best of times. We're still using FIDIC Silverbook, for God's sake, for most of our offshore wind contracts. And that is designed for onshore civil construction. And it has been amended to try and make it more appropriate, but the pass-through of risk doesn't represent the true risk to the operator and the warranty holder in the end. So I get it, but you need to have the umbrella corporation that is able to take that responsibility for, I agree, there's an issue here, let me fix it.
Thanks.
So I think one of the things I can probably add from our experience, we tried to develop products, solutions for industry, open to all of the industry, and feeded by our partners, which are developers, and many of our advisory groups, which have many different OEMs in them. So I kind of see the problem, but at the same time, I feel that the same as we have with many other areas of fixed and floating offshore wind, it's like, how can we together as an industry collaborate to standardize many things? And that could include digital twins, that could include sensors, that could include like a range of different things. However, as long as there's no incentive for the industry to collaborate, it is going to be a very hard sell. Coming from a health and safety background within offshore wind, I used to work at the G+, where a lot of data sharing was done within different developers, and us as a third party would analyze the data to understand main trends and develop systems that could work for everyone. I feel that type of working together can sort of be expanded into many other areas that can help industry. However, there is a very big barrier to that, and it's basically everyone trying to develop their own thing to be more competitive compared to the other companies, basically, which unfortunately doesn't really allow for that sort of level of standardization, even if some of us try to push towards it.
Only just to riff off what Arturo was sharing, in my background was in innovation at the UK's offshore renewable energy catapult, and we were always trying to foster that attitude of collaboration. I was at the catapult and filled with hope and aspiration that I would see that future very, very, very soon. I was chatting with Phil in one of the breaks that there's still a culture of competition from acquiring seabeds and CFDs and IP and the best, very best, and winning and beating out the competition. And I'd love to see that change. I talked about ports. Everybody can win. There's a big prize to win. I think we need to adjust our expectations a little bit and be open to that collaboration, multi-port strategies, etc., etc. Something needs to shift. I think it could be that, but it's a very big thing to shift.
I think I'm good from my side. Thank you.
Well then, unless there's any other burning questions from the room, I would suggest that we close the panel session there. So thank you very much for your insights and the conversation. It's a very pleasant conversation. Thank you.
Thank you.
I now stand between you and freedom. And as you haven't heard enough from me, I wrote a small play, which I'm going to perform. I am, of course, joking. There's no play, just for anybody who doesn't have a sense of humor. So, first of all, congratulations. Well done. You made it to the end. Virtual medals for everyone. If I could give out badges, I would. You can have mine. And yeah, thank you so much for those of you who've stuck around right until the end. I hope it was worthwhile. I certainly got a lot out of that conversation and all the ones before it. So it's been good for me. I took the liberty of writing down some thoughts on the state of floating offshore wind, and I'll read them out verbatim if that's all right, and then you're all free to go. Of course, you can leave anytime, but I'm going to read out. So, floating offshore wind is at a crossroads. The technology has proven itself to a degree. Demonstration projects across Europe and Asia have shown that floating wind can operate reliably in deeper waters where fixed bottom turbines simply weren't viable. The potential is immense. Vast stretches of ocean could be harnessed for clean energy, opening up markets where conventional offshore wind was never an option. There is an element of democratization that we have to admit is now feasible with floating wind. And yet, despite this promise, the sector is struggling to scale. Costs remain high, supply chains are still fragmented, and the first large-scale projects are facing delays, regulatory hurdles, and inflationary pressures. Investors and developers are nervous. Governments have set ambitious targets, gigawatts of floating capacity by 2030, which is just around the corner.
But the reality is that the infrastructure, port facilities, and industrial expertise needed to deliver those sorts of targets are still catching up, as we talked about. What we need now is not just a leap to industrial scale deployment, but more demonstration projects to figure out what technologies we're actually going to deploy. Are we doing monopiles? Are we doing jackets? Are we building a Ford Mondeo or a Bentley Continental GT? We don't know yet. We still need to prove it. Real-world pilots can refine designs, drive down costs, improve bankability. We need to test different floating platforms, mooring systems, and grid connections in a range of environments. These demonstrators will build confidence in the supply chain, reduce risks for investors, and create the stepping stones to full-scale commercialization. But there is hope. Floating offshore wind is not just another industry. It's an innovation-driven sector that has already overcome immense technical challenges to get where it is now. The cost curve will bend, just as it did for fixed-bottom wind and solar before it. With strategic investment in demonstrators, collaboration between industry and policymakers, and a steady, stepwise approach, and a reasonable step-by-step approach to scaling up, floating wind can become a cornerstone of the global energy system. The technology works. The resources are there. The challenge now is to bridge the gap between promise and commercial reality. And history shows that when the world truly commits to a clean energy revolution, it delivers. Thank you very much for your attention. We'll see you next year.
Coming here today and joining the discussion. Thanks to all the speakers and all the interesting presentations. Thanks to our sponsor today, of course, Windid, and big thanks to our chairman today. Alex, thank you so much for your guidance through this day and for chairing all the panels as well. And of course, we look forward to receiving your evaluation. It would be great if you can hand it to me or my colleagues' evaluation form, or if you didn't have the time, you can find it online or on our platform and just put it there, so we will receive it that way. If you have any questions, please do not hesitate to write to me or any of my colleagues, and I wish you all a safe journey home. Thank you all for coming. Thank you very much.